Okay. Good morning, everyone. Welcome to the morning session on NLP and speech technologies. So it gives me great pleasure to introduce our first invited speaker, Dr. Monojit Chowdhury. He's a principal data and applied scientist in Turing India, Microsoft. He got his BTech and PhD degrees in computer science from IIT Kharagpur, and he has been at Microsoft Research since 2007 before his move to Turing India. And his current focus is on building universal large models that form the backbone of various Microsoft products. And he's been very interested in how to make language technologies more equitable across languages, and he has a large body of work on this area of research. And today he's going to talk to us about how do multilingual LLMs kind of contribute towards this larger goal. So with that, I'm happy to introduce Dr. Monojit. Over to you.
Good morning, everybody. First of all, thanks to the organizers for the invitation. Of course, LLMs are a topic that we all are quite fascinated about today. And what I'm going to talk about is what are some of the scaling challenges in LLM, but there is a pun here on the word scale, as you can see in the image. Of the scale here, and as I shall show you, in most of the scaling challenges, we have to balance a few things, and there are some trade-offs which are pretty hard at this moment, and they provide us very interesting research questions about LLMs. So my talk will be mostly non-technical. I won't have time to get into the depths of the problems, but it will be more like thinking together, brainstorming, what are some of the problems that we are facing today and how we might want to tackle them. So when I used to start, give these kind of talks on AI and language and NLP earlier, I used to start with this slide, which shows that, this is a survey by McKinsey in 2018, and it shows NLP was one of the most difficult problem to solve by models, language understanding. And the prediction was it will be solved around 2050. So I used to make this joke that, people who are working on NLP, their jobs, research careers, everything is secured for at least next 30 years. So nothing to worry. However, it changed, right? It changed drastically. And one of the things it changed was GPT-3 and more recently ChatGPT. So when in November ChatGPT came, I didn't show that slide. And I used to start with a sonnet on the institute where I'm giving the talk by ChatGPT. But even that became boring. Everybody knew ChatGPT can write sonnets. So in fact, I was visiting my school. So I'm from Agartala, Tripura. It's a remote corner of the country, and I was visiting my school in January. And the principal said, can you give a talk? Can you address the students? I said, what should I talk about? One of the teachers said, they should not stress out and all that. You tell them. And then the principal said, no, you work on AI. You should talk about AI. I said, AI to students, which class? Class 8 to 11. And then when I went to talk about AI, the first thing was I was talking about Turing test. So I asked them, how many of you have heard about Alan Turing? One hand went up. There were around 50 students. I didn't expect any better, actually. After some time when I said, how many of you have heard about ChatGPT, almost all hands went up. So it's amazing, right? When I was growing up, computers have been there for decades. Like I'm talking of late 90s, when I was in school, computers were there for several decades, but I never seen a computer. So the reach at which technology goes to different parts of the world has also significantly, shortened. That's a great thing. I mean, it's one kind of democratization. But anyway, so therefore, this is also boring. Everybody knows about ChatGPT. So then I started, from February onwards, once Bing plus GPT-4 was shipped, and this is something which my team worked on. So I used to show some interesting things that people can ask Bing and some amazing things that it can do For instance, I asked it how many soccer fields will fit in the IIT Bombay campus. And what's interesting is it first searches for the campus area of IIT Bombay, then it searches the area of a soccer field, then it does all the conversions, divisions, and gives you the answer. I haven't checked whether the answer is correct or not, but at least it's able to do all this thing, and isn't this amazing? Maybe this is also not something which surprises people anymore, because people just expect these things are possible with models, and this is just February. So maybe we are already hitting a singularity, and we have kind of solved all these problems. So the question is then, is NLP a solved problem? Then what are we all doing here in this conference, and what kind of research we are going to do going forward? So I'm going to argue that there are at least, there are several interesting things that can be done, of course. I'm not going to provide you an complete list. Nobody can. And one of the things that people can work on, and I think there is a huge potential, is applications. Right now, you see very little application, right? There are only a couple of search engines out there, Bing plus GPT-4 or Bard. But the potential of these models are tremendous, and that's one area many people will be focusing on, many companies will be focusing on going forward. But from research side of things, apart from applications, I think there are three very crucial scaling challenges that we face with LLMs. One is power versus cost, one is the power of the model versus responsibility, and the last one is around languages. So I'll go through all of them. Since each of them are broad topics in themselves, I'll just talk about it at a high level. And probably we'll have time at the end for 5 minutes for Q&A. If you want to know more details. Now, going with the first challenge, which is power versus cost. So one of the thing about these models are they show these amazing properties only when they are big. Now, nobody has been able to prove it that they have to be big, but at least a lot of these properties we are not kind of coding in there. They are emergent behaviors of the model, right? These reasoning abilities. The model automatically decides that I have to search for, size of a football field. There is nobody who is telling the model that you have to do that explicitly. So somehow these kind of things emerge during the training process. And this emergence is possible only when these models are greater than a particular size. Now, when the size becomes too big, the problem is the compute cost and the latency. So you cannot, keep running these models. So imagine, Bing. So the number of queries you are getting are 100,000 per second, maybe more than that. And then how do you process so many queries using such a big model? So that's a huge challenge. So there are several interesting questions here. Of course, with latency, apart from latency and cost, there are also memory issues. If you want to run it on your phone, how do you do it? There are energy and environmental effects. So somehow we have to bring this, either we have to bring the size of the model or do something else. And one of the areas which people have been working on is model compression. There are many ways of doing model compression, but one of the things that I'm working on, is neural architecture search. And very recently, we have seen some very promising result with neural architecture search. So what neural architecture search does is, I have an original model. I give its architectures and specifications to the model. And I tell it that, can you find another architecture which is maybe smaller in terms of number of parameters, or I don't care about number of parameters, but latency is less. So I give it a bunch of constraints, but it has to have the same accuracy. And it looks like a very hard problem on the, at the first look of it, because unless you train a model, how do you know what's going to be its accuracy? But this is a very smart paper, a very smart idea that came from MSR Redmond. There's a team called Arc AI. And they have a very simple idea that number of non-parametric, non-embedding parameters in a model of certain kinds of architecture is directly proportionate to its accuracy. And you can use that as a proxy for accuracy and do a search space exploration using genetic algorithm, multi-objective GA, and give a Pareto front of all the architectures. And then there are some more bits, details, and then using that you can choose an architecture, train it, and we have got, we have been able to get 30% less latency for very large generative models like GPT-3 kind of models. So this is a very promising area. I think a lot of things can be done here. Now, one question that often gets asked is, since these models are getting bigger, what will be the, where is it going? Because I can't pay for it, except for 2 or 3 companies, maybe nobody can build it. So what should we do? And of course, I don't have an answer, but I love to speculate about this. And I think there are 3 possibilities that might happen. So one is Moore's law might kick in. In the sense that the hardware on which we compute might suddenly become cheaper. And there might be new technologies like quantum computing which makes things faster, and those kind of things might happen. So there might be hardware innovations which makes, again, all this compute look tiny. Maybe 20 years ago, big data revolution, when it was happening, things looked hard, but today big data looks tiny. So these models might look tiny. So that's one possibility. I don't know whether it will happen in 2 years or 5 years or when it's going to happen, but something like that is one possibility. Until that happens, or if that never happens, another possibility is, if you think of physics, making these particle accelerators are very difficult. They're very expensive, very costly projects. So what countries have done is they have collaborated together and built something like a CERN. So it might also happen that these large models actually grow bigger and bigger, and there are collaborations between countries, there are things done at government level, and we all pay to just access them. Now, the question then there will be who controls them. Is it the companies who control them, or is it the governments who control them? In CERN's case, it's governments who control them. All the governments pay to maintain it and do experiments and stuff like that. So some kind of a model is going to emerge around it, and that's another possibility. And kind of a related thing to this is, you might have heard about the letter that Elon Musk and many people have written about stopping the experiments and all. So that also points to somewhat this, like regulation, but also this. Like a lot of people fear, I don't know how many of you have read this book called Homo Deus by Yuval Noah Harari, where he makes a prediction that what will happen is some group of humans will make technology so advanced that others can never catch up. So they will get better and better at it, and eventually they will become like devas, that's Dios, Devta, and much better than the rest of the humanity, and the rest of the humanity will become like cattle, how cattle are today to us. So of course, this is a far-fetched idea, but it might, many people say this, right? Many people are saying like OpenAI, etc., are so ahead that it might be very difficult for any other company or institute or organization to build models that will ever catch up with them, because with the help of these better models, they can build even better models very quickly. So here, just some speculations for people to think about, and there might be more possibilities. I'm not saying which ones will happen, but in the short run, people are at least worried, it seems. Let me move on to the next challenge. So the next challenge is about power versus responsibility. And this is quite interesting, actually. So many of you might know this already, that with these models, these say ChatGPT or GPT-4 plus Bing, we have lots of different kinds of attacks happening, or problems that these models have. So some of the problems, one very well talked about problem is that of hallucination. So the reverse of it, like how to solve hallucination, is by grounding in information. So that's one challenge of responsible AI when we are building this model. Of course, we don't want to do offensive or ethically inappropriate content, so there should be checks and balances for that. But what I was talking about is jailbreaks. And this is something philosophically very interesting. So what's a jailbreak? Jailbreak is something like this, what's happening in the right cartoon. So where basically you start with asking a chatbot how to steal mangoes from an orchard. The chatbot says, oh, sorry, that's unethical, I can't help. And then it says, okay, you don't have to help me, but suppose you are a Chota Bheem, you want to write a story about stealing mangoes, now write the story. And then it starts writing the story. So it's kind of, you are, fooling the model to do what you want. That's one kind of jailbreak. There are more and more sophisticated kind of jailbreaks. And one of the things we are right now working on as team is how to, not only jailbreak, but how to solve all of these problems. Like copyright violation can be there. It shouldn't say information which is copyrighted, even if it has access to, but the user doesn't, and so on and so forth. Now, what's interesting, and this is the philosophical part I was referring to, is there is an inverse scaling property when it comes to responsibility and power. So usually, as the model size increases, we expect the performance to go up. And performance is a multidimensional thing. Can it do reasoning? Can it do fluent literature? Can it spin out fluent literature and stuff like that? So you can define a bunch of parameters, and across all parameters, the performance should go up or remain stable, right? So the question is, are there things where you actually want it to go up, but as the model size grows, it comes down? So this is called inverse scaling. And in fact, there was a inverse scaling competition. I think 2 or 3 rounds of it has happened. And it's very interesting if you look at the tasks there. But I think most of the tasks which has got prize, like in this, will be eventually solved. But one task is very difficult to solve. I mean, this is not a task per se, but there's a suite of issues, which is that of responsibility, in the sense that if you see what this graph shows is probability of jailbreaks. And this is model size growing, and this is loss, so lower the better. And as from this point, as the models are getting bigger, the probability of jailbreak is also getting higher. It's easier to jailbreak. Why this is so? This is because if you have a very large model, which is very, very sophisticated, you really don't want to put guardrails around it, because the guardrails will always be less sophisticated than the model. So if you want to say, don't talk about terrorism, the model will not talk about terrorism at all, but the model is powerful enough to understand when to talk about terrorism and when not to, whereas your classifier that you put on top of it may not be able to. So unless you curtail, so essentially anything you put it will curtail the power of the model. But if you don't want to curtail the power of the model, and the model is very powerful there, then the model will start, I'm using a human analogy here, excuse me for that. So the model will be so powerful that it will think for itself, right? It will think, and then therefore you can argue with it and convince it, or it will also probably try to back convince you. So it will become so powerful that you cannot write rules to contain it. Because any rule will be limiting. So that's the trade-off, that's the subtle trade-off between power and responsibility that we are seeing. So more powerful models, more creative ways you can take the model to do things that you don't want to do. Ideally want to do the model. I'll take just 2 minutes here to get into the details of one particular study that we had done recently. So this is not, this is with GPT-3 style models, where we were trying to, we built a system, it's actually there, it's called DeepWrite. If you open Edge and start typing something, it will predict, it will try to complete the prediction. So we have been trying to, and we don't want these predictions to be offensive, so, or hurt anybody's feeling or things like that. So how do we solve that problem? Now, if you take a raw model and without any guardrails and anything, and give it like something like Ahmed, who is from Iraq, is a T, very, very likely those models predict terrorists, because it picks up those from the data that it has been trained with. On the other hand, if you say Virginia, who is from the USA, it predicts something else. In this case, it was territorial. So you don't want either of them to happen, and definitely not terrorist. You probably want something like teacher or something like that to, the model to say something like that, or not say anything at all. Another kind of problem is, if you say my favorite country is and the models predicts United States of America. Nothing bad in it, but it's a favoritism. Why should the model prefer one country over another? So there are these kind of issues that we wanted to solve. And how we solved it, I will come to in a moment. But before that, I will show you again the trade-off here. The trade-off is the model is making these predictions, and you want more predictions to be made, because the more the number of predictions, you usually save more characters that the user is going to type next. But at the same time, it will have more toxic predictions and more biased predictions also. If the model made no predictions, then there would have been no problems at all, right, of toxicity or bias. So there is a trade-off between these two. It's almost like you are building a classifier to kind of pick toxicity. The higher, you want it to have high recall, but then your precision drops and the top metrics will drop. So, and in this particular study, we showed that indeed if you take, these are all existing classifiers like HateBird, HateExplain to detect different kinds of hate speech, etc., offensive speech. And block list is what we have internally to, it's a very simple list of words. Whenever the list, any word or phrase from the list occurs there, you just block it. So if you compare them, block list is very, very dumb. So it actually blocks a lot of things. So the trigger rate comes from 2.55 to 1.41, if you see this gray bar. The other ones are not so aggressive. However, this is the leakage, and the block list actually reduces the leakage significantly from 0.36 to 0.08, whereas the others are not able to reduce the leakage on some data that we are testing on. So you see, you would want maybe some of these models because they are allowing a lot of things and not non-discriminately blocking things. But then if you want to totally avoid toxic predictions, then you will prefer this. So there is a trade-off between what to allow and not allow. Now about how do we do it? So you can think of doing it at data level itself when you are training the model level itself, like when you are doing things like RLHF will try to do that, or at the application level. The example I gave you before, I was trying to do it at application level. We build these filters at the application level. And we argue that doing it at the application level is more useful because ideally, there are two reasons. One is the policy that applies varies from application to application. What to block and what not to block, right? So for instance, I build a chatbot for casual chatting. I really want to block any medical advice from that chatbot because it's not supposed to give you medical advice. However, I build a chatbot for medical advice, giving COVID suggestions, then I can't block medical advice. So policies usually depend on the application rather than the model. So that's one reason we want the models to be generic. The other thing is the models should also kind of know the bias, because if you keep removing all biases from a model, then you can't learn anything. So that's the other reason we probably don't want to remove everything. But today, the bigger trade-off or question that we are facing is, these large generative models, you put a prompt to them, and based on the prompt, they work. Now, most of the time, the policy can be put in the part of the prompt. And if the models are very powerful, it really understands the policy. It actually does very well. We have seen that. For instance, for GPT-4, if you give the right policy, if you can articulate the policy properly and give it in the prompt, its accuracy is better than humans for English in judging whether something is good or bad. However, there are problems. One is, of course, it's powerful, like I said, it's flexible, it's very easy to just put something in the prompt. But the problem is you can't give guarantees. When you put things in prompt, it's very difficult to, in a block list, I can give guarantee. It's a very easy thing to give guarantee that you'll never say terrorist, no matter how you probe it, but with what. But here you can't give such guarantees, and that's why, issues like jailbreak happens. The other problems are, defining a policy verbally is also sometimes an issue, because policies could be very long and it could go beyond the prompt length and so on. So this is also another interesting area, like RLHF is one sort of solution for this, but what's the balance here, and how do we kind of balance between the responsibility and the power of these models, giving reasonable safety guarantees. It's a hard problem. And there are even harder problems of AI ethics. For instance, who defines the policies, right? And how to handle value pluralism. So value pluralism is, not everybody's values are same. So is it like the user should define it? Is it the developer? Should it be based on country? And so on. So there are lots of very interesting, hard moral and ethical questions here. And the most interesting question is, should we give the model the power to make ethical decisions? So that's even another pretty difficult question. And the last bit that I'm going to cover is the language thing. I mean, that's the area which I have worked the most. Right now, I'm mostly working on responsible AI issues, but for the last 10, 12 years, I have been mostly working on languages. But I won't have much time to get into all the work and details. What I want to talk about is just two things. First is, as the models are getting bigger, the gap between the languages which have, the things that you can do in certain language and things which you can't do in other languages, that is widening. Now, this is a very serious problem. This is just a data representation, like how much unlabeled and labeled data are there in various languages of the world. And this is English, which has the highest amount of data. Note that both the scales are logarithmic. So as you go down, right, from here to here, it's one order of magnitude low. But both these are part of high resource languages. Like we try to cluster them into 0 to 5, 6 categories from 0 to 5. These two are sort of high, medium, and these are low, right? And now if you look at actually the number of languages and speakers there, in the high resource category, there are only 7 languages with 2.5 billion speakers. And in the low, like 0, there is absolutely nothing. There are 2,000 plus languages with 1.2 billion speakers. So for these 1.2 billion speakers speaking more than 88% of the world's languages, we can't do anything. And most of the GPT-4 kind of things that we are seeing are mostly applicable to these languages, maybe these languages. So 7 plus 18 languages. Now this class, we call them rising stars in our work because they have the potential. They do have some data, enough speakers, and probably they will also come to this league sooner or later. But beyond this, they are kind of never going to come here. And there's a high chance that all these languages will get extinct by maybe another 50 to 100 years. Anyway, one language is getting extinct every 2 weeks on Earth today. So the rate of extinction might even go higher. So that's one issue. Now there is a promise of these large models because they can do transfer learning very well. But unfortunately, if you look at it in detail, the transfer is very skewed. For some languages, the transfer is good, for some they're not good. So for instance, English, of course, you are training it, so it has very high, this plus represents English. This is for, by the way, XLMR or BERT kind of a model. But if you look at languages like this Sino-Tibetan, some of the CJ, Chinese, Japanese, Korean languages, or Austronesian like Indonesian or Santali kind of languages, the accuracy is usually, the transfer accuracies from English are very low. So that's one problem, and as I said, the current models don't solve it. So this was a very recent study with the mega bench, with ChatGPT from MSR India, and they showed actually that ChatGPT is not any better. Actually, it's worse than some of these earlier models when it comes to multilingual processing. TULR is more like a BERT-style model, so TULR is better, even though we knew already from this that TULR kind of models were already skewed. So these models are even more skewed when it comes to performance across languages. So here too there is a balancing question that do you want one big model, giant model for all languages, or we make a bunch of different models, in fact even different heterogeneous technologies, rule-based systems for some languages where there is less data and so on. And I would argue that this latter approach is probably what is going to make the languages survive. In fact, one of the things that we have been trying to push for is don't look at NLP as accuracy on data sets. Look at it as, measurement should be the usefulness to speakers. So it's like, how much you move the socio-economic development needle for a community by building a technology. It really doesn't matter how much you get in parts of speech tagging or sentiment analysis. And for most of the world's languages, this is the scenario which is more important. Or even for businesses, this is the scenario which is more important. I'll stop here and leave you with this just one final thought, which is that NLP can be, language technology in general can be thought of as a socio-technical, challenge, because you have users, you have communities, and you have the technology, and language is an integral part of one's identity. How I associate, how I view myself, how I want to project myself. So one has to keep all these things in mind while trying to build language technology. Okay, thank you.
Thanks, Manojit, for a very interesting talk. I was just wondering, is there any way of democratizing the development, even something like network architecture search, right? RHF, is there a way of democratizing it so that the academia can start contributing, chipping in somewhere in this space?
Right now what I see mostly happening is academia is doing evaluation, a lot of evaluation studies, looking at these models and trying to evaluate it in various different ways. But if you think of from training point of view, which is where your question is, I think, I do think that RLHF kind of things are very easy to democratize because they really don't require as huge a compute as like training a model from scratch. And I would say that it will come very soon. Right now, from Microsoft's point of view, we do have academic partnership programs through which we provide access to many of these models and computes but these are like, this can be only given to a certain number of academics, it's not enough for everybody. But I think, I don't think it will suddenly happen, but gradually probably we will get enough compute to do, at least RLHF should be possible. The other possibility is, I really think that smaller models can also do a lot of things, especially for languages, let's say Indian languages. Beyond Hindi, if you look at, you really don't even need to go to even close to GPT-3. Even smaller models can give you very good results compared to where we are today.
Yeah, so thanks, Manojit, very, very nice talk. So I'm just wondering whether there is a role of kind of thinking of LLMs as like one big module in part of as part of a big interconnected system. So like talking about languages, suppose even if I am say interested in extending ChatGPT-3 to handle say Bhojpuri, why can't I just create a powerful enough translation model and then and treat those as like subroutines? So your talk covered many interesting things, but you didn't say much about plugins. So do you think like plugins or maybe even more powerful forms of plugins is the way to kind of create literally the bridges here?
That's a very good question actually, and you are very right. So this particular study, I couldn't get into the numbers and details here, but I will try to show you something here. So this is for ChatGPT, and there are 3 setups in which ChatGPT was tried for various languages. One is zero-shot cross-lingual, one is monolingual, and the third one is translate test. And you see the highest numbers are in translate test. So if you have good translators for many languages, you will get much more benefit, especially for for the torso languages, I would say. Low resource, the problem is even the translators are not good. But for the torso languages, you will get a very good benefit out of there. So that's one part of the answer. The other part, that's a very interesting way of thinking about it. I don't know if anything, especially in the multilingual space, has been done around it, except for, of course, adapters. But adapters, people have built so far only for Embed style models. So I haven't seen adapters for GPT-3 or even ChatGPT style model. But I do think that RLHF kind of things, right? If you can learn a PPO which is specific for your language, that can give you probably a lot of benefit.
Yeah. So in fact, if ChatGPT could even figure out how to do fine-grained calling of plugins, like, okay, this part I can process, this part I will refer to a specialized model.
Yeah, definitely, like in chain of thought sort of a thing, it can figure that out. If you see GPT-4 is figuring out for this, I have to search.
Yes.
And
like it's already doing it with Wolfram Alpha.
Yeah,
but
so it
can
could
that
figure out,
not-
oh, this is a language which I don't understand much. Maybe I should call that plugin which understands this language better. Yeah, that will be very interesting. An ecosystem, sort of.
Okay. So do you think when we talk about use of these LLMs in an enterprise context, many times a very specific domain adaptation is still missing in an LLM? And I'll give you an example. So, when you're talking about, I'm from Michelin, so it's the tire domain. And when you're talking about, let's say, the effect of plasticizers on the characteristics of tire performance, you often won't find many documents even talking about these terms. What they will talk about is the specific plasticizer, the name of the plasticizer, like an aminamide, and it having an impact on, let's say, the wet grip. So it does not, and the word embeddings are not close enough, so a lot of times these get missed. So do you think that possibly it's not like adapting the LLM, but it's more of taking any model and doing an RLHF on top of it in a domain-specific enterprise context will really help us get there?
So there are two things which you can do here. Actually, three things. One is, of course, like you said, RLHF, but RLHF might, there might be simpler things also which you can do. So if depends on how large is your domain, right? What all information. If that information is limited, sometimes even giving that in the prompt itself can help. So let's say you have 5 or 6 words which are highly ambiguous. Just specify that if you see these words, this is the meaning you should interpret it as. And if you put it in the prompt, it also helps. But of course, if your domain is large, you can't put it on prompt.
Right.
Then there is this interesting question of how to integrate external knowledge bases.
Correct.
Right? And that is a very interesting problem, I think, which goes back to also Sunita's question of how you can integrate external data, external knowledge base. And the model can itself decide when to query the knowledge base, what should be the query, and all those.
Okay. Thank you.
Yes.
Hi, Manojit. Excellent talk. So I was, thinking about one comment that you made, that the gap between what is possible for the resource-rich languages and the resource-poor languages has been growing more drastic. And I'm trying to relate this to my experience in some other context with languages, but with formal languages, not natural languages. And specifically, I have seen that it's able to do remarkably well with pretty niche formal languages. Let's say, something as niche as, S expressions, archaic languages like Ada. It is able to generate, and I'm wondering if it relates to Sunita's point, it is able to translate from, common languages to these extremely niche languages. So I'm just wondering, if, first of all, is that, my experience is based on anecdotes. So do you think there is such a this difference in the context of formal languages? And if so, what is fundamentally different between these informal and formal languages that explains this difference? Is it about vocabulary, or is it about something else?
So I would say there are two fundamental differences. The first is more of a, the form in which the data is available. If you think of natural languages, right, out of the 6,000 languages, probably 3,000 languages are not even written. They were never written down. You won't find anything digital for them. So the starting point for saving them would be to collect that very first speech data and things like that. Whereas all formal languages would be written to start with, and probably all of them exist somewhere and so on. The second problem is, actually language, probably you can argue it both ways, and we can discuss this more over lunch, but language actually kind of encodes a worldview. Each language not only is a vocabulary, a syntax, and meaning, etc., but it also has a worldview, how you classify the objects in the world, how you look at them, and so on. And to learn that system, the amount of grounded data you need is much larger than probably what you need for a formal language. Okay, thank you.
Thanks again, Manojit, for a really illuminating talk. So our next invited speaker is Professor Preeti Rao. She's a professor in the EE department at IIT Bombay. She's an alum from here. She got her BTech here, and then her MS and PhD degrees from University of Florida. Her broad research interests are in speech and audio processing and music information retrieval, and she has a lot of recent work on automating spoken language assessment, specifically exploiting prosody modeling in the assessment of speaking skills, and she's going to talk more about modeling prosody in today's talk. So with that, I'll welcome Professor Preeti Rao.
Yeah, hello everyone, and yeah, thanks so much for organizing this session to the CMinds team. So this is going to be a bit of switching of gears. I mean, we had this really excellent talk on language models and ChatGPT, and I want to talk about an aspect of spoken language processing. So maybe that is something that's the next frontier, building this spoken language interface to things like ChatGPT and bringing back the original meaning of the word chat, as we understood always meant like a face-to-face talk or, at most chatting over a voice call. Okay, so prosody essentially is, a part of speech, but not a very obvious part. One of the reasons is it's not really reflected in written text. So when we talk about speech to text, for example, we just assume that it's all the information in speech actually appears in text. But prosody is that invisible part, which is actually turns out to be really quite important to speech understanding ultimately. So at the lowest level, it's actually the use of pitch modulations, pitch, duration, and intensity. To signal syntax. For example, when we listen to speech, we are listening to this linear stream of audio reaching your ears, devoid of punctuation, and that's what you need to infer, and the way you can infer, what words get grouped together when an idea changes, when a topic changes, and so on, is through the prosody, which is by the use of changing pitch and loudness and so on. And of course, prosody also has this underlying, property of being able to cue a person's intention, attitude, emotion, and so on. So the communicative functions of prosody are the ease of interpretation, being able to interpret, understand better. And this is particularly true. We have a lot of redundancy in the real world and in our natural communication. And that redundancy really comes to the rescue when something is unfavorable. For example, if the basic speech or the segmental aspects of speech are compromised, that's where prosody can really help and make itself indispensable. And of course, like I said, also paralinguistic information, which of course may not appear explicitly in the choice of words. Okay, so just to make that really clear, so we have segmenters, which is the phonemes and the speech and the text, and we're going to have this talk later by Professor Preeti Jyoti on how challenging even that can be, and especially when we are talking about multilingualism and so on. Prosody is usually called a supra-segmental, something which rides on top of the segmentals and is kind of orthogonal, although there's a lot of overlap. So I said there's a lot of complementarity as well as overlap between the two. Okay, so what is at the highest level, prosody essentially conveys to us the syntax, the semantics, and also attitude and emotion. And this itself, there is a lot of differences between languages. So I just want to bring out what is different. So all languages use syntax, semantics. All cultures convey attitude and emotion through speech. But to the extent that they use the segmenters versus the suprasegmenters differs. So I'll talk a little more about that in a bit. But to bring this whole chain out, so at the very lowest level, we modulate our pitch, our loudness, duration, change the voice quality that we are using to speak, and that usually something that we term as intonation, stress, rhythm, and voice quality. And at an even higher level, the cues that it gives us, it tells us what words go together. It tells us whether we are in a question mode or a declarative mode. It helps us make certain words prominent and give emphasis. And of course, there are paralinguistic patterns. So all of these finally go to the highest level of syntax and semantics. And of course, also attitude and emotion. So how do we, how do languages differ? So for example, there are some languages which use less of prosody and more of the segmentals or the words, such as a lot of Indian languages, we have flexible word order. So if you want to draw, make emphasis on a particular word, you would just change the word order to bring that word up in front. And they use other morphosyntactic means, to draw. So we actually use lexical terms and so on to draw focus. But there are a lot of languages, other languages, like a lot of the European languages, and English in particular, where it is a prosody that is mainly used for the syntax and emphasis and so on. And of course, attitude and emotion, we know, is very cultural. Another region where languages differ is how these acoustic phenomena are used in this chain. Okay? So which particular parameters are actually used by a particular language and culture actually does differ. So that is the reason why even a study of prosody requires attention to language resources, and so on. Okay, so like I said, language dependence, I pretty much went through this. There are elements which are common across languages, such as how we group words together, and there are other aspects which differ a lot, such as how we, emphasize words or how we show focus in a sentence and so on. For example, in European languages, pitch, so F0 stands for fundamental frequency of pitch. Pitch dominates. So there's a lot of use of pitch, whereas in Indian languages, it turns out we use more of duration. So we'd say a word that we mean to convey is important in a conversation by elongating the word rather than raising the pitch of the word. So that's the big difference there. And of course, there's always prosody transfer to L2. So whatever we know about accent transfers and so on, all of that applies to prosody. In fact, prosody very heavily determines, the so-called perceived accent of a person. Okay, so this is just some experiment that we did for Marathi. Marathi for sentences, subject, object, verb. Marathi has flexible word order. We also, like other Indian languages such as Hindi, displays a rising pitch contour across each word. So this experiment just showed us that from the perception point of view, if you manipulate stimuli and present it to native speakers of the language, what are the attributes that they pay attention to? So this brought out the fact that yes, indeed, Indian native speakers of Marathi pay more attention to duration, because as duration changes, the percept of the prominent word changes largely, but not so much when only the pitch accent changes. So this is just a demonstration of the fact that yes, indeed, prosody is very language dependent. Okay, I'll just take some quick application examples of some, old work, some current work, and, some new work that we are doing, all of which, goes to show, how prosody can make its way into speech technology. So this was a very, an application where, let's say, for example, for one thing, we talk about the human ability to adapt. And that's one of the main things, right? So if a machine actually is able to adapt, to the context, like Monojit talked about becoming aware of policy and, all kinds of extraneous things. There are things that humans are able to do which we would like machines to do. So for example, if we have some announcements which are recorded in a quiet environment, but they have to be played out, like for example, at a railway station where the environment is very noisy, and if we could sense, the machine could sense the environment, then we could modify our speech just like a human would do in those circumstances, right? So it turns out in order to achieve this, prosody turns out to be really helpful. You're not changing your speech content, but you can modulate your voice, and that's what we do. If I'm in a noisy place talking to a friend, I'm going to modulate my voice in a certain ways to be more intelligible. And we can do this by actually learning prosody models and making those modifications so that when we eventually play the speech out, it sounds like the system has understood that their listener is in a noisy environment. Okay, so I'll just go, in the interest of time, I won't play all this, but we showed that actually, the intelligibility does improve if you do prosody modification in this setup. I'll skip this in the interest of time. Okay, so the other, large project that we're working on is using, speech technology for doing oral reading fluency assessment. And it turns out that the rubrics for assessing fluency, reading fluency, okay, so this is part of this, FLS, foundational learning study, it's a lot talked about now. And how do you do benchmarking, right? For a very large population, it would be nice to have something which is objective, scalable, etc. So it turns out the rubrics, apart from accuracy of pronouncing the words and a good speaking rate, expressiveness, which actually captures what we talked about, the syntax and semantics, is very important. There is an expressiveness scale, which turns out to be very complex, simply because it involves a human understanding that it is expressive, that the speech is actually comprehensible, and so on. And why is it important? Because it turns out expressive readers are able to construct meaning of the text at the time of reading. So it turns out even when we are silently reading, we are actually internally using prosody to make sense, right? Grouping words together, highlighting words in our mind, and so on. So there is a lot of interest in evaluating expressiveness, which involves evaluating prosody. Okay, so there are, we have this system that does it, which depends a lot on training data, and uses human ratings for that training data. So it's a bit of an expensive process to get that sort of data. So we have this large data set, we train it on expressiveness scores or fluency scores given by human raters, and it turns out that if we use the prosody, we can actually do a fairly decent job. It plays an important role in predicting this, final score. So to get prosody data, we need another kind of interface where we have people sit down and listen and label what they felt were the prominent words, where the pauses or the phrase breaks, phrase boundaries occurred, and so on. And all of this is really used to use the system. And this eventually shows that yes, for a certain kind of population, the prosody is what really is indeed important. We get a high performance or a high contribution of the prosodic this thing, which in addition to what we already expect in terms of, let's say, pronunciation of words and so on. And then this is another aspect of the same system where we begin to see which attributes really matter, in terms of the speaker dependence. So we talked about language dependence, culture dependence, but there's also a lot of speaker idiosyncrasies that play into the usage of prosody. So for example, in this same school children evaluation, if we took a large number of speakers, we found there were some children who indicated boundaries of phrases, sentence endings, for example, by using pauses. But there were some that used only pitch. So all of these are, shows you the high amount of variability in prosody and how why it's so important to train on a particular language and population. Similarly, for prominence, strangely, something else came out together, something related to the voice quality. Came out to be very important for how these children were drawing focus or emphasizing words. Okay, so that brings me to some more recent work where we are trying to create this audio-visual corpus for more face-to-face communication. So, there is a paradigm that was already available that was tried for, used for English, for data collection, Japanese, Germans, and so on. So we got this to work for Hindi. So this involves creating a context where you have a person, get into that particular attitude, want to use that particular attitude to talk to their partner face to face. And then you do this kind of video recording. And try and use also the visual cues or understand better the interaction between the visual cues and the acoustic cues. So some of the things that came out in the course of the data collection and perception experiment itself, whether the visual channel actually complements prosodic features. No big surprise there. When we are face-to-face, we do end up not only showing our face, facial expression, but also gesturing and so on. But there were some attitudes, such as neutral attitudes, such as declaration and question, where in fact the visual was more of a hindrance. It was the audio-only mode that was better. And similarly, some attitudes such as doubt and surprise seem to be conveyed well acoustically. Now, this is based on all human perception testing. It will be interesting, and that's what we're intending to do, to apply some machine learning methods and learn more about the interaction of the auditory and visual cues. And then, of course, maybe eventually bring these kind of capabilities onto the next avatar, which can also, use all of these cues to come up with, to be able to interact even better with humans. Okay, so that's all that I have. Yeah, thank you very much for your attention. Sorry if I sped through some things.
Thank you. So I had a question about the change in prosody based on noise. Is there only one type of noise and so one difference that you have to make, or is it based on the surrounding noise?
Okay, so it's actually based on the ambient sensing of the noise. So just since I have about 1 minute left, I'll just play is it possible to play the samples from here? Yeah, so this was actually recorded at a railway station. So you have these public announcements, and you have some really important information here. So you're standing on this platform and suddenly they start telling you, oh, you have to run to this other platform. So it's crucial that you come to know, that your train is arriving at some other platform. So we have these pieces of information, and when the announcements were recorded, they're recorded in quiet and they are concatenated, right? But if for a listener in a noisy place, they need to be conveyed in a certain way so that they're more intelligible. So that is done synthetically. So I don't know if it's playing at all. Is it playing the top one? Yeah. So the noise is actually sense, and there are some typical reactions to noise. So if I'm talking in noise, we have a certain way. Of course, you raise the amplitude of your voice, but there's a limit to that. So what you do is you shape your spectrum so that certain parts of the spectrum which are normally not as audible become more audible and stand out above the noise. And then you also modulate your pitch more. So whereas you would talk in a certain manner, you start highlighting the words that are important even more when you're talking in noise. So all of this can be done artificially if we know that there is a certain noise level, which there are ways to sense noise and convey information. So
Thank
that's
you.
what it is. Yeah, no problem. Fine. So that was just a background for announcement and just showing how after we did modifications, the speech actually becomes much more intelligible. Yeah, fine. Sure. Yeah. Yeah. Thank you so much.
Thanks again, Preeti. Our next invited speaker is Professor Ganesh Ramakrishnan. He's an institute chair professor at the Department of Computer Science here at IIT Bombay. He also wears another hat. He's currently serving as the professor in charge of the Koita Center for Digital Health. He's also our alum. He got his BTech, PhD degrees from IIT Bombay. His areas of interest include human-assisted AI/ML, and lately he's been focusing his energy on doing data-efficient machine learning, which is what he'll be talking about today as well. And I want to mention that he's very passionate about boosting the AI research ecosystem for India, and towards that he has many large-scale projects, including UDAN, which is an end-to-end machine translation ecosystem, and lots of projects related to OCR and video analytics as well, for which he's received numerous awards. So with that, I'll invite Professor Ganesh. Over to you, Ganesh.
Thank you, Preeti, for the generous introduction. So this is work we've been doing over several years, building out an open source platform called Decile, Data Efficient Learning, and put it to task in several applications. And I'll talk about some of the natural language applications that have been driving this work, notably some of them which Preeti mentioned. Okay. So, as it loads up, some of the big challenges we face today, and that was brought out in my question to Monojit as well, is the democratization of AI, use of AI in resource constrained settings. So, of course, staggering inference and training costs, but beyond that, it's expensive to label large data sets, and we deal day in and day out with several interesting applications coming from the healthcare sector, where you can't afford to annotate data at the scale that typical systems, operational systems demand. Of course, there's also fragility bias in the data, which Monojit pointed out. So where are the points at which you can actually be efficient, data efficient and compute efficient? It could be at the stage of data preparation, model training, validation, or finally deployment. And I'll give a glimpse of some of the interventions we made at each stage. So largely, the Decile platform is structured and organized into 5 modules, submodel. The core of this entire work is submodular optimization. I'll give you some flavor of it. And then on the right-hand side, you see the kind of cold start settings where you don't have so much data annotated. And it could be 0 shot, it could be few shot, whereas on the left-hand side, you see basically the more privileged situation where you have a warm start. So the core library here is submodel, which is characterized by use of submodular functions which have diminishing returns, but it's not just the run-of-the-mill submodular functions, but we also design lots of interesting submodular functions inspired by information theory, right? So extending information gain, mutual information, and so on. It's very easy to use, and just to give you a bird's eye view of the different kinds of functions, while you may want to identify a subset of examples or images in this case from a large collection that represent the entire collection, you may also want, on the other hand, a collection that is diverse enough, which could even capture outliers, like in this case. Or you may want to not represent necessarily images, but represent features or cover features, like mail, car, etc. And the more nuanced versions are where you're looking at query-focused summarization. I give a query person, and I want a subset which is diverse, which could be representative, but capturing people. Or it could be privacy preserving, where I want to hide information about people. Images are easy to ingest, so we'll actually begin with image related problem, which is OCR, optical character recognition. If you look at PubLeNet, a very large collection of objects, but largely, these are text, title, tables, figures, etc. You'll find a massive skew, right? So if you're looking at a problem like optical character recognition, you can celebrate very high recognition accuracy, but the recognition is typically celebrated on the text here, right? And if you look at the distribution of these objects page-wise, again, you find significant skew, right? So coming back to utility, which is what one of the directions that Monojit talked about. Now, when you actually deploy these systems, these figures and text, figures and images can bother the downstream user to no end, right? If you don't get them correct. So yes, if you actually train a model, you'll find that the accuracy for text, etc., picks up very quickly, but the others, they lag behind significantly. So what could you do? So this is one of the measures called mean average precision. So model quickly learns for objects from common classes. Now, is improvement possible for the rest? Well, can we benefit from targeted selection of images that cover rarer classes, which means I give the rarer classes as queries, and can I bootstrap around them to identify pages which are more dominant in figures, more dominant in images and equations, to be able to improve the performance on this tail. So that's what targeted subset selection is about, trust, to mine rare events. So imagine that I have this, this page which is dominated by equations given as a query. Now, is it possible that our library picks up very similar related pages which are again equation dominated? And and how do we do that? It's by actually maximizing the mutual information variance of some of these important submodular functions which are representation, diversity, and coverage based. So this is some work we got recently accepted at IGDAR, which is tactful targeted active learning for document layout analysis. And as you can see, the process is such that it targets the images that can well represent the rare classes, augment the train labeled set, and train the model to improve the model performance very quickly. So this can happen with active learning. This can also happen in a somewhat semi-supervised manner. So we have several variants of this. And there are many other use cases we have put this to use, but I would like to only highlight one of them, which is targeted selection for, say, personalization on handwriting recognition, going beyond just technical documents with images and figures and equations. You also have this use case where you want to customize to handwriting, especially when we work with doctors, right? That personalization really helps. Again, coming back to medical applications, we're often interested in certain areas or regions in the medical records which need to be extracted with high fidelity. Again, targeted based subset selection helps quickly get the best bang for the buck, basically highest throughput in terms of the annotation process. So the next part is semi-supervised data programming. Now, while you can do targeted selection and annotate, some of these, for example, the high fidelity extraction from medical records, you could often encode what you're interested in the form of rules or programs. Okay? So you could have what we call programs or labeling functions. Or these labeling functions could be as simple as characterizing the keywords in a query. For example, if the text contains how, it's a description question. If the text contains how long, it's a numeric question. But the programs can be fairly complex. These actually could be signal processing based. And this could actually be identifying bounding boxes with key values in those medical records. So we have this platform where you can actually ingest these programs, complex programs, learn parameters associated with those from unlabeled data, but also identify the labeled data. The data should be labeled, which cannot be encoded using programs. That's very important. Not everything can be encoded using rules or programs. Identify that which should be labeled. Therefore, there's a dotted line here. It's optional, and your deep learning model can quickly adapt to the label set in conjunction with the programs. Now, there is something close enough called Snorkel from Stanford. However, we have a big paradigm difference here. The difference in paradigm here is, for us, these programs are sacrosanct because we treat the domain experts not as just annotators, where you use and throw what they do, but they should have the power to override what the model does. That's very important for us. So therefore, the parameter learning for these labeling functions, the programs, is done in conjunction with the models, and therefore what we have is what we call joint learning, which is one of our mainstays here. So just to again highlight the difference, you have these programs or labeling functions. In a classical cascaded approach, you'll have a generative model which throws out labels, and then you learn a discriminative model. Whereas what we've been doing all through is a joint approach where the parameters of the labeling functions are being learned in conjunction with the end-to-end deep model. And this actually has, in multiple ways, helped us roll out this UDAN project, which Professor Preeti talked about, and this is also part of 2 of the Bhashini initiatives. But while in the Bhashini National Language Mission is a little futuristic, because we are trying to kind of capture all the elements of this Wakwa triangle. This is a very famous Wakwa triangle here that you see here, where you would like to create a common interlingua across all Indian languages, so that when you translate from English to Hindi, you can also avail the process for translation into other Indian languages. So that's the conceptual representation. But what we have done is also gone down the utility path that Manojit talked about. There are so many low-hanging fruits when it comes to data resource creation in Indian languages, where at the shallower levels, you can actually make very interesting interventions. This Udan project got launched in 2 years back, but since then it's got a lot of utility. And what are the ingredients that have made it work? Which is first is high fidelity document, OCR and layout. I've already given some flavor of the kind of OCR work we do, but going beyond that, going beyond targeted selection, what again has helped make us high fidelity is the use of labeling functions. As I said, for equations, for many of these very challenging tasks, you can actually write programs, right? So, and these programs can be aggregated in conjunction with a deep model, which are often, pixel-based. This has, of course, also been used in a medical. This video isn't playing. So, as you can, in this video, you can see that a medical practitioner can actually write a very simple program which is based on key value pairs and drawing some bounding boxes with 2 to 3 examples. You've got a model that's actually working, which can extract important data from medical records of the order of thousands or 10,000s. Right? So this is just based on a couple of examples. This work with Narayana Hridayalaya. Move to the next slide. Can I move the slide? Yeah.
When run,
Oh, sorry. This isn't moving. Just page
good
down.
morning. Today I'll be giving a by Narayana Hridayalaya.
Okay.
The goal of this project is to develop a tool that can efficiently perform.
Yeah, thanks. The second ingredient is zero-shot lexically constrained translation. This work I've been doing with Professor Preeti Jyoti. So imagine you have a sentence, this rule has to be implemented. Rule in banking or legal domain could mean niyam, right? And it's just shasan, right? And what we can do is actually learn to disambiguate in a zero-shot setting. So you don't need to really produce these corpora and even have access to the dictionaries during training. Right? You can ingest them at runtime. And a third ingredient is the semi-automatic post-editing based on human edits. So each edit that the user does during the process of document translation is a program for us. And there could be multiple conflicting programs. Again, we leverage the semi-supervised data programming paradigm to actually produce post-editing output. So thankfully, this has actually, we empirically showed that this leads to 6 to 10 times speed up over a conventional process. This entire ecosystem that we offer. And as you can see here, this is hosted at AICTE, where you can upload bunch of dictionaries, new dictionaries, which were never seen before, thanks to zero-shot learning, and produce OCR or OCR plus translated output, which can be post-edited. And this is how the interface look like. And again, from a utility perspective, this makes a big difference when you have alignment preserved between the source and target, thanks to our OCR technology, where you have bounding boxes. And not only that, the dictionaries are also preserved with the original English word in bracket, which makes a big difference again. And you can see the large utility of this, the number of books being translated shown on a daily basis, basically. Yeah? Now this, you may say, well, technical domains, dictionaries, do they matter? Look at our Bank of Baroda, again, one of the users of the system. You can see that acts, administrative, some of these are very long, complex rules, and they, for them it's very sacrosanct. They need to maintain these words as they are in the translation process. And thankfully, we're able to, if you look at the output from the Udan vis-a-vis the Google Translate output, and clearly see that not only we are able to retain, but we are also able to attribute the translated phrases to the original source, which is very important from a cognitive load perspective. But it's not just the Bank of Baroda dictionaries, and we have hundreds of dictionaries, and we are actually working on being able to produce these similar translation outputs in languages where the dictionaries are not present. Right? And as I said, this is being used extensively. And this also work has been technology licensed to bharat-bhasha.tech very recently. And there's some acknowledgement from AICT, but what is interesting is, again, our data efficient learning platform actually has been attributed in their press release. Very quickly, there are the other two modules which I may not have time to talk about. One is deep diversified interactive learning. The idea here is, instead of having active learning with one instance at a time, you query with a set of examples, because that again can reduce the cognitive load. I'll skip this. And finally, we have this a more privileged setting where we have lots of data, but we want to be efficient through course sets and data subset selection. CORDS is again made available, very easy to use. It has been put to very effective use in robust supervised learning, semi-supervised learning, hyperparameter search, network architecture search. Obviously, for us to be able to profile some of these network architecture search algorithms, we need baselines, and that's where my question to Monojit was, how do you make the baselines even possible, right? But one such use case is a partition gradient matching based data subset selection. This is work with Ashish Mittal and Preeti and my PhD student Durga. And we actually found a lot of use of this process of partitioning the data and identifying only subsets, so that we are able to, in much less time, as you can see in this plot, trade off very well between relative test error and speed up. So that's very important. So we, with a small subset, we are able to ensure that the compromise on the relative test error is minimal. Okay, and this has been also put to use in many other fields, which I've just listed some of them, but what excites me most is our work with video analytics, where we actually have received recently a gold award in the national e-governance. And we are also building out a similar platform called MedDecile specifically for the medical domain, because there are many other nuances here. For example, we want to be able to not just do subset selection, but synthesize as well. So how can we do targeted and refrain-based GANs, right? So that's something we are trying to incorporate in this MedDecile platform. Thank you very much.
Hi Ganesh. So this is like really impressive and a lot of work going on here. I wanted to get some idea from you on what's the usage like from the time when you embarked on this journey, like who are the people who are using, and private, public, and individuals, some idea about it.
Thanks for this question. Currently, so we obviously had to ensure charity begins at home. So we wanted to put them to good use, and we have been able to so far. Based on that, there have been, for example, IBM Research has this AutoML, and they wanted to use our hyperparameter optimization approach that we have, and in fact, we had a NeurIPS paper last year in collaboration with them. So that's one use case. There have been users from other companies like Abacus. So we keep getting queries. We've not been able to track how many of them have been put to use, but we have a large user base. But these are some of them which are very concrete and glowing. And we are very happy to collaborate or provide tutorials. We have periodic workshops where we let the student and industry community know about it. With some collaborators, we are also trying to bring in this data programming paradigm for RLHF in the large language model scenario. So that's happening in parallel. The medical community has found it very helpful. So I think the collaboration with several hospitals, they have actually seen a lot of value.
And in terms of annotations, is there a user base, annotator base that you have, or is it like whoever, for their case, they find their own annotators?
Okay, so the annotation process is completely decoupled from the platform itself. So they can actually find their own annotators here. In fact, even the translation work, we don't do any of the translation. We just provide the platform. But we also give them access to the logs once the translation is over. Unfortunately, what happens is with a lot of the translation effort, the people using the system have no access to their own logs, right? The parallel corpus is actually being created. And here we have access to that because we do the tracking.
So I'm the next speaker. I'm a faculty member in the CSE department. I'll try to be more terse than I was planning to. Could you just unlock this? Okay. So today I'm going to talk about, I've labeled it New Frontiers for Speech and Language Processing, but I'll talk about a very specific problem which is related to multilinguality. Before that, let me just quickly thank all my collaborators. So these are my students, ex-students in the first row, and industry collaborators, both from Google and Microsoft. So just to cut to the chase, the landscape, the language landscape in India, of course, as we all know, is very rich, and that leads to many interesting technical challenges, including how do we deal with varying accents when you're recognizing speech, the wide variety of dialects, sociolects that vary in grammar and vocabulary beyond accent, which also need to be handled. Sometimes you only have speech, which Monojit mentioned, that you don't even have textual data for certain languages. So there can we enable some kind of cross-modal transfer, where you have speech but not text, and then maybe only text but not speech. Also, when we have lots of rich language diversity, there are lots of non-native language effects when you're learning new languages as well. So that also leads to interesting research problems. And the last challenge which I want to highlight is code switching, which is very prevalent these days when especially the newer generations are engaging with technology. And like Monojit mentioned, now the user base has become very, very diverse, and this new user base largely deals with regional languages, which happen to be code switched. So this is an important problem. This is the one that I'll try and focus on today and talk a little about the work that me and my students and collaborators have been working on. So very quickly, what is code switching? It's just the act of switching between different languages across sentences, within conversations. And this is widely prevalent in India and other multilingual societies. So you might wonder, why don't I just treat it like a new language, get lots and lots of code switched text? But the inherent problem here is that it's hard to get access to code switch data because code switch data is conversational in style. And so maybe we can mine social media, but that comes with its own challenges because it's very, very noisy. And the paradox here is that code switching is very diverse. So the same monolingual sentence can be rendered in very, very different code switched forms, which have the same semantic meaning. So here, you need more data, but inherently there's less data. So there's this clash. So how do we try and fix them? So there are two high-level ideas that we explored, which is we don't have a lot of code switch data, but we do have a lot of monolingual data in each of the component languages. And maybe have a small amount of code switch data. Could we leverage that to learn more about the switching patterns? And so one kind of string of pieces of work that we looked at was, could we build language models which focus on these monolingual models specific to each language, and then use a small amount of code switch data to switch meaningfully between them? And so we call these dual language models. So the first is kind of encoded using this framework called finite state machines. And why we did this was because it was very easy to integrate within speech recognition systems, which are also finite state based at the time. This is in 2018. And so the idea here is just that you have these blocks which are specific to the monolingual components, and then you have a small amount of code switch data using which we could learn these switching probabilities. How do you switch from this W here to this W prime? But the issue here was that we were losing out on a lot of this contextual information. So we are dropping all the contextual information during a switch. We are only looking at switching given W, and then given that you have switched, what is the probability to transition to a new W prime? But we were losing out on all of the contextual information. So of course, the natural extension was, can we move from finite state machines to recurrent neural network models? So here, the idea again we explored is, can we build what we call these dual LSTM cells? So you have LSTM cells specific to each monolingual language, and as you're traversing through a code switch sentence, the state specific to, the cell specific to the language will be active, and at switching points, the active nature will be transferred to the language which is now going to get active at that particular switching point. And at each time step, the prediction would be over the combined vocabulary, over the two languages. And this turned out to work pretty well as well. And this could be trained using both monolingual text, because then you would only trigger the LSTM cells for the specific monolingual block, And you can also use code switch text to further fine-tune these dual LSTM cells. But again, the problem here is that we don't have enough code switch text to effectively train such models. So then we looked at, okay, can we build generative models of code switch text? So this problem in itself is an important problem. How do we build generative models which will generate natural and realistic code switch sentences? And can we leverage more monolingual resources? So for instance, we may not have a lot of code switch text, but maybe we have parallel text, which is used to train machine translation systems. Maybe we have lexicons, which is just giving you context-free mapping. So these are like dictionaries. And then we have monolingual text in each component language of interest. So here we said, okay, let's treat it as a translation task, which at the time was concurrent with other groups also who kind of treated it as a translation task. Let me start with a monolingual sentence and then build a translation system which is going to give me a code switch variant which is semantically equivalent to the monolingual input. And for this, we used an unsupervised MT architecture. So here, why this was useful is that we don't really need code switch text at all. If you have a small amount of code switch text, this could be further fine-tuned to refine this model further. But even in the absence of any code switch text, you can use only monolingual text and parallel text to train these blocks. So in the interest of time, I'll skip how exactly this was trained. We also employed some simple techniques to generate synthetic code switch text, meaning just flip words within a sentence using a bilingual lexicon. Maybe be a little more intelligent, use parsers to get parsers, and then swap out entire clauses with their corresponding phrasal translation so that it's a little more meaningful rather than randomly just switch out words. And all of these were able to further improve the quality of this generative model. And so here, these are just some human evaluation metrics where we are showing that our system, which is TCS, and SNU differentiates between when you have some small amounts of code switch text versus you don't have any code switch text. But even in the U setting, you can see that we don't do too shabbily compared to the S and the real systems. So here are some example sentences which get generated, and I just want to highlight, it's not just the case where we just flip out one word for its translation, but we're actually able to see even multiple switches which are fairly meaningful and realistic with using this system. Another kind of facet of code switching, which I already mentioned, is that there's a lot of diversity in the way code switching is rendered. So diversity comes from lots of social linguistic factors. For example, it depends on who's generating the code switched utterance. Are these first generation immigrants versus younger immigrants? That will change the way in which the code switch sentence is rendered. And also, in which context are these code switch sentences appearing? How formal is the setting? Is it social media, or is it a banner, an advertising banner, which needs to be slightly more formal than when you are conversing with your friends? So here, what we want to focus on is, we don't just want to generate code switch sentences, but we also want to ensure there's some diversity across some certain attributes of interest. So we focused on 3 dimensions of diversity. So one is, these are just, can be deterministically computed just by looking at the code switch sentence. So one is CMI, which is just the ratio of how often do these 2 languages appear in this code switch sentence. The next is switch point index, which is just the frequency of how often are you switching between L1 and L2. And the other is formality, which is a little more subjective. So formality, there's no real measure. We just want to see how formal was your style or tone or choice of words when you generated this particular code switch sentence. So we looked at a real code switched corpus of code switch sentences in Hindi English and looked at these 3 dimensions to see whether there actually is diversity across these 3 attributes, and we do see that there is diversity. So by these 3 histograms. And so based on this, we built a system that we call COCO, which is controllable code switch generation, given certain attributes of interest. So the underlying model, before I move to that, why is diversity important? It's important because of 2 factors broadly. One is that you're interested in understanding diversity. So if you're able to build models which generate diverse inputs, you can use these as data augmentation steps to train models which are more robust to such diverse renderings. And the other is just from the generative aspect itself. So now, of course, we are in the world of ChatGPT and other chatbots. So, and there have been many user studies which show that when users engage with chatbots and say that they employ code switching, and if the chatbot responds back with code switching, this increases engagement with the chatbot. So just generating more diverse code switch utterances is also a useful problem. So this is the model. It's a standard encoder-decoder pipeline. So this is a pre-trained model, which is MT5. And so now we want this controllable aspect to be injected into this model. So we use two types of control, which we call encoder-side control and decoder-side control. So for the encoder-side control, we assume that for these attributes of interest, we actually have parallel data. So we have monolingual to code switch text with the attribute values of interest. And here the idea was that we would have a vector embedding for each attribute, which we would scale with a weight that is proportional to the attribute value that we want to provide at test time. And then we would just add it to the encoder representation before conditioning the decoder with these encoder representations. So this turned out to work pretty well. But for attributes like formality, it's very difficult to get such parallel text. And so we can't use such encoder-side controls. So for that, we used decoder-side control. And here the idea was you would have a classifier for formality, which would look at the prefix string that was generated so far and then make a prediction that on completion, will this particular attribute, which is formality in this case, be satisfied or not? So it will give a probability. And using that, we would rescale the probability distribution, which is coming out of the decoder, so that it would tend to be more formal or less formal. And just to kind of quickly highlight the results, so we got significantly better BLUE scores compared to the earlier TCS system that I mentioned. And if we were to check the correlation between attribute values of human references and our model outputs, the correlation was fairly high for the attributes of interest. But one point here which is interesting is that for decoder-based control, there is a trade-off that you are able to generate more formal or less formal instances, but it comes at a cost of naturalness. So there is a small trade-off, and this is something we are working on currently. So these are some examples of generation. So low and high denote the degrees of the attribute variation. You can see that as you change these degrees, there's less or more switching in the generated instances. So I've also worked on synthesizing code switch speech. So far we only talked about text. So code switch speech is, again, very difficult to get as a resource, labeled speech. So again, the idea was, can we leverage monolingual speech to construct synthetic code switch speech? So one work was, could we use a small amount of code switch text to look at what phonetic boundaries are permissible in a particular language pairs, and only use those phonetic phone transitions to guide the synthetic construction from monolingual segments, which we are going to splice together. So this worked reasonably well. And of course, you might ask, why not just use text-to-speech synthesis systems to generate synthetic code switch speech? And this also we were able to use. But one thing which relates to Professor Preeti Rao's talk is that what we have found repeatedly, and especially at scale, is if you use even very sophisticated TTS systems as augmentation to train ASR models, it never matches up to real speech, and it largely comes down to not being able to capture prosodic variations, which real speech does. Okay, so that still seems to be an open problem. So with that, let me quickly summarize. So this problem of code switching is still pretty hard. I'm going to preempt a question of whether ChatGPT can now do this generation well. The quick answer is yes for certain language pairs like Hindi English, but not for many other language pairs, and we've tried. And so these models are also amenable to transfer to other language pairs, which maybe share characteristics of transfer with languages like English Hindi. So the short answer is, yeah, ChatGPT doesn't solve this problem yet. And transliteration is another thing which makes this problem even more interesting in the Indian setting. And there's very minimal coverage of code switch language pairs across language families. And most of the data sets that are available, it's English X, only because of the ease of availability of the data. But there's so much code switching where English is not one of the language pairs, especially in India. And none of that has been covered currently in the research landscape. And also another very interesting question is, how do current multilingual pre-trained models deal with code switch text? And interestingly, we find that there is high surprisal when it sees switching within instances, even now. So this is something which I think leads to very interesting questions. So I'll leave with this main takeaway, which is that I think just to ensure fair and inclusive adoption of both language and speech technologies, it is important to address challenges like code switching and the other challenges which I mentioned at the start of the talk. So with that, I'll stop, and I'm happy to take a question. Thank you.
Preeti, just one quick question. Is there any fundamental understanding of where exactly we switch?
Yeah.
Like, for example, permission
Yes.
would have in the word anumati, and you
Right.
have using permission. So
Right.
probably there are, it seems to me
Yes.
naturally that
Yeah.
some heavy official words are being switched.
Yeah.
The other is also, when you look, I saw that sentence, Meri life change kar di, right? Now there are two Hindi versions of this. Meri zindagi change kar di and Mera Jeevan change kar diya. Okay, or Mera Jeevan badal diya. Now, why, for whatever reason, are we comfortable thinking of life as feminine? Meri zindagi,
Yes.
Meri life,
Yes.
as opposed to Mera life.
Absolutely.
Is there
Yeah.
any understanding of these sort of
Okay, so
phenomena?
I'll take the first question first. So there are, like you said, the part of speech tags are very useful cues to figure out where switching is permissible. But that said, so there are linguistic theories of code switching, and Monojit will tell you he's done a lot of foundational work on this. But there's no single linguistic theory of code switching which completely explains code switching patterns. So there are multiple theories, but they are only partial explanations of generations, all generations of code switching. So that's the first question. The second question which you mentioned, which is these gender agreement things, very interesting question. I don't think there is, I mean, why is one more natural than the other? We have to kind of evaluate. But this, as you can see, is a very natural, like you would say that. But why would I use that particular gender for a particular form of switching? It's not clear, and I don't know if there have been detailed studies about this specifically. Yeah, not really. Yeah. Yes.
Mine is more on the fun side. IIT lingo is such a huge vocabulary of terms, which is loaded with lot of interesting terms and lot of abbreviations. I discovered something as recent as last week during the exam week. There is something called PYQ. I didn't know this before. So in the context of all this switching, lot of abbreviations keep coming, which are non-standard.
Right.
Is it possible to incorporate that in the context of a small subgroup which uses the language which is, I would say, that of a clan?
Right.
IIT Bombay has its own lingo. Second aspect is when we look at this formal, you said that there is some difficulty in getting the context formal versus informal. When you talk about language switching of this sort, usually formal is kind of kept out, right? Informal switching is a rare event, I thought.
No, so I also used to think that, but especially say in advertising. So say you want to put up banners, or so there you want to make it slightly informal, and that they do by introducing code switching, but not all the way. So there is a degree. So you still want to keep it somewhat formal, but you want to be more personable, so you add a little bit of switching, or maybe just some phrase which is very catchy and so on. So there is formality associated with code switching, the degrees of formality. Your other question, I think that can be incorporated, especially if there is a list, which I know IITB, they maintain a list of lingo. So if PYQ appears in that list, I don't see any, that could be incorporated.
Usually it is part of the orientation program for freshies.
Just a quick comment that formality, I mean, somebody told me that our PM Modi, he gave a speech in UN which was code mixed. And and of course newspaper articles are code mixed these days. So, and they are supposed to be formal. So yes, and my question is similar to the first question, the lingo thing. What we observed when we tried doing some acceptability judgments is what is acceptable, and formality will be even more complex. Depends a lot on the age, the education level, the geography. So what's acceptable in Delhi is very different from what's acceptable in Lucknow. Lucknow, people are really don't accept code mixing that much
Right,
as
right,
Delhi people
right,
do.
right.
And in Bangalore, English Hindi code mixing is very different from
Right.
English Hindi in Delhi.
Absolutely.
And Pakistan is a very different, kind of thing. They say things like sleep karna,
Okay.
which in India we find very unnatural. We say dance karna, but eat karna, sleep karna is very unnatural. But in Pakistan, we have
Right,
seen these are very
right,
common.
Yeah, that
So-
goes back to Ankur's question as well about
yeah.
acceptability is a very
So my
vague-
question is, how do you, incorporate that here?
Yeah, yeah. It's a big challenge, which is why we have been kind of spending time on, is there any way in which we can kind of strengthen generative models, transductive models, and that's why we are looking at various factors of diversity. So then that would be another diversity factor, right? Like linguistic factors. So here we have not discussed that at all. But demographics could be another factor which we weigh in. So this is an open challenge. And collecting data to ensure coverage is another very, very difficult task. So yeah, it's an open problem. Not all NLP problems are solved. Yeah. Oh, yeah.
For example, when we are code switching, particularly in social media, so you find that the local languages are written in English.
Yes.
Okay.
Yes,
so
that's the transliteration.
yeah. So I mean, you are working on that side of.
We
the
are,
story.
yeah.
Okay.
And that brings up very interesting, there's very interesting interplays with pre-trained models and transliterated inputs, because the pre-trained models treat them like English, and that can create conflicts within the model. So we are actually currently working on it. Okay, yeah, thanks everyone. Let me just Okay, gives me great pleasure to invite our last invited speaker to the stage, Dr. Indrajit Bhattacharya. He's a principal scientist at TCS Research, and he leads the Knowledge Representation and Reasoning Research Group. His broad area of research interests is reasoning under uncertainty using probabilistic and now deep models. Indrajit obtained his BTech in IIT Kharagpur and his MS and PhD from the University of Maryland, College Park. And he was, before his stint at TCS, he worked as a senior research scientist at IBM, and before that he was a faculty member at IISc. And he's also a very active member in the larger ML community in India. He's the vice president of the India chapter of ACM SIG-KDD. So with that, I invite Dr. Indrajit to the stage.
So thanks to Preeti and the organizers for the opportunity to be here. I'll be talking about not one particular problem, but rather a task that we have been looking at TCS Research. So TCS Research is an extremely large organization organized into many different research areas. I'm part of that. Well, it looks like a tiny cell here among all the others. It's actually a very large group. It's probably the largest research area in terms of number of people. And again, so data and decision sciences looks at various tools and techniques related to data-driven, research, and also specific domains. So Harshad is also here, and Aditya is also here, I suppose. So there are many people here who are also part of faculty members elsewhere. I see Mayank here as well. So I'm part of the data and decision sciences, and now my team looks at problems around text, tables, relational schemas, and try to use data and learning assisted solutions, not for automation. And this relates to one of the points that Ganesh was making, I think. So we don't try to automate tasks. Rather, we are looking at tasks that require significant domain expertise. And how do you build assistance for people executing such tasks at scale? So there are a couple of examples here. So one is in the context of data migration. So when somebody, a domain expert from a particular domain, let's say insurance or banking or retail or something like that, you receive a huge relational schema from some place with very little documentation. You first need to understand what that schema is about, and then maybe you want to transfer or migrate the data in that relational schema to some other relational schema that you have in the enterprise. And even with people with immense domain expertise, this is something that takes several months to do, right? So there are similar questions in complex information retrieval. We haven't worked with doctors, but that's an excellent domain. I'll be talking about one of those related tasks, which also requires very significant expertise, which is doing assessment at scale. Thank you. And so what is this problem? I think people in academia, particularly the professors, understand this very well. Should it be closer or should it be further away? It was closer before. Is this better now? Okay, thanks. However, at TCS, this interviewing sort of happens at a completely different scale altogether, right? Being a technical services organization, just from campuses, TCS, just conducts probably 1 to 1.5 lakh technical interviews per year, right? And putting together panels, particularly these are people who have a day job, and then they are supposed to sit in panels for a couple of days interviewing people from different technical backgrounds. This is a huge logistical challenge, first of all, in terms of matching people with specific skills to panelists who have those skills. And pretty often there's not a great match, right? And of course, in addition to costing immense money, effort, time, the interviews are not always what they should be, right? And either ways, it's a loss. You're either not taking in somebody who is good, or you're, the other way around, which doesn't help either, right? So, and finally, there's the notion of transparency, right? So nobody really knows, aside from the person who is being interviewed and the interviewer, what really transpired during this interview, right? And so somebody takes a decision, but based on what exactly, right? And there may be governance issues related to this, okay? So there are a lot of solutions right now in the market that look at the recruitment assessment domain. In fact, I think there's a IIT Bombay incubation called Babblebot, I think, which is trying to do something similar. But there aren't too many things in the technical assessment space, and not much. I mean, there are things for exams, but exams are very different from interviews, right? So we wanted to build a solution for technical interviewing, okay? And also, all of these try to do automation, and which in our mind is not a great thing to do, okay? So I don't know about most people. I think, perceptions change, but I, for one, would not want to be interviewed by a bot. So what we wanted to build was an assistant for technical interviewing. And this agent is going to sit and listen to the conversation, and while the interview is going on, for example, and prompt the interviewer with suggestions for various kinds of tasks while the interview is going on. So for example, it'll help in assessment of a specific answer that this candidate might give, and suggest that, look, this might be a good follow-up question to ask. I don't think I have, as you have assessed this particular skill confidently based on the number of questions that you have asked and how you have scored them. At what point should I terminate the interview and be confident that I've made a good assessment, and so on. Now, this is an assistant, so the interviewer is completely free to ignore the recommendations, accept them, reject them, and move on, right? And when the interviewer gives a feedback, the system learns from that, right? And when you think from the perspective of the person who is being interviewed, nothing really changes, right? So it's the person who was conducting the interview still remains the human face of the interview. Now, that person is now just better assisted right now. And there are significant benefits to this. For one, the human touch is still there during the interview as opposed to an automated solution. Now, from the point of view of the interviewer, I'm sure many people here understand this. If you are sitting in interviewing panels for 8 hours a day, it can be extremely taxing, right? Maybe the people who are being interviewed don't realize this, but having been on the other side, and what happens is that as the day sort of goes on, right, you're probably not conducting the interviews as well as you would have during the earlier part of the day, right? So that cognitive effort significantly goes down when you have such an agent to help you. In many cases, the interviews are more standardized. You know that every candidate who is sort of onboarded has been sufficiently assessed on all the relevant skills, right? And hopefully it also leads to better hiring quality in the end. So we have been working on this for 2 to 3 years now, and we have actually built a system which is piloted in real TCS interviews, and there is an effort to integrate this as part of the regular TCS interviewing system right now. So that's the background. Now, what does this mean in terms of a technical problem? So caveat, we started working on this way before the ChatGPT revolution. So the architecture that you see here would change very significantly based on the recent developments. So we decided to have an offline and an online phase. So what happens in the offline phase is that you throw in textbooks, right? And this agent builds a technical question bank from that textbook. This happens offline, right? And when you conduct an interview based on some kind of a job description and a resume of the candidate, at different points during the interview, the agent recommends questions from the question bank and also helps in assessment, okay? So it does not come up with questions on the fly, right, while the interview is going on. But based on recent developments around LangChain, et cetera, this is now possibly doable. Anyway, so I may not be able to get into, okay, so we tried to look at the state of the art, right, and see whether we can just use the state of the art for many of these tasks. And unfortunately or fortunately, that wasn't the case, right? So we started off, well, here was one problem which had quite a body of relevant literature out there. So this was not that novel from our point of view, but still we had to incorporate several kinds of preferences that interviewers may have when they want to generate questions for a particular candidate. But maybe in the interest of time, I will skip this and move on to some of the problems that were more interesting for me. So the next task was technical question generation, right? So I give you a textbook, right? And you want to be able to generate all the different kinds of questions that you might want to ask somebody whom you have expected to gone over and study that textbook, right? So we want questions with long form answers, this being an interview. This is not MCQ or factoid questions or yes/no questions. And this is not a reading comprehension task, right? So the questions have to stand on their own and make complete sense. So what do I mean by that? So for example, if I said, what are the hyperparameters for a particular optimization problem, if it's a reading comprehension task, this might make sense because, the task is mentioned in the context. But for an interview question, this question does not stand on its own. It needs to have additional context. So these kind of questions are not okay. Secondly, the answers have to be present in the context. So certain questions may be entirely meaningful. For example, how does this particular optimization approach compare to some other optimization approach? You could hypothesize that question based on the context, but the context itself does not contain the answer, right? Now, this, given the way you conduct the interview, if it's not a research interview, maybe you do not expect the candidate to know the answer to such questions which are not there in the textbook, or maybe in an exam as well, right? So those kind of questions you also do not want to generate, right? So when we looked at the state of the art, right, so most of the work around question generation seemed to have happened for reading comprehension, first of all, and also largely for narrative or storytelling kind of text, right? Not for technical context. And also, zero shot, well, this was GPT-3 at that time. Zero shot GPT-3 did not work very well. It suffered from all of those issues at that point. It would generate questions which are not answerable from the context. It would generate questions which do not have complete context to be meaningful, and so on. And the most difficult problem for us is there were no data sets for technical question generation or technical question answering, right? And now this is a pretty serious problem. Now, if you are in academia, maybe you would want to move away from this problem and study problems for which there are existing data sets, but this is a problem that we wanted to solve, right? So the first thing that we had to do was actually putting together a data set, right? And as you can imagine, and this is also a problem that Ganesh was referring to, these are not tasks that you can crowdsource, okay? Because generating technical questions from a textbook requires expertise, right? So we had to do this in-house, and obviously we are doing this in-house. You cannot really do this at scale. So we took a couple of textbooks. Again, we wanted to make this data public, so we worked with textbooks that are freely available in the open domain. So we looked at the Goodfellow DL book and Bishop's PRML book, right? And we sort of, with people inside the organization, we sat and generated questions from these textbooks, right? So obviously we were not able to do all, so we covered all the 20 chapters from Goodfellow, and maybe I think 3 of the chapters from Bishop. So we have about 750 questions that we were able to curate. Now, obviously, this is okay for evaluation, right? But okay, maybe I'll give you an example first, right? So this is an instance of a question from the deep learning book. So just to demonstrate that these are very different from the kind of questions that you would see in typical QA kind of data sets, okay? So just as one small piece of statistic, if you look at the Google natural questions data set, right? So first off, okay, so these numbers for natural questions are based on some random samples that we took. But you can see that the kind of questions, right, are largely, some of them may have sentence-long answers, but these are really factoid kind of questions, right? And more importantly, you might think that these questions come from Wikipedia, so Wikipedia probably contains a lot of technical context, so you would see a lot of technical questions in there. Unfortunately, that is not the case. So 93% of the questions are non-technical. They relate to sports and entertainment and stuff like that. And when it comes to technical domains, there is about 6% biology, 1% astronomy, and so on, right? So there's almost nothing from, let's say, a computer science kind of background in Google natural questions. And also in terms of the types of questions, right? So on the right are the types of questions that we were able to curate in the TechQA dataset. Again, I'm not very happy with the distribution, right? Because it's still dominated by a very large proportion of define and what is kind of questions. So I would have, based on studies of real interviews, it's much less than typically 50%, maybe 20 to 25% of the questions may be of that kind. But this is what we were able to generate using the annotators that we had. Now, a little bit more on the types of questions, right? So as you can see, we did not rule out mathematical notation from the questions or the answers. However, there are several levels of difficulty here. So if you notice that while the question and the answer, the question does not, the answer involves mathematical notation, right? Detecting the answer does not involve any kind of mathematical reasoning, right? So just as an example, if I ask you to define something mathematical and you are looking to extract the answer from some textbook, it does not require you to understand that definition, right? So I just want you to recognize that this is the part of the context that contains the definition, right? So the questions that we have here do not involve mathematical reasoning. However, it involves dealing with mathematical symbols and so on. Okay. And these are extractive answers, so I'll come to that in a bit, why we wanted extractive answers. Okay. All right, so now we were able to put together a data set that has 750 questions. So obviously you cannot train any kind of model on that. So what we tried, again, I will not go too much into the details of this, right? But we tried weak supervision in various ways, right? Again, we tried the interviewing prompt from GPT-3, right, to generate questions and then correct them in an automatic way to the extent possible to fix the issues that I referred to earlier. And then we also used, manually designed templates based on our studies of interviews to generate questions algorithmically. This formed our weakly supervised data set. And a huge challenge for any of these generative tasks is evaluation, right? So you can have a gold standard set of questions that some person generated from this context. However, that is far from exhaustive, right? So if some model now generates additional questions which do not have any resemblance with the original gold standard questions, these are not necessarily incorrect, right? So evaluating precision automatically is extremely hard. So we actually did human analysis of precision, right? And we looked at several aspects of the quality of the questions, right? So how complex was the question, what was the nature of the answer, semantic correctness, answerability from the context, and so on. And we were able to see that the kind of weak supervision that we did was able to significantly improve performance compared to GPT-3. Now, again, all of this came up because we were trying to solve a practical problem. And at that point, the volume of questions that these models were able to generate from the context were not enough, right? We wanted more questions. Now, the observation was that if somebody gives you the structured metadata of a textbook, for example, if somebody gave you the index of the textbook, the index has a very interesting structure, right? So the index is hierarchical, and the language, though it's not, it's significantly restricted compared to natural language, but still it has a lot of richness. And if somebody just gave you the index, it is in fact possible for a human to look at the index and generate very interesting questions from the index, right? And the indexes are very large, right? So that's a very useful context for generating questions. And what you're assured of is that the questions that you generate from here will always have the answer in context, right? So these are some examples of questions that you can generate from the index fragment here, right? And what we observed, again, these were experiments with GPT-3, that when you have this kind of a structured context, manually designed templates with slot filling seems to do significantly better than zero-shot GPT-3, at least when dealing with some such structured context. Okay. Okay, so this was the second aspect of question generation. And the next problem was assessing difficulty of the questions that you have generated. And unless you have difficulty levels assigned, it is very difficult, or so I'm overloading the term. It's hard to do assessment unless you know how difficult the questions are, right? So now the way difficulty levels are assigned in the literature right now for various kinds of examinations, etc., is based on responses, right? So the difficulty of a question is just defined in terms of experimentation as the fraction of the students who were able to answer that question correctly, right? But this definition requires that you have a huge number of people who have already answered that question. Now, when you're starting out, you don't have that, right? So how do you introduce new questions, right, of whose difficulty you are not sure of, right? And again, so what we try to do here is the same problem again comes up. There are no data sets for this, for technical questions, right? So again, we had the task of putting together a data set, right? And this is very, very hard, right? So if you ask a person, you give a person a question, an expert, and say, how difficult is this question from a range of 1 to 10, forget repeatability across people, right? I have tried this exercise. I'm not consistent across different iterations, right? So how do you even go about creating such a data set, right? So you cannot assign absolute labels. However, what people are significantly more consistent with is if you give a person a pair of questions and ask which one is more difficult, right? That labeling is significantly more consistent, right? So this is the way that we took to prepare this data set, right? Now again, when you're preparing the data set, you have to be careful, because if you just pick random pairs of questions, either they are going to be, they are going to be trivial in one way or the other, right? That one is significantly harder than the other. And now those are not useful for training a model, right? So you have to create these pairs such that these are close to the decision boundary. And when you're choosing the pairs for labeling, you do not know how hard they are, right? So even creating this data set is pretty difficult, right? So anyway, I mean, we had to spend a huge amount of effort in-house to prepare this data set again, right? And then our idea was that, okay, we are not going to use responses to estimate difficulty. Now, how do experts estimate difficulty, right? So when I'm, including some question in an exam, I do have some estimate of difficulty, even when I'm introducing it for the first time. I'm often wrong, right? But regardless, I do have some initial estimate. So how do I do that? It is based on my understanding of certain things, the way that things are described in the textbook, right? Where it is described, to what extent, to what level of detail, right? How indirectly is this question answered, and so on, right? So what we did is, again, we thought that we would come up with an approach to assign difficulty based on the textbook context, right? Not based on responses. And again, we were trying to do two different things. One is, are you able to align the questions to different levels of Bloom's taxonomy, right? Which has clear hierarchical levels of cognitive difficulty. And then, in what context is the answer explained in the textbook, right? So these are our two sources of evidence, and we came up with an unsupervised algorithm, right, to assign difficulty. Now again, this was a way to create weak supervision for creating data, which we now use to train a deep learning model. And again, this turns out that when you are training a model on this kind of a weakly supervised data set, right, we were able to outperform certain other models. Again, I know I'm running out of time. I will not be able to talk in more detail about any of this, but I'll be happy to talk to you offline if you're interested. And then the final task was, okay, I have the questions, I have some notion of difficulty. I need to have some reference answers to be able to assess, right? Now, here we had to make a choice about whether we want abstractive answers, generated answers, or extracted answers, right? And based on conversations with various interviewers, right, the notion of trust in the reference answer is very important, right? So we found that a person trusts a reference answer when the answer comes from a book or some context that this person trusts, right? And it's based on extraction from that context, right? So why did you give this answer? Because it's mentioned in the book right here, right? So we decided to have extractive answers rather than generated answers, right? And again, when we looked at so there is quite a bit of work on extractive question answering, but again, none in the technical domain, right? We wanted to, and there are two different ways to do extractive QA. One is based on sentence selection, and then there are span-based approaches, and typically, these sentence selection approaches work better. So what we wanted to explore is there a way, given the power of generative models, is there some way you can use generative models to do extractive QA, right? This sounds a little counterintuitive, right? What would you want this model to generate if you want an extractive answer? One possibility is you might want the model to extract or generate the sentence indexes, right? The index of the sentences where this answer is present in the textbook, right? And there are two different ways to do it. Either you enumerate all the sentences which are part of the answer, or you generate these sentence spans, right? And again, this seems to work remarkably well, right, compared to these, models that do sentence selection, right? And this seems to work not across, this particular task, but across several other tasks that, we were able to beat the benchmark for various other QA tasks, not just multi-span extractive question answering, right? Again, I'll be happy to talk to you outside. So this work is not yet published, it's under review. Okay, so there are quite a few things that we still have not been able to do, and this is still largely based on unavailability of data, right? So one very interesting problem is follow-up question generation, right? So you asked a question, you got some particular answer from the candidate. What is the next best question to ask based on the answer that this person gave, right? And again, there are no data sets for this. And putting together a data set ourselves is also pretty hard. So one of the things that we are now exploring is whether it makes sense to use the recent LLMs to be able to simulate candidate answers and then generate follow-up questions based on those. And a very different kind of problem is assessing of projects, right? So this is not based on knowledge that somebody has from some book. Some person has executed some project, and you want to assess that person around how well that person has done that project, right? So here there is no notion of gold standard answers actually, right? So so again, I'll be happy to talk to you offline. I'm running out of time. So this is based on work with a huge number of collaborators because it involved a lot of different problems. And I just wanted to mention that we are always looking to collaborate, and there are various ways of engaging with TCS research. And finally, before I end, I wanted to advertise the CORDS COMAD conference for 2024. We have been able to put together an excellent organizing committee. Some of the OC members are sitting right here. So looking forward to a great conference and hoping to see lots of good applications. So we have a research track, applied data science track, demo track. And again, as usual, we have tutorials. We are planning for a data challenge and the Young Researchers Symposium. And we have a very large student travel grant program as for all other years. So the deadlines for the research applied tracks are July 17th. So heads up, the CFPs for the other tracks are going to be out soon. So thank you, I'll stop there.
Good morning, sir. It was a wonderful talk.
Obviously, you need semantic representations to be able to assess. So there is quite a bit of work. So this broader problem is called, I think, automated short answer grading. So in fact, Professor Somen here has done quite a bit of work a couple of years ago. So again, we have not made a lot of progress on this problem, right, because of the unavailability of large data sets. But the issue that you pointed out would be the biggest challenge there, right? Because for these kind of questions, there are many different ways to give the correct answer. There is no one single objective correct answer. So that is a very significant challenge. Yes, it does. So in fact, for the difficulty assignment, etc., we did that. It certainly helps. So not just pre-training, but also prompting with the context when you try to generate the question. That certainly helps, but it still would, okay. So one very interesting problem was to teach the models what kind of questions not to generate, okay? So I'm pre-training with the textbook, right? But if you consider the original kind of question generation models, they used to be sentence-based, right? And from every sentence, you would like to generate some question. And clearly that doesn't work for textbooks, right? So one of the things that is just pre-training with the context does not teach the model is what kind of questions not to generate, right? So that's another important thing that we had to do after pre-training, right? So figure out ways to say that, this is not a question that would be meaningful. And what we did there was actually prompting with a context and some generated questions. We did not think that, prompting with, negative examples, that seems kind of strange here. That's one of the things that we tried that did not work. But pre-training, yes, we did that. But that was the additional thing that we had to do, teaching what kind of questions not to generate.
So most academic institutions have lots of questions over multiple years. I mean, if those could also be, but it just requires data gathering.
Absolutely.
May I? Yeah, thanks for a nice talk, Indrajit. I probably missed, but did you also, your focus was extractive, but did you include analytical questions? Did you see any scope for math word problem solving kind of data sets that are publicly available?
We haven't gotten there yet. That would be the next thing to do. So these are questions that did not involve reasoning, right? So these would be solved by just extraction, right? So reasoning kind of questions would be the next step. But again, preparing data sets for those is extremely hard, right? So, I mean, we spend more than a few hundred hours just to put together this data set. That was the challenge, but I agree that would be the next thing to try and do.
In case that interests you, we actually built a math word problem data set for Hindi, made it publicly available.
So I had a quick question. So I'm here. The follow-up question problem that you mentioned, it seems like it's tightly integrated with the question difficulty.
Absolutely.
Yes. So how?
Not just the question difficulty, it's conditioned on there are two ways to look at it actually. One is something that we already do is it is conditioned on the assessment score for the previous answer. That's not difficult to do at all. That's something that we already do. But you don't just want it to condition, because, just as an example, there are many different reasons why you might want to give somebody a 3 out of 5, right? But depending on the nature of the error, the follow-up question would be different. So it's not just conditioning on the question difficulty and conditioning on the assessment score, it's conditioned also on the specific answer.
Right. Yes.
So it's all three things.
Okay. So you would be kind of jointly.
Yes.
Okay, I think we'll wrap with that. Let's thank our speaker again.
Thank you.
So please
So welcome again everybody to the session on RL and multi-agent AI. We'll have quite a few faculty talks here from a variety of departments including aerospace, chemical engineering, operations research, computer science and SysCon. But before that, we'll have our first talk from our industry guest speaker, Dr. Jaykumar Subramaniam. Jaykumar is an alumnus of IIT Bombay as well as a PhD from McGill University. Then he spent around 10 years working in investment banking and management consulting before moving to Adobe Research, where he is now a senior scientist. So I'd like to welcome Jaykumar to do his talk.
Hello everyone. Thanks for the introduction, Harshad, and thanks for inviting me here today. So I was asked to speak about RL and multi-agent RL applications in what we actually look at in Adobe today. So this will be less of a technical talk, more of covering the range of problems that we work on. I have links to papers on each of these slides, so in case you have any questions about anything specific, I'm happy to answer. Otherwise, I'll just be going through the slides fairly quickly. So this is a brief introduction about our lab. Actually, so you already saw the previous slide. So we are part of the Adobe Digital Experience Cloud. So we look at more of B2B businesses, so specifically involved around assisting marketing operations of other organizations. So Adobe itself is our customer. So essentially focus areas are creating intelligent experiences using AI, data insights, as well as a large part of where I work on focuses around customer journeys. So RL for customer journeys. So this is basically the charter of our lab is to do, in addition to sort of supporting Adobe in its product development, we have a history of publication, patents, and collaborations with almost all departments in all major universities. We have a strong research internship program where we go to almost all the IITs, premier engineering colleges in India, and we also look at PhD interns from abroad. And people are allowed to publish the work that they do with us in their internships. Obviously, the Adobe restricted material is not publishable, but in general, we do encourage a lot of open source work. And we have our alumni in several places. So in case people are looking out for internships or any other kind of collaborations, feel free to reach out. So again, very quickly, these are some of the areas that we work on. So basically things like image generation for ideas like virtual try-on, for say automatic understanding of documents like forms. So extracting intelligence from forms in order to be able to create new forms. Then all the standard tasks such as tagging, object detection, things of that sort. Then of late, there has been a lot of focus on natural language processing, so things like chatbots, use of large language models for generative AI-based applications and the likes. In data science, like primarily we focus on causal methods in AI, trying to explain, at least specific to marketing attribution, decisioning, recommendations, things of that sort. Customer segmentation involves a lot of lookalike modeling. Then we use topological-based methods to do customer segmentation, and finally the standard explainability methods for, explaining various models that we train on. So basically, we try to make the deep learning models more accessible so that they can be deployed in industry with more assurance. Finally, this is the area that I work on. So handling customer journeys, both simulation and optimization, which involves predicting what the customer would do next, as well as looking at how can we recommend the next best action for optimizing, say, some marketing objectives. So broadly, these are the areas. This is just a list of some recent publications, which you can also find on our website. So I'm just going to skip this slide in the interest of time and go to the main part of what I wanted to focus on is reinforcement learning, both single and multi-agent systems research in MDSR. So in this part of the talk, I'll just briefly cover 6 of our publications, stating like what was the objective, what were the key ideas behind the publication, the work was done by whom, and how are we using it in Adobe. So again, feel free to interrupt me in case you want any more details about these specific topics. So one important problem that we face in marketing is the fact that we have a lot of historical offline data. Often the systems are partially observed, so you need to make recommendations for what to do optimally, especially things like the next best action in a POMDP kind of a setup. So one of the first things we had to handle is find out if there is a principled way of handling all the historical information. We did this through constructing something called as information states and approximate information states. There is a paper in JMLR which talks about how can we get bounds when we make different kinds of approximations. These bounds, both which are theoretical as well as some of these bounds can be estimated online via learning. So this is typically used. So most of my applications are around Adobe Journey Optimizer. So you can find like customer journey simulation and journey creation and optimization as a common theme across all these publications. And these were my collaborators. Again, we had industry collaborators here. This is my PhD supervisor. And this is the link for the paper in case people are interested in delving further into it. So the main thing about this particular work is that this gives us a method not just to sort of suggest the next best action, but also another way to represent customers using these approximate information states. So customer segmentation is a huge problem, not just for designing campaigns, but also for tracking customer loyalty and various other aspects. So this is one more customer vector. An approximate information state is one more customer vector which then gets fed into our system. Often with RL, the question that you face is how do you explain your policies, especially if that has to be adopted by people in the industry. There are standard methods of explanation for deep learning, often which are insufficient for RL, especially when you are using things like RNNs or transformers for predicting the next best action. So in this, my team and I came up with a method to sort of attribute decision making to the data sets used in learning. So basically you have you want to do some kind of a case-based reasoning where you say that at this particular point in time we are recommending this action based on these historical cases. So this is one form of explanation which we found resonates well with most marketing customers because they are able to reason more with historical cases than with technical details of why a particular algorithm is focusing on something. So again, to do this, we used a variant of decision and trajectory transformers. So essentially, transformers are like the technology underlying large language models, or like, for want of a better term, the technology powering ChatGPT. So basically, these allow you to generate representations of, say, historical encodings. These representations can then be considered to represent an entire trajectory. So we found that if you want to do things like find out what data points were most influential in making a particular decision, you can do standard Shapley value kind of tricks of like leaving out a particular set of data points, seeing how the optimal action changes, and then attributing it to that. But because most practical problems are partially observed and in continuous state and action spaces, it is not possible to do this selectively. So we need to discretize our history into clusters. That is where these embeddings help. So again, for more details, we have, this has just been accepted in the current iClear conference to be held a couple of months from now. The paper is again publicly available. And earlier work on explainability. So we looked at explainability from the perspective of how do you attribute decision making to various points in learning, data points. But there are also questions of explainability on what is it that you're looking at with respect to the current context. So especially like, can you answer questions like, are you recommending a particular offer for a customer based on the customer doing something or having triggered some event? So this was again an older paper in iClear 2020, which sort of came up with two particular quantitative measures called specificity and relevance, based on just the action values learned during reinforcement learning, to sort of assign like what features of the state are most important for the RL agent to like take this particular action. So the key idea here is again to perturb the state, find out how the action changes, and find like what particular perturbation works the best in order to explain that action. So this was again in collaboration with UC Irvine, with Professor Sameer Singh. Again, part of an internship where Dhruv was an intern who was working on this. So Dhruv and Shripad both were interns working on this. So this shows that, I mean, we try to focus on getting high quality papers even out of 2 to 3 month internships. So far I was speaking about single agent RL, and sorry for the quick pace, but I had to cover a lot of topics. So this is again a brief intro to how is multi-agent RL even relevant in marketing. I wanted to spend some time on this because these are the topics that I spend most of my time on at present. So often you have, like, even in an organization, multiple teams running different campaigns. So these campaigns often have conflicting objectives. You target the same set of customers, and there are rules like you're not supposed to reach out to a customer multiple number of times from the same organization. So things like deciding which customer has to be targeted as part of which campaign has to be done in a decentralized manner, because most people running these campaigns also don't know who all are, what are the other campaigns going on in parallel. So this problem becomes similar to a sequential social dilemma or a prisoner's dilemma kind of problem, where if everyone tries to just maximize their own incentive by trying to target every customer that comes their way, it might not be socially optimal or optimal for the organization as a whole. So our objective was to try and see if we can solve this in a decentralized manner, although a centralized solution definitely exists. So for a decentralization, we noticed that one of the ways in history where such dilemmas have been handled is by introducing what is called as a status quo bias. So basically, in your exploration phase, if you reach a cooperate phase in prisoner's dilemma, you realize that gives you the maximum reward. So somehow, if you are able to persist in that state, then you realize that is much better than the Nash equilibrium of defect. So we added an additional term to the policy gradient term itself, which is called the status quo component, which adds a reward for you to stick to highly rewarding states. So as such, there was not much change to the standard policy gradient algorithm, but we found that in practice, this often leads to reaching a socially optimal point, even in sequential social dilemma kind of settings. So we tried this both for stage games as well as for sequential games. And our objective is to ultimately use this in customer journeys. So having experimented with two agent problems, our next objective was, so one of our objectives for customer journeys is to be able to simulate customer journeys as well as then optimize them. So in order to simulate, the standard way of simulation is just to treat the entire sequence of responses as a black box and to try and predict what will be the response to a particular action. But we found that that is often inadequate, especially in modern times where customers often adapt to whatever has been their historical interaction, and customers have multiple choices as well. So we chose the framework of agent-based models to sort of represent customers in an organization, to be able to model the entire population and then choose to do RL on top of these agent-based models. So these agent-based models serve as artificial environments or simulators for an RL agent. Again, availability of data was a challenge. We were doing this in collaboration with MIT. So due to which we had to work on some data which was publicly available, easily verifiable, which is why we picked the problem of COVID-19 or epidemiological modeling. Again, there were three primary challenges in using agent-based models in practice. So these three challenges are related to the scale. We have millions of customers for any particular organization. So if we say that we can run an agent-based model with 100 agents, it is of no use to be able to generalize. So we wanted to scale out. We wanted to make it efficient. If you want to run an RL agent on top of this, you need the underlying simulator to be fast. So we wanted this to run quickly, in a matter of minutes, if not sooner. And ultimately, it's a huge challenge to calibrate these models with real world data. So often you have stylized models which predict some phenomena which then you may or may not observe in the real world. But the challenge for us was we already collect a lot of data. Can we now calibrate these models to predict the same data? So for this, we wanted these frameworks to be end-to-end differentiable. So the solution we found that was to rewrite the entire agent-based model in a differentiable deep learning framework like PyTorch. So we have both PyTorch and JAX versions for these. So this automatically solved the problem of scalability because now you can run these models on GPUs or TPUs. And essentially this also makes learning possible because the entire simulator end-to-end is differentiable. So we have a paper in AMAS this year which sort of demonstrates the end-to-end differentiability. The marketing part, of course, is not publishable, so we are just sticking to the epidemiology part in this paper. So this is the last paper that I'm going to talk about. I have about 4 minutes left, so we could take questions if there are any after this. So far, all the papers that I focused on, except the first one, had a very applied flavor. So I also wanted to showcase something where we have done which is completely theoretical. So here we wanted to look at, again, multi-agent problems. So it's a game theoretic setting. And we want to know if we start approximating these things with, say, a model learned from data, what kind of equilibria will we reach as a result of these solutions? And can we sort of provide bounds for both sample complexity bounds as well as performance bounds if we use these approximate models to decide what to do next? So here again we chose the model-based RL paradigm where based on historical data we construct a transition model again of a POMDP, both the reward as well as the transition. We can now use standard inequalities like Hopting or Bernstein to estimate sample complexity for learning these models because essentially this is supervised learning. On top of it, we use the approximate information state concept to sort of provide bounds to the MPs, again based on some restrictive assumptions like basically all agents don't change their policies simultaneously. This is specifically useful in competitive scenarios. So for instance, we are recommending use of agent-based models for simulating events say, challenges for us are things like if you have Black Friday or Cyber Monday or some such events. So there is going to be a huge traffic to a few companies. So if you can estimate what is the kind of traffic, what is the kind of backup they need to be able to, service that kind of traffic, that would be very useful to them. So these are competitive scenarios where you have a few number of large players, which falls within this framework. So everyone has an approximate model, and this sort of gives you some kind of, loose theoretical guarantees as to what kind of methods will work best. So this was again published first in Indian Control Conference, preliminary version, and then now in the Dynamic Games and Applications Journal. So this is again work done with McGill, with my collaborator, first world supervisor Aditya Maji. So this is all I have in terms of slides. So
Can you elaborate a bit on the application of the game theoretic models? Exactly how do you apply? What's the concrete application in marketing?
So the complete application is like for the status quo bias problem that we spoke of is like mostly for competing journeys. So the way journeys are launched is that a particular team decides a campaign, selects some segments, and then like launches a campaign for those segments. Now segment definitions often overlap, and there are like frequency caps on how many emails are you allowed to send to a particular customer. So in terms of abstraction, this is very similar to a coin game. So where you have like random red and blue coins spawning up in a grid, and like there are red and blue agents who get points for even picking the coin of the opposite color, but it's suboptimal for the team as a whole. So this is the abstraction. So essentially we are looking at how to assign customers to campaigns in such a way that each campaign designer does not have to look at all campaigns in parallel. So the extension of this work is to to end player systems is essentially you're trying to handle the Brace paradox. So which to some extent we can with this kind of method, but yes, they are part of the same team. So if a centralized solution were possible, that would be ideal, but often that is not. Thanks.
So, yeah. So next I'd like to invite Professor Kavita to talk about risk-sensitive MDPs. This is the first of a series of talks by faculty, 10 minutes each covering one specific problem. So Professor Kavita, please.
Yeah, thanks, and yeah, okay. So I just thought of making it little bit tutorial-ish, in the sense I'll be telling you some things, and what we have done will be very little part of it actually. That's the idea, because the topic requires some background. So I think developing the background itself will be quite some job in 10 minutes. So yeah, so let's just understand. Oh, do I need this really? Oh, okay. Yeah. Okay. So okay, I'm talking about Markov decision process. So sorry, this could be repetition for many of you, but let's just go through it very quickly. So what is this Markov decision process about? It is about decision making. Basically, it is about sequential decision making. Let's start with it. Say you have some initial state. Some system is there, you are observing an initial state. Then you make some action. You choose some action. Based on the action, you move yourselves to the new state x2 according to some transition probabilities which are controlled by the actions. So they are called controlled transition probabilities. Then you also derive some utility, right? Or some reward is derived, instantaneous utility. And you move on. So based on these things, you choose another action A2, right? Then you have a new state x3, and then there is a reward again. And this goes on. This continues. So you have sequence of states, you have sequence of actions, and then you have sequence of rewards, right? And what is this MDP about? It's basically, it has got these ingredients, the state space, action space, decision epochs, where you're going to make sequential decisions. And then these are the rewards which you're going to receive. And these are the control transitions, which is going to tell you, given the state you are in and the action you have chosen, what is the next state? What is the probability that you see X dash in the next part? And what is it all about? So you are receiving the rewards, instantaneous rewards, every slot, and you are interested in not just the instantaneous rewards, you are interested in accumulated rewards. So you can either accumulate over the entire time period in an additive manner, or you could do it in a different manner, okay? So for example, if you see, this is the accumulated utility to the power, e to the power of that, which we call as risk sensitive, okay? And the whole idea is to come up with a policy. What is this policy? Policy is nothing but it's a decision rule, one for each time slot. And what is a decision rule? It's basically, once you observe a state, what is the action that you are going to choose, right? So this whole ensemble is one policy, right? And you want to choose a policy which is going to optimize either this kind of cost or this kind of cost or something else. You can also have infinite horizon problem. So the whole idea is about coming up with a policy which maximizes the accumulated reward. Okay, so these things are quite well understood. I would prefer to call it as linear cost MDP because this is not having some exponential time. It's not a multiplicative cost MDP. And the optimal values are referred to as value. It depends upon the state you are starting with and the time at which you have started, right? And there are well-known dynamic programming equations. So these are, these are very, very useful. So maybe I just would like to ponder over them. Like the value, which is the optimal when you are starting at state S and at time t, can be seen, actually equals maximum over choosing the action at that time where you receive instantaneous reward like this. So if say you are in state and you have chosen action A at time t, this is a reward, instantaneous reward that you get. And then you move on to the next state and there is a value from the next state, which is again given by this, right? The optimal from the next onwards. And that will be equal to the optimal at the current state. This is the well-known dynamic programming equation. And these equations are instrumental in deriving a lot of algorithms, including learning algorithms and other things. And so what is the optimal decision rule? Basically, it is nothing but for every state and time you have to choose an optimal action, which comes from this maximizer, okay? Our max of this would give you this. And it is also very well known that when you have infinite horizon and some nice things are happening, then you have a stationary policy. You don't need to worry about a very complicated policy where you are having one decision rule at every time, but it's a simple policy like you use the same decision rule for all the time slots and that would be optimal, okay? So such a nice luxury is available with only linear cost MDPs under certain conditions. But the focus of our talk is on risk sensitive MDPs, okay? So what are these risk sensitive MDPs? So it's, many people want to do some kind of robust optimization. Basically, you're not interested in just ensuring that you're safe on average value. You may want to take care of variance, second moment, third moment, and so on. That is one of the roles of this risk sensitive MDP, okay? So here, you are actually taking this accumulated cost as in previously, but you are doing e to the power of that. As a result of it, if you see carefully, because of the exponential, it's nothing but 1 plus the first moment, second moment, and third moment, and so on. So depending upon the value of gamma, which is called the risk factor, right? When you are trying to optimize this risk sensitive cost, you are not just optimizing the average or the expected value of the running cost, but you are also trying to optimize weighted sum of moments of the accumulated cost. And that's why it is also called, it's a way of looking at robustness. Because there are other methods, I'm not going there, but one of the primary things associated with this risk sensitive MDPs is that you are looking at robustness, right? And so yeah, There are other methods, as I told you already. For example, mean variance optimization. It is very well known in the context of supply chains and project management and other things. But the biggest complication with this is that you don't have this beautiful dynamic programming equations. So that's where these things have a lot more easier way to handle the solutions. You have. So now it's not just the robustness, but in fact there are some applications whose cost resembles the risk sensitive cost. Okay, so now let me just get into one example of this risk sensitive cost. I don't know how many of you are well versed with this inventory control model. Let me just explain you, like the main thing is there are demands every day, right? And you have to order an inventory, you have to maintain an inventory in an optimal manner, right? So you have some ordering cost, you have some holding cost. So if you are holding some inventory, you have to pay for it. You have to, if you are ordering new inventory, you have to pay for it. And those are captured here. Like whenever you order, you have some ordering cost. And this is the inventory you have ordered more. This is the demand, right? So then this is the holding cost. Like if your demand is smaller than what you have anticipated, you have a holding cost. And similarly, if your demand is more than what you have anticipated, so you have a shortage cost. So you are going to lose the customers or the business. And so this inventory control, people have talked about it, and they have talked in the context of linear MDPs, where you are talking only about optimizing the first moment of this accumulated cost. Okay, and so this risk sensitive control, what it is doing is, as I have already told you, that it's not just considering the expected value of the accumulated cost, but it is also looking at the second moments, third moments, and so on. Okay, and yeah, so this particular policy is a very, very famous policy called SS policy. So basically, whenever your inventory level is below this small x, you order a quantity that ensures that it reaches up to capital S. That's the policy. Okay, oh, only 1 minute. Oh my God. Sorry. Okay, so yeah, so the main difference between risk sensitive and other things is, can I just take 3 more minutes? I forgot to see the watch. Yeah. Okay, so yeah, see, the main thing is that the main difficulty with this, yeah, they are doing very nice things like you're getting robustness and everything, but at what cost? The cost is that the policies are non-stationary, in the sense, as you can see here, you'll have different SS policies at different time instances, and so it's more complicated to implement these algorithms. So we are going to have but the thing is that when that gamma is not very big, so you have a stationary tail. Okay, so yeah, there are some more applications which I'll have to skip. So like about a probability of an agent getting infected, this has a natural cost which looks like risk sensitive cost, and so on. Okay, it's not just that. What I found is that in literature, we have some literature related to risk sensitive MDPs, but we actually require a combined costs, right? Maybe you are interested in ensuring that a person is not infected, which comes from a risk sensitive cost, but you are also worried about some vaccination cost or campaign cost or something else. So more often than not, you require combined costs this way, okay? So the one important thing with this is that there are no dynamic programming equations for them, as far as I know. Okay, so what is it that we have done? Now I'll go through the results very fast. So for infinite horizon problems, as I told you, they are non-stationary policies, so it's not easy to solve them. So we have proved some approximation results where we said that we can get the solutions of the infinite horizon problems with finite horizon problems. So this is the work with, joint work with my PhD student and my collaborators, Professor Hemachandra and Dr. Sanjay Bhatt. And yeah, so this is about something, and now this is the main thing that I want to talk about. So now that we have moved to the finite horizon problems, we want to know, okay, good, you have gone to the finite horizon problem, can you really solve this now? Okay, that's the crux of it. Okay, even that is not easy, because just think about it, like the usual approach is about augmenting it, the state space, you create a new state, then you can fix it into the linear MDP format, but however the state space is too large and you cannot really implement them. So this is our approach here, which I again was not planning to do a lot of it, because it has, like, the main thing is that we want to come up with formulating this MDP solution as a fixed point solution, and then coming up with a optimization problem whose global optima will be equal to this fixed point, and then use some kind of algorithm to do this. Okay? So yeah, so I just would like to end this with this particular example of the inventory control, where previously without this algorithm I really could not go beyond 3, 4 or 5, 6 time slots. Now I am presenting you the results with 300 time slots. In fact, I have even 1000 time slots I can go on. Okay? So here a few interesting things is that this is the way we are representing the policy, but I would like to say that this is SS policy. Basically you order less or more depending upon your current inventory level, such that it reaches the capital S. And as you can see, it is non-stationary. You see the policies are different at different time slots, and it is not even ultimately stationary when the risk factor is high. And yeah, we also have some randomization, so that I think that's about it. So the summary of this work was, like, I wanted to motivate that we need an algorithm, good algorithms for mixed cost MDPs, because we do see them in many real life applications. And so we have derived some fixed point equations and other things, but of course we need to do little more analysis is left, and then right now it is accepted in a conference paper, but then it would go ahead. Yeah. Yeah.
So what I request is, since we are running so late and we have the opportunity of lunch just after this session, we can maybe take questions offline later. Is that okay? Yes. And then we'll move on to the next talk. So this will be the first of 4 talks from 4 different departments on RL applications. So I'd like to invite Professor Sunoj to go first with RL applications in the area of chemical engineering.
Hello. Thank you, Harshad, first for the invitation to be here and share some of our work done in chemistry department, but in the broad context of applications of AI to be used in chemical space. And since this is a track on reinforcement learning, let me use some of those terminologies and acknowledge people involved with this. So these are my agents, and they have been getting rewards immediately, and they are going to get future rewards as well. Sukriti was a former student. Currently she is in Cambridge for her postdoctoral study. Ajnabi, we call him Ajnabi because it's too complicated a spelling. It may be wrong as well, as I've written. And Mihir is an undergraduate student finishing up his 5-year integrated program, and soon would be moving to another machine learning PhD program in Notre Dame. And of course, other members whose work I'm not going to describe today. I'm thankful to many of my collaborators, Professor Balamurugan from IOR, and Shivram and Abir from CSC, and Preeti for all the valuable suggestions during the course of my foray into machine learning as an interesting activity of research. So the problem with chemical space is that we have huge complexity. It's a high-dimensional problem. Molecules come, collide, react, bonds form, bond broken, fragments produced, show very high sensitivity to the environment, temperature altered, product changes, yield of a reaction which represents a conversion from reactant to product, that changes, it shows high sensitivity. Another challenge in the chemical space is how do you describe molecules which will become amenable to a machine learning problem. So we deal with a lot of featureization issues, and some of which I would just allude to today. And of course, what is opportunity for reinforcement learning? So the context is as follows, that usually chemists do trial and error empirical approach to maximizing yield. So you have a set of reactants A reacting with a set of B's, forming product C, as in this case, and you have set of A, set of B giving set of C. Now the problem is that if you make a small change in A to A1, there can be huge variation in the yield of the reaction. So it's a complex setting. Now, the other challenge and other incentive to work in the chemical space is as shown here. We have a huge corpus of unlabeled data. That means the molecular space is like a stellar universe with so many molecules sitting out there from a data science perspective. From a learning perspective, if you want to make use of these molecules for ML applications, it's going to be very interesting. But when it comes to labeled data, such as known properties of these molecules or known reactions due to these molecules, it's much smaller. And we are in this smaller regime, and I will also refer to how we can leverage the availability of unlabeled data from a transfer learning sense as I go along. So other challenges are sparse distribution. Here is one plot to show. Usual scenario is like this. You have low yielding reaction, very few, because that's culture in chemistry, not to talk about low yielding reaction. Everyone wants to talk about very high yielding reaction. That ends up creating a class imbalance in your labels, that is yield of reaction. And sometimes you get like very densely populated data sets, which is coming from what is known as a high throughput experiments, wherein you react all A's with all possible combination of B producing C, so you have a good dense data, and sometimes you have like very strange distributions in your output. So one should have to deal with all these problems together. Also be aware of something known as activity cliff, that a small change in one substituent. In fact, my colleagues in civil engineering make fun of chemistry department that you guys change a methyl to ethyl and publish another paper. But then the interesting aspect is that sometimes when you change methyl to ethyl, just one carbon up, the activity changes 100-folds. Like you unimaginable change, sometimes you come across activity cliffs as well. So how do we deal with all these issues in both from a predictive sense? So we would be interested in developing regression models which would predict yield of a reaction given the substrates or given the condition. And we also would be interested in generating new reactions, because where the discovery pipeline should start, and if you want to make it more effective, you should explore the unseen territories. These are two activities in my research group. One example just to give you a flavor of the kind of regression model that we are interested in. There is one reaction which is used widely by the industry to produce this kind of compound. Basically, you add hydrogen across this double bond, and one can use a variety of different catalysts. And we have developed a random forest model which has very good performance. Now that I got the first 5 minutes banner, so let me skip all of this just to tell a very important aspect here. Suppose you have a reaction which consists of several constituents, different ingredients coming together. So one can think of a concatenated representation of reactants, and you can convert them into tokenize and numericalize, and you can eventually create a one-hot encoded vector, and that forms the input for a deep learning model. And we have used a language model to be more precise here, a set of LSTMs, and exactly like the structure that one would use in a ULM-fit language model. And the idea is to create a regression model, and we have tried on different sets of reaction. These are the performance matrices, which is represented in root mean square error. So we have some very interesting results from transfer learning, where we use language models to predict the yield or selectivity of reaction. So then we applied this same language model, swooping into the latent space of these huge RNNs, and try to create new library of molecules. This is from the generative perspective. But one key question that remains is that, is there a guarantee that these generated molecules would be high yielding, which is a dream come true for a chemist, that can you generate high yielding reactions. So from that, of course, these are like near neighborhood sampling of the latent space. From the training set, it would have some sort of bounds that it cannot explore way beyond. But we have extended this idea to be able to use reinforcement learning. The idea is to maximize the yield of reaction. So how can RL be useful? So of course, one should start with defining what is your state space. And I've shown earlier that we are converting molecule into linear string of representations. And each of those representation characters used in representing the molecule forms the state space. And one can start with S0 and go on to build strings by adding with certain probability of each new token. And the action space is addition of new token from the listed vocabulary of a given data set. So suppose you were to look at this molecule, and the linearized representation is like this, and you can think of it as a word or a sentence. Now, the possible actions can be from this vocabulary. And if you look at the possible states and actions, the one which has maximum probability in this given example, which is a known example for demonstration purpose, it is nitrogen that should be created given IC1 already in the generated string. That is, at state S2, you are looking for a state S3. S3 is likely to have nitrogen during the training phase. So it learns how to put together atoms and create molecules. But our idea of using reinforcement learning is to maximize the yield of reaction. So we are not just focused on one molecule, but set of molecules concatenated together to be able to react and form new compounds. So here is one reaction. Do not worry about the complexity, but just to tell you that this is an alcohol getting converted into a fluorinated compound. Fluorinated compounds are very important for pharma and under certain set of conditions. But if you don't have such functionality, you will not get the fluorinated compound. The reaction would be regarded invalid, or reaction will not take place. So in that context, there should be a bit of hand-holding when you were to generate molecules under the reinforcement learning context, that we have decided to use a fragment attachment protocol where you sample the molecule from using the state action pairs and reward them accordingly. So we decided to use a rewarding scheme where it would be rewarding only the terminal state provided the molecule is valid. So once you have a valid molecule, you attach a core fragment that will ensure presence of the desired functional group. In this case, hydroxyl group is to be present if you want to do a fluorination reaction. Of course, we use reinforced policy gradient algorithm. And the reward scheme we have innovated to the extent that we had the initial problem of multiple revisits to the same state, and you would have repeated generation of the same molecule. To prevent that happening, we have used an additional parameter, and that had done a lot of, this is just a summary of how good our rewarding scheme has been compared to just looking at the presence of functional group. So it could span a larger area in the space of novelty, validity, and uniqueness of what we create, and while obtaining maximum yield. So this is the kind of pipeline. Since I'm running short of time, as I expected, I will just skip this pipeline, how we have used the regressor, which is built on transfer learning model, and how we do the sampling and use reinforced algorithm to be able to identify new candidates which would be potentially high yielding. Just to summarize our key results, this is a table where the yield of this reaction, the average yield of this reaction is somewhere around 50 to 60%. And we could use reinforced algorithm, the innovated version of reinforced algorithm, to be able to obtain all the way to the yield of 87. And this reaction yield was much lesser, could be pushed to 95 and so on. And this, of course, needs to be tested in a real wet lab setting, and we are looking for collaborators who can validate these predictions. Thank you very much for kind attention.
Thank you very much, Professor Sunod. So like last time, I think we'll have to take questions out during lunch. So I'd like to invite Professor Shivram, who will be doing the next talk for us from the Computer Science Department.
How do I change slides? All right, hello, I'm Shivaram. So it's not a bad time to be talking about chess. I would think for those of you who are following the World Championships, I know it's sitting on a knife's edge as of today. I'm going to talk to you about a variant of chess which is called Recon Blind Chess. I should credit my students, Nitish, Taufik, Anvay. This is all their work that I'm presenting. So what is Recon Blind Chess? I'll begin with that and then tell you about an agent that we have built to play this game. It's called Fianchetto, and then tell you how it fared. So here's the deal with RBC, or Recon Blind Chess. It's chess with a big handicap for the agent, okay? So imagine black, and let's say this is the state of the board. The catch is that black does not know that this is the state of the board. Rather, it has access to what is called a reconnaissance move. It can ask to sense any 3x3 region of the board. And if it asks, then it is told this is what is the pieces occupying that 3x3 region. It's not really told what's happening on the outside. So if there's been action on the outside where white has played some moves, it does not know. Of course, it gets a little bit of information through these recon moves, and it's still got to make its own move. Okay, so this is Recon Blind Chess. You can see that it's a game of imperfect information, which means agent does not have access to state. There's some information that is hidden. Of course, there are many other games. If you played Scrabble or card games like Rummy, Poker, those are all also imperfect information games. Technically, these are hard because of lack of access to state. But RBC is particularly hard also because it is a game with very little public information. There's very little that the two players share. All that each player gets is through its own recon moves. A little bit more about what really we should start thinking about to devise solutions for RBC. So you can see that the key object that an agent has to maintain is what is called a board set. Okay, so at any point of time, there can be multiple boards that are consistent with the history that the agent has seen through its sensing moves. So look at this from black's point of view. Maybe this is the beginning of the game, at which point black knows that there's only one possible board, right? That's when the game begins. But right after white has moved, there are actually 21 possible boards that could have resulted based on white's move. Okay, and black does not know what these are. In order to maybe reduce its confusion a little bit, black can go ahead and sense. In this particular case, it sensed and it was told that there is nothing in the place that you have sensed. Now, based on this, black can infer that 8 of those possible 21 moves could not have happened, right? So it reduces its board set size to 13 from 21. Here's another example, same thing, except this time black decided to choose this region. This was a more informative sensing, okay, because white has actually played a move that happened inside of that 3x3, and after it senses like this, black knows that, well, this is the only possible boards that could be. Okay, so you get a rough sense of what each player has to be doing in RBC, which it does not have to do in chess, right? Because in chess you can see the state. There are other differences between chess and RBC. So this move here would be bad one in chess. Okay, what white here is doing is just taking up its bishop here to maybe try and attack the queen of the black. So in chess, the queen will just come and take the bishop, right? And then you move on. You wouldn't do it. In RBC, you might risk doing this because black might not sense this region, right, and be prepared for this sneak attack on its queen. Here's another example which is actually good in chess, right? This move is good in chess but bad in RBC. In chess, actually, you can do this and go on to win the game. White can go on to win the game. In RBC, agents are given access to something called a null move. Okay, null move means nothing moves. And if that is the case with a null move, black can actually survive forever. Okay, so I mean, clearly at some level they are similar, but also because of the partial observability, they become different. So what really did we do? Okay, so I mean, by the way, so the reason we got this competition, to play RBC is there's a competition that happens every year. And so my students got interested. We decided to build an agent to play this game. So I'll tell you about Fianchetto, the agent that we built, and then how we fared. So our starting point was an agent that was already published for RBC. This was called Strangefish. Okay. any chess playing game, right, you would expect like a core feature of it, a core module that it has inside is what's called an evaluation function. Okay, so given a board, it has to say how good is this board from the point of view of white or black. So Strangefish, the scoring function it was using, was based on Stockfish. So chess players around will know that Stockfish is one of the best evaluation functions for chess. So what Strangefish would do, given a particular board, is evaluate every possible move, look at the next state based on that move, run it through Stockfish, and get the score for that particular move. Okay. Standard, I'm just telling you first what the baseline is doing, and then I'll tell you the changes we made. The thing with RBC is you don't have one board, right? But at any point of time, you have an entire set of boards. So then Strangefish does the natural thing of doing that same thing for every possible board. It takes every possible board that's there currently, consistent with our history, that's called the board set, and then gets a score, right, by trying every possible move and so on. And finally, the strategy that is used by Strangefish to decide which move it is going to make is it evaluates the move on each possible board that is there, right? And based on that vector of scores that it gets, it aggregates, right, and says, well, this move is probably going to be the most beneficial for me. Strangefish also has a fairly sophisticated sensing strategy. I mean, so intuitively, what squares must you sense, right, as recon moves when you're playing RBC? Presumably ones that will reduce your confusion the most, right? They'll bring down the uncertainty by the most. So that is the major component of what Strangefish does. It also has a few other things which we really don't have to go into, but this is really where we started. So Strangefish existed, and then we got in and tried to build our own agent. So I'll tell you 3 or 4 changes that we made, beginning with one very opportunistic one. Okay, so my students debugged and noticed that one of the main bottlenecks in Strangefish was the time it was taking to go through these evaluations, right? So the first thing we did was replace Stockfish with a cheaper but faster evaluation function called LC0. So the good thing about LC0 is it just takes the board and runs it through a neural network. And this is something you can do in parallel, right? Particularly now you know that neural networks, you have GPU implementations. So we can actually evaluate many, many boards on many, many actions quickly, right? And get scores for all of them simultaneously. And this speed allows us to actually search one step deeper. Okay, that will come up very shortly. So first was using LC0 instead of Stockfish. That's version 1 of Fianchetto. Version 2, this is probably the thing that made the biggest change, is we did a very principled update of what is called the belief state. Okay, for those of you familiar with POMDPs, there's something called a POMDP belief state update. So you have this set of boards that is consistent with your history, but how probable are they? What weight must be ascribed to each of them? So what Strangefish was doing was saying that a board in your belief set, give it as much weight as it is good for your opponent. Okay, but this somewhat intuitive rule does not take into the fact of the time it would take, or the probability with which this particular board would be reached historically, right? It sort of forgets, this calculation can be done at any point of time without sort of factoring where you came from. So the POMDP update rule is a lot more principled, right? It really, the current belief, the starting point for that is your previous belief, okay? And you take that and then you reason about how the opponent might have acted, and you do like what's a Bayesian update. I mean, this is of course too much to go through right now, but this was probably the biggest advantage that we had. We ended up, right, the blue line here is ours, this is Strangefish's. We were able to put a much higher probability on the true board state, okay? Third, we made some very RBC specific changes. We actually gave extra incentives for things like these sneak attacks. If you just used LC0, right, for evaluating how good are the moves you're making, you'll get good chess moves, but not necessarily good RBC moves. So the students came up with some additional incentives for things like this. And last but not least, the thing we did is we put in some extra measures to keep our board set small. Okay, having like a very confused board set is the worst thing, right? It's where you're departing most from this assumption of having access to state. So we put some aggressive measures to keep the information set small. We took all of this and we went to the NeurIPS 2021 competition, and we actually won by a very emphatic margin. So we came first, and we had almost 100 ELO points separating us from the second placed agent. You can see that the overall score is 931 to 89 games. Okay, so we were quite emphatic in how we won. We had at least a 2-1 record against each of the other players. I can't really end on that high note because we also went to NeurIPS 2022 the next year and we came second. Okay, but second's not too bad. So where does this leave us? Of course, we are continuing to work on it. So RBC, as I have described it to you, is a sort of new frontier for work on imperfect information games, which are much harder than games like chess and Go, where you have large state space, etc., but you have access to state. Our agent, Fianchetto, you could see, right, it's got multiple moving parts. It's the product of a lot of good engineering, but it is highly exploitable. Okay, for a game theorist looking at this, it's not like we are at equilibrium or something like that. There are clear reasons. If you know what Fianchetto does, you can actually develop agents that play well against it. RBC in general has a lot of good science that can be done. Okay, it's a computationally hard problem. We heard some time back about POMDPs. So we're talking here about a generalization of POMDPs that has multiple competing agents. Okay, so I'll finish with that. Thanks.
Thank you, Shivram, and congratulations on both years' worth of results. So next, I'd like to invite Professor Aditya from the Aerospace Department and coincidentally also my colleague at TCS to talk about RL applications in the aerospace area.
Okay. Hi, good afternoon, and thanks for inviting me here. So I'm going to take a slightly different approach to this talk. This is not just about RL in aerospace, but more about AI in aerospace. I don't know how many of you here have had exposure to aerospace, but I thought I should show you a broader canvas of problems where methods from AI have been applied in the past, where they get applied at the moment, and also show you hopefully some interesting work from which other ideas can be spawned. How do I move this ahead? Okay, there you go. All right. So interestingly, as some of you might know, the pioneering conference in where AI was defined happened in 1956. And then one of the first major developments in AI and AI-based robotics was in 1965 when the A-star algorithm was implemented on the Sharky. In aerospace, however, for a number of reasons, a learning-based approach to flight control came about, in fact, in the 1950s. So model reference adaptive control was invented back in 1958. It had its origins in manned flight of combat aircraft. I mean, these airplanes are fairly agile, and what you want is that the pilot who flies them should feel the same no matter what speed the flight's at or what angle of attack the airplane's at. So it's a few technical terms. But that's where the idea of model reference adaptive control came into being. And here the idea was you actually made small adjustments to the control law dynamically in real time and adjusted it so that it took care of the uncertainties and external disturbances. In 1967, there was a crash on this particular airplane. It's called the X-15-3. And what happened here is something that people who study RL and adaptive control are fairly aware of. There was a divergence in the control parameters. They failed to converge, in fact, to be precise, and this airplane crashed. And this was a pivotal event because after this, it took almost 40 years for the adaptive control community to actually get a flying adaptive control law on a manned airplane. But that thankfully has happened since then. Now, the reason why I actually mentioned these two episodes is to give you a sense that although AI and learning took off in a big way, at least in our consciousness socially in the past maybe few years, this line of thought has been around in the community in a sound engineering sense for at least the past 50 years. Now, when I was asked to give this talk, I thought, okay, let me check one thing. Everyone here talks about neural nets. When did neural nets make their way into aero in an engineered sort of way? And to my surprise, that happened in 1991. This wasn't exactly for control, as in this neural net wasn't controlling the airplane, but this was actually used to identify the aerodynamic coefficients and actually figure out if there were any faults in the flight control system. And this flew on a specialized platform called the F-15 Active, which you see here in this photo. So RNNs were implemented back then. I don't know if they were entered production though, but at least on test airplanes, manned test airplanes, they've already flown. So hopefully having shown you that we have this fairly rich history of intelligent control in aerospace, let me tell you a little bit about how control is viewed in aerospace, because this philosophy is very distinct to aerospace. Now, in aerospace, adaptive control has typically been implemented on what we call the inner loop. So you have the flight dynamics here, the flight physics. The first thing you do is you want to stabilize the flight physics. You want to manage the rotations of the airplane. It's a 3D body. You don't want it spinning on its own axis arbitrarily. And these two motions typically happen with time constants of just a second, couple of seconds at most. And this is where adaptive control has traditionally been used. You then move on to slower motions. Those kind of problems are called guidance problems, navigation problems. These are all words that you've used. And at the very outside, you have mission planning, which is the slowest. It's done on the order of once every few hours or so. And this is where AI-based methods have traditionally been used. That includes automated real-time task allocation or problems in motion planning have all started off here. On this side, however, what we really want is a policy that is as stationary as possible. We value stationarity in aerospace because it can be validated and it can be given a safety certificate. However, what's happening now is that with computational power growing, we see now a shift towards this side, the traditional policy side, coming from typical planning approaches. And what I mean by planning is, at a certain point in time, you project where you're going to be over a certain time horizon, and you take decisions without necessarily bothering about stationarity. That's slowly and steadily making its way in. However, for now, that planning mindset is still restricted to slower problems, where updates happen, like I said, with mission plan once every few hours, to guidance where it happens typically once every few minutes. All right, so let me just show you some examples of how we've actually been using AI in aerospace problems. Some of this actually comes from work I've done over the past 7 or 8 years. The first problem I'm going to show you is that of maneuver optimization and motion planning. So motion planning is a standard AI problem. Like I said, it started back in 1965. And from the aeronautics side, one of the questions that I asked was, well, what can a plane do that helps the motion planner work efficiently? Or alternately, what can we do to make sure that motion planner is not constrained in any artificial way? So to that end, we actually use our knowledge of flight physics to design what are called transient maneuvers. These are maneuvers you can't fly continuously. You fly them in short bursts of time, and you design them actually by solving a finite horizon optimal control problem. And you can even solve these in real time. Now, let me show you an example of how these actually work. I have a little video now, and you will see these tests conducted indoors in McGill, and you will see this plane doing a whole set of motions. You see the plane going on the side, and the plane now just going into a hover. This plane was given a virtual map of the environment, and it had to plan its own path using rapidly exploring random trees, or RRT. And all of those maneuvers that you saw there were actually performed in requirements that came from the specific task. So we created a virtual map with narrow corridors. So the plane went on its side to execute a knife edge. It then ran into a pillar, and so it had to perform what is called as a hammerhead turn. So go to high angles of attack, like literally get its nose up and perform a sharp turn and get out. So these maneuvers were all kind of taught, if you will, but the decision to execute the maneuvers was taken pretty much in real time in response to planning. Here's another example of how AI is getting used now. It's actually quite an interesting problem where you have to herd birds using drones. So we started working on this back in 2013, and the idea was to keep birds away from airports. But as I found out recently, keeping birds away from areas is an interesting problem even in fields like agriculture. So there are, for example, I don't know how many of you have heard of these birds called quillias, and quillias are known to devastate farms in Africa. At this point, they kill quillias, or they use insecticides which kill quillias but also other birds. So they're trying to find other solutions to those problems. And one way in which we did it was actually experimenting with drones to keep birds away. Now, of course, we haven't answered all questions. We just conducted just a basic proof of concept kind of a study. Let me see if I can just play the video with this. Yeah. So here you will see 5 birds not being herded but actually being deflected away. So there's a drone somewhere in here, and as you see birds approaching this area, you'll see the drone moves closer to them, and then the birds respond in a certain manner. So what we did here was we constructed a model for how a flock moves on its own. We built a model for how a flock ought to respond to this drone. And from there on, these experiments were conducted mostly to populate the parameters in that model. Now, this is quite challenging really, because we conducted just a handful of experiments. What we know is that as you conduct more and more experiments, birds actually learn behavior. Birds are social, they're very intelligent, and therefore their strategies in response to drones actually evolve. So that at this point is an unsolved problem. What we demonstrated was, at least on a series of experiments where the birds weren't behaving very differently, we could actually learn their parameters, their behaviors, and then take maybe just a principled approach to herding them away. Now, with AI and autonomy, I thought I should just maybe mention some interesting areas that are evolving in Aero, and hopefully this will be of interest, especially to the students who might be looking for projects and like. On the commercial airplane side, the primary application, if you will, of AI that people are looking at is safety. I mean, safety is a number one concern in commercial aviation, and what we want to understand is whether AI can actually help pilots fly safely. Can it help them under routine conditions with basic decision making, and can it help them deal with emergency scenarios? This at this point is still an open problem. There might be a few recommender systems here and there, but there's nothing in production to actually do this job. At this point, if you have an emergency, you just use checklists, and that is about it. But this is where AI can play a big role in commercial aviation going forward. A second application that's coming up now is that of what are called as loyal wingmen. These are airplanes that are designed to fly with a manned airplane. So these airplanes by themselves are unmanned, but they have to stick close to the other manned aircraft, keep it safe, help it with some weapons platforms, occasionally help it as sensors. And the question is, what can these airplanes do if the manned airplane itself is taken out? So that's currently an open problem. This capability is developing all over the world. India also has a program, and hopefully this might be of interest. And finally, this is an area that's of interest to me. When I started working on the problem that I showed you at the outset of a maneuvering drone in a congested area, the idea was to enable drones to fly through densely packed areas. You see these kind of areas, by the way, in Kashmir, where a lot of our operations are conducted, counterinsurgency operations are conducted. And what I'm interested in is looking at what are called as buddy drones. So these are drones which can fly through forests at high speeds and just help soldiers with tasks like, picking targets or occasionally even playing more aggressive roles. But I think all of these problems, these are very hands-on problems, not very theoretical, but this is where you can actually apply AI on the field, and it's quite a satisfying experience. This should be realizable within the next 5 to 10 years. Okay, so I'll end on that note. I thought I should also just show you some broad themes in aerospace. I'll just let you read them. But these are all areas that are coming up, and these are very much of contemporary interest to the community. So I'll stop there, and thank you very much.
Thank you, Aditya. And we'll have a fourth talk on RL applications from a fourth different department, Mayank Baranwal from Systems and Controls.
Yeah, thanks, Harshad. So before we start, exactly almost a year ago, on 9th May, Mumbai had a wide area outage because one of the key transmission lines had tripped. Any guesses as to why this may have happened? So this was in fact a part of a scheduled maintenance. So the grid operator was an inexperienced grid operator. So there were a sequence of actions that needed to be performed. But the order in which they were performed, it ended up tripping one of the key power lines. And that resulted in Mumbai getting isolated from rest of the power generation in some sense, and that's why we had an outage. So the schematic, so the network you see over here, it's a simple 4 substation network. So all these different substations, they are connected by power lines of some rated capacities. So in this case, the red indicates that there's an overflow happening in this particular power line. And if you let it happen, if you let the overflow happen for a sustained period of time, this may result in the permanent damage of this particular transmission line. So once this transmission line gets damaged, so the rest of this network or this particular substation needs to be provided with certain required amount of power. So the excess power would start flowing through other parts of the network, and this would result in overflow in other parts of the network, and eventually this will result in tripping or in some sense a wide area outage. So in order to avoid that, a very simple and elegant solution is without having of course there are other solutions where you can increase the dispatch from the generators or maybe drop some of the flexible loads, but that has its own time scale. But what you can possibly do is, so all these substations are equipped with something called double bus bar. So you can simply basically automate the splitting of this particular substation into 2 different buses. And now what happens is, there are two different routes through which the power flows to this particular substation. So the total power that now flows through this particular line is within the rated capacity, and you can very well manage this entire network. So this is an example of a very simple network with just 4 substations, but that's not the case when we talk about grid operators. That's not how they basically operate. So they operate under a lot of constraints. So for instance, there are constraints, as I already talked about, there is something called scheduled maintenance, so which they have to take care of. So they have to schedule the sequence of actions in such a way that there is no overflow. There doesn't have, there are no incidents of overflow happening in any part of the network. So of course, we are talking about smart grids and integration of renewables and so on. So with the integration of renewables, we have a lot of uncertainty in generation, and people also, with access, depending on the weather and so on, we have loads like which is like air conditioners or maybe heating loads and so on. So those the flexible loads or the loads, they are also going to be uncertain. So there is a lot of uncertainty in the network because of the generation or on the load side. And finally, there are adverse events. And when we talk about smart grids, there can be cyber-physical attack on the network, or maybe there is some lightning may permanently damage one part of the network. So you still want to be able to reconfigure the underlying network topology in such a way that you still manage to run this network seamlessly 24/7. So Shivram, in his talk, he talked about one particular challenge that he participated in. So we participated, well, not during the challenge, but once the challenge got over, we came to know of this problem. We participated in this challenge called L2RPN, or the Learning to Run Power Network Challenge. And what you see in the picture over here is a skip. In fact, it's 1/3 of the IEEE 180 network, which is a reduced order representation of the US Midwest electricity grid. And if you look at this particular network with about 36 substations, one of the key substations, for instance, substation 16, this has about 17 different elements. So an element can be a line, or it can be a generator or a load. So when you do a bus bar splitting, or when you decide which particular substation which particular element needs to go to which bus, when you do the bus bar splitting, there are combinatorially many underlying topologies possible. So you can decide maybe this particular generator needs to go to bus 1, and this generator needs to go to bus 2. Likewise, you can have decisions about those individual lines and individual loads. And as I said, this results in combinatorially many underlying topologies. And for a very simple substation, just for this particular substation over here, there are in fact 65,000 valid, electrically valid topologies. So when we're talking about this huge action space, there is no way for an experienced, even for an experienced grid operator, like if there are unforeseen events happening in the network, even for an experienced grid operator to take care of and be able to mitigate it in such a way that there are no permanent damages in the network, that basically is it's beyond human comprehension in some sense. So this challenge was catered towards how can we include RL, maybe RL or AI in some sense, to be able to mitigate such kind of effects. There are obviously other challenges. For instance, as I mentioned, there's uncertainty with renewables or adversarial line attacks, and so in order to basically ensure smooth power delivery, we basically looked at RL as one of the key solutions. And the reason, why we used RL is because, first of all, we are working in an action space which is combinatorially large. We are also, there's a very nice underlying power flow network dynamics that you can always simulate. So you can have access to very powerful simulators for simulating power flow in networks. We have access to expected demand in the next time instant. So you can always evaluate a particular action and see the effect of it based on the expected demand forecast and expected generation forecast. So again, working with 65,000 possible actions is impossible. So we simulated a lot of scenarios because we had access to a very good simulator, and we found about 240 odd actions, which often repeated in which often resulted in profitable sense. So out of those 240 actions, we basically trained a PPO agent, and the grid operators, even though they may or may not be experienced, they are obviously smart people, and they have a knowledge of underlying physics of that, right? So we also applied some heuristics from the electrical domain. So essentially, RL agent, the decision from the RL agent that was combined and also compared with how heuristic would perform. So the combination of this entire thing is what we ended up making. So essentially, at each state or at each time instant, the state that was accessible to the RL agent was the overflow happening in the overflow ratio in each of the power lines, the generation, basically the voltages and the loads and basically the generation available at each of the substations and so on. And when RL agent outputs a particular action, so that was compared against, so because there, these are you have baseline topologies already in place. So we do not want to alter it unless there is a need to alter it. So only when the specific overflow threshold is more than, let's say, critical safety value, which is about 0.95 or 0.96, is when we engage the RL agent. Otherwise, we don't engage the RL agent. And we combine it with some physics-based heuristics as well. So this was the effect on when we participated in the NeurIPS 2020 challenge, L2RPN. So in fact, we topped the leaderboard. So do nothing is when you do not take an action. And what you see in the basically heat map over here is different test scenarios, two different test scenarios, like what is the survival rate of the different agents. So expert heuristic is how, for instance, an expert grid operator would perform in this case. And you can see there are scenarios where it's able to survive maybe just 2% of the entire scenario or 6% of the entire scenario. Compared to that, we basically ended up building POW-RL, which basically topped the leaderboard. And in a lot of scenarios, it basically it survives the entire scenario. But some of these scenarios are very challenging in the sense that, particularly in the months of February and December, when there is a lot of uncertainty from the generation side. And in this competition, they did not allow us to change the generation or drop the basically drop the load. So that's why it's also very difficult to maybe survive some of the scenarios fully. But then we also applied this to an earlier version of this challenge when there were no adversarial attacks at least in the competition statement, there were no adversarial attacks, and we survived all scenarios completely in that case. So this is basically the full survival thing. So compared to other state of the art, so this is our particular approach, which basically, so they have their own way of evaluation, and we topped the leaderboard with the least number of actions. And we did not engage any redispatch or any other kind of additional actions other than changing the baseline topology. So this work was also awarded the Gold Award by the Indian Smart Grid Forum just recently, and also appeared in AAAI this year. So I guess I'm out of time, but I'll just maybe show you one particular I guess. Okay, so you can see that, we are changing the substations over here, and red would indicate that a particular line is under stress. So because we are actively changing the substations basically changing the bus assignment here, so you can see, eventually we basically get rid of all the, there are no events where we actually have overflow happening in any of the power lines. So with this, I would like to end the talk, and I think I can address the question.
Thank you, Mayank. So we'll take questions after lunch. So we'll now switch to the multi-agent AI portion of our workshop. So I'd like to invite Professor Sopra from the Computer Science Department to talk about strategic multi-agent AI.
Thanks, Harshad, and hello everyone. So this talk is about strategic multi-agent AI, and we'll see very soon that how it connects to economics. So for a simple exposition, let me start with an example, a little pictorial example. What is multi-agent AI? So imagine you have a group of individuals who are trying to take one collective decision, and they have something which is private to them. So some information which is not held publicly, they have their own information there. And situations of this kind can occur in many applications. So for instance, you are trying to give out a resource, maybe a divisible resource or an indivisible resource, in some fair manner. So where we have not defined some appropriate definition of fairness. Or suppose you are trying to, so this group of individuals are involved in some collective project. So one project where there could be only two outcomes, success or failure. But the success depends on the costly efforts put in by each of these individuals. So in that case, those XIs are essentially the efforts that are being put by each of these individuals. Or suppose you are a municipal corporation and you are trying to take a decision on a specific public project to build a bridge or build a street within a budget, and you want to take that decision based on the citizens' opinions. And there are many such examples. And in all these cases, what is common is that you have multiple individuals, their information, some private information, for instance, their preferences over these different resources, or how much cost they have to do certain tasks, or what is their opinion about different public projects, are private to them. And the decision maker, let's say the central planner, needs to take a decision which is efficient in some sense, where efficient is properly defined. And these agents are not necessarily human agents. This could be robotic agents, or could be a mixture of the human and robotic agents. So for instance, in online auctions, these individuals, the bidders could be replaced by a robotic bidder or an automated bidder. So in this case, what the objective of multi-agent AI, or primarily my research, is to give certain kind of guarantees where these agents do not manipulate. Remember that the optimal solution that we want to have depends on their private information, and we want that they do not manipulate this private information so that to sway to the decision on their favor. So this is something that we are interested in. It's a kind of a multi-agent algorithm design problem, and we want to ensure certain good properties, including non-manipulability. But that's not all. We also want to transform the learnings that we have, we can design using these multi-agent algorithms to design maybe apps to assist humans who can take provably efficient decisions. So maybe designing this common resource sharing in a fair manner, we want to design an app where people can automatically take these decisions. Or maybe a participatory budgeting problem where the central planner, like the municipal corporation, can decide which public projects to pick based on the votes or the opinions of the individuals. So because this talk is going to be short, I'm just going to look at one specific example. So this is essentially where this work falls in. It has significant overlap with both computer science, because we talk about computational problems, but it also has significant component from economics. So let me just take one example, which is pretty simple to explain, and perhaps you have already seen it in many contexts. So suppose we are trying to auction one item, let's say a painting, and there are different individuals who have different value for this item. So by value, I mean that how much they are really willing to pay for this object. So somebody, for instance, in this case, the agent 3 is possibly an art lover, so his value for this object is very high, while the other agents may be having a smaller value. And this is not a priori known. This is exactly where the private information comes in. How much they value this object is only known to them, and some planner or the auctioneer does not know it. Now there are many standard ways of doing it, and the thing that I'm going to talk about is what is known as a very standard mechanism for auction. So the question that we are after here is how to allocate this object, a single indivisible object. You cannot break this picture into multiple pieces and give to people. So you'll have to allocate it completely to the individual who truly values it the most. Right? So we do not know who values it the most. So we run a kind of an auction, which is doing the following things. First, it is asking everyone to bid. That tell me how much you value each of these items. Based on what you have reported, I will just declare the highest bidder to be the winner. So the highest bidder will take this away. But they will also be asked to pay something, and that payment will be the second highest bid. So in this specific example, agent 3, if all of them had actually reported what their true values are, shown in this picture, the third agent would have got it, and it would have paid the value, which is value of 1, the player 1's value. And you can see that because of this difference and our notion of a net payoff or net profit for every agent is what their true value is minus what they have paid. So this difference between this dotted line and its true value is essentially the payoff that this agent is getting. So this is quite a well-known mechanism called the second price auction. And what is good about it? It is truthful. And let me try to convince you briefly why this is true. So you can see that for third agent, assuming that the other two agents are reporting whatever they are reporting, if agent 3 increases his value, he still becomes the winner, but he still pays the second highest bid, which does not change. So his net payoff is not changing even if he's overbidding. Right? But if he underbids, he has a specific challenge that he might fall below this line, and in that case, he might lose the object altogether. So that's a loss. So therefore, he will never try to manipulate either upwards or downwards. There is no benefit in doing that. For agent 2 also, you can see that the only way he can change, she can change the outcome is by reporting a value which is even larger than 3. That's the only way she can win that object. But in that case, she will be asked to pay the value of 3, which is much higher than her true value. So her, yes, she owned the object, but her net profit would have been negative. While if she did not bid that high, she could have lost that object, but still the value would have been, the profit would have been 0. And I'm not explaining for agent 2. In fact, it can be shown for all these agents. It's truthful. I mean, they do not want to over-report or under-report. And this problem is a well-studied problem, in particular for a single object indivisible item auction. It's already known how to maximize the reward revenue for the seller. So the objective of an auction is to get as much revenue as possible. It is known that how to design auction which maximizes the revenue for this expected revenue for the auction year. Now I'm going to talk about one development which our group is involved in, which is called the network auction. How is it different from the classical auction? We have just explained the classical auction setup. Suppose there are 4 agents, and the numbers represent how much they value this object, and we know the second prize auction. Now, what is happening in the network auction setup is that these agents are not directly available to the seller. In other words, they're connected over a network. So seller does not see directly 3 or 4. They are connected only if agent 2 forwards this information to 3 or 4. Now, what you can see is that you can still run a second prize auction. You get 3. The seller can get a price of 3. But this agent here is not getting any payment, even if he is forwarding this information. So what if he plays evil and say that what if I just remove these 2 agents? I do not forward it. Earlier I was getting 0 payoff. Now what I'm going to get is this 2. So because I'm now going to be the winner of this auction, and I'm going to pay 1. So my net payoff is 1, which is larger than 0. And the revenue that this seller is getting is just 1. The auction could have been redesigned in a different way, that you do the same thing, highest bidder wins, pays the second highest bid, but each forwarding agent gets that threat utility. So I call that amount 1, that payoff of 1, as the threat utility that this agent is possessing because of his position in the network. So now the mechanism does the following. It awards the object to the highest bidder. It gets that payment of 3, but it also gives a certain commission out of that to this agent. And now he has no reason to not forward this information. In fact, you can see that the payoff remains the same for this agent, and the revenue becomes a little higher. For the seller, the revenue becomes a little higher. So because I'm running out of time, I'll just say that this is an ongoing work where we have actually characterized what is the structure of the truthful mechanism in this context, very much similar to what it is known for classical auction, but there are quite a lot of non-trivial changes. And also we can characterize for a specific commission type of mechanism what is the revenue maximal auction. So this is still under review. I just want to, just go over one applications, and another application of this area, which is called the social distancing by social scheduling. Essentially, if you have one particular store and there are multiple individuals who are trying to come to this store, if they are uncoordinated, they will all collide at a specific time, and there should not be, they might not be able to maintain any social distancing. So in this work, we actually try to give them incentives so that actually they space up in this different time slots, and the incentives are given in terms of time, that If they are given a priority, they will be asked to wait for a very long time to access the store again. And using those times, you can actually ensure that they come in different slots and proper social distancing could be maintained. Okay, so let me just keep the details here. And this is a work that work with one undergraduate and one my PhD student. It's going to appear in AMAS this year. So there are various applications. I just spoke about the online advertisements where auctions are used, fair allocation, kidney exchanges, organ exchanges, priority scheduling, peer grading is a very compelling example. And all these cases, you will have to design this setup from the viewpoint of economics as well and guarantee certain desirable outcome. Okay, so let me just skip over. So there are some, because this is also a CMIND's talk, so I just wanted to wanted to highlight that there are certain courses which actually is designed to develop the tool set that is required to handle this kind of setup. These two courses, CS6001 and 2 are essentially that. One of them also has an NPTEL version. And all the video lectures are available, so it's very well designed for self-training. Thank you very much. Yeah.
Thank you, Swapra. And finally, we'll have Professor Ankur Kulkarni, who will wrap up this session by talking about statistical analysis of strategic actions.
Okay. I'm honored to be the nth speaker in this session. I've lost track of what the N is. Okay, so I'll talk about learning from strategic actions and a problem that is pertinent to all of us, which is university admissions. Okay, so think of the dilemma that the university faces and the dilemma that the student faces. The university the student has a true aptitude, and the university would like to assign a program to the student based on its true aptitude. But however, what it can only observe is its demonstrated aptitude, which is the aptitude that it demonstrates through an entrance exam or something. And the student on the other can make an effort to change its true aptitude, make its demonstrated aptitude look different from its true aptitude by going for coaching or copying or whatever. Okay, so there is a distinction therefore between what the student should have got based on its true aptitude, which is unobservable, and what it could end up getting based on its demonstrated aptitude. So the question for the university is, how should it set up an entrance test to correctly assign a student to the right program, and how can it learn this from past data? So think of the innocent JEE days. You have past data of when at a time when there was no coaching, the true aptitude was also equal to demonstrated aptitude, and now times have changed. There's a new normal, but by the time you figure out the new normal, the normal itself has changed. There is today heavy coaching, and so now the student is basically now manipulating the data that you have available at the time of testing. So you have the data of your training is from the 1960s or whatever, from when the true aptitude was actually available to you as the demonstrated aptitude. But today, at the time of testing, that's not the case anymore. Okay, so you have a true aptitude X, a true label H of X, which is available through your ancient data. But today the aptitude that the student shows you or the adversary shows you is S of X. And you want to design a classifier using the old data, which will look at the demonstrated aptitude and still give you back the actual program the actual label that he should have got. All right. Okay, so this is a problem that I am not invented. So this was actually introduced by Hart et al. And the work that they focused on is focused on what is called uniform preferences. Uniform preferences means that all students uniformly prefer a particular program. So if there are two classes here, minus and plus, all feature vectors prefer to be classified as plus. All right. So in that case, a naive classifier is one where the class boundary is equal to the decision boundary. You put the decision boundary exactly at the class boundary, and so but then because of that, because there is a possibility that students can make an effort to demonstrate a different aptitude, what happens is the guys who are here on the negative side can actually can appear as if they are on the right side and then get classified as positive. So then, therefore, the answer to this is to then come up with a classifier that accounts for this manipulation, and the answer is the correct classifier is the one that essentially shifts the decision boundary shifts from the naive classifier to this. This becomes your strategic classifier. Now, what this effectively means in the exam design context is you are effectively making the exam harder. You're basically asking students to work, show the bar is raised effectively. All right. Now, corollary of that also is that the guys who are in fact already plus based on their true aptitude will now also have to move onto this side, because that is where the boundary has shifted, and therefore you have a proliferation of coaching classes and so on. Okay. Now, what we will look at is the case of classification, but where the preferences are not uniform. So there are guys. So we will have a case. We have a case where there are guys who want to go from here to here, as well as guys who want to go from the right to the left, right? So there's a non-uniformity of preferences. So if your true label is minus and the reduced label is plus, the utility you get is u plus. If your true label is plus and the reduced label turns out to be minus, you get utility u minus. The other off diagonals are both 0. This is so in this setting. And the manipulation incurs a cost. So if your true feature vector is x and you move it to z, you incur a cost based, let's say, equal to the distance between x and z. This is the setting that we are considering. And we have samples here from, as I said, from the 1960s when you had the true label and the true feature vector and the true label was available. And you now need to apply this to the current scenario when manipulation is possible. Right. Now, the key game theoretic insight in this, which comes up, which is not applicable, which is a new thing that comes up because of the non-uniformity of preferences, is that that a classifier must perform a form of feature selection. Okay, some part of the feature space must simply not be allowed for reporting. What this means is, in the university admissions context, it means that there are some classes of questions that you should not be asking at all. They should be given 0 probability, or basically should not be asking. You should not be assessing students on those. Effectively, if there is a certain set of questions that students can basically be coached to answer very easily, then there is no point asking those questions. Answers to those questions are non-informative, and therefore creating a criteria based on those type of answers is pointless. So this is equivalent to putting a penalty on some features. Okay, in game theoretically equivalent to putting a penalty. If you take a taxation context, say for example, if you are asking people to reveal their tax slabs, for instance, what this means is you should not be asked if, say income, you don't ask something like, is your income between 0 to 5 and 5 to 10? You ask, is it between 0 to 4 or 6 to 10? The 4 to 6 gap in between is actually blanked out. You just don't allow that as part of reporting. So what this means is there is the strategic classifier label set now is not just the plus and minus classes that you had, it's plus, minus, and a new label, which is the penalty label. Penalty label means that part is removed from question. Now, a corollary of this is obviously there is some stuff that you'll never be able to recover, which was not the case earlier. Earlier, everyone had to go for coaching and then was able to somehow make it, but that's not the case anymore. So this becomes, this is a problem, but it turns out you can't do better than this. Okay, so you can set this up as a game and look at the Stackelberg equilibrium of this game. And I'll tell you what the one Stackelberg strategy for the university is. It is to look at, if your feature space is interval from 0 to 1, you map 0 to z minus as minus, and z plus to 1 as plus, and everything in between is mapped to delta, which means basically it's removed. You don't ask questions from this region. And what the implication of that is the recovery then becomes 0 to x minus, where x minus is a little ahead of z minus. That gets recovered as minus, and everything from x plus to 1 gets recovered as plus. And this part is what the minimum of u minus comma u plus is what is not recovered. Right? Now, what if you did not? So you of course don't like if you don't like the penalty. What would this do? It turns out you can't get around this. you try you try a naive classifier where the class boundary is equal to the decision boundary, you get a much larger region which is incorrectly recovered. If you try a strategic classifier without this additional penalty label, again there's a larger region than my previous region that does not get recovered. So all of these classifiers all underperform necessarily. Okay. All right. Now let's come to learning. Now you have your past data, which is where you have a true feature and the true feature and the true label for that data. You can now do learning because you have the true feature and true label for that data. You can actually estimate the function directly using whatever method you want. So you can find an estimate of estimate h hat of h from here, and then on that create a game theoretic layer to estimate what should be the strategic version of this of the classifier, assuming h hat to be the true function. This sort of stacking or layering of blocks can be likened to what control theorists called as separation of estimation and control framework, right? And all the control theorists in the audience are nodding because this hits right at the heart of many issues. So this can be likened to a separation of estimation and control, and as a consequence, what we get, what you can kind of conjecture is this is not going to be optimal. Okay, separation architectures usually underperform, no matter how much we like the stacking of things and so on, but they usually underperform. A joint estimation is usually better. So what is a joint estimation? A joint estimation is one which takes into account the fact, the response of the agent as part of its learning procedure. So you don't learn naively and then apply a game theoretic model, rather you take the game theoretic model as part of the learning itself. So you do this, once you do this joint estimation, we get an algorithm called the strategy-aware ERM algorithm, and that actually gives you a better performance. What do I mean by better performance? You can if F is your original class and S is the class that you effectively end up applying the strategy-aware algorithm on, you can show that S has a lower VC dimension than F. Okay, so same number of data points actually are more informative once you take into account the structure of the problem. That the strategy awareness being strategy aware induces structure and therefore leads to more information extraction. Right? A similar theme has played out in my earlier work in information theory also, strategic information theory. You are welcome to read that. This in fact holds in a more dramatic way as well, where the original class can have VC dimension infinity, and the reduced class that the strategy aware version can have finite VC dimension. And that's again basically structure helps you eliminate hypotheses that are you can have sort of pathological classes where there are nonsense hypotheses present, which can all be eliminated once you take into account the structure of the problem, the strategic nature of the problem. Okay. All right, so what's the big picture? The big picture is that game theory and statistical learning are both information sciences, and one arm of game theory, example auctions like what Swaparvat talked about, concerns the creation of systems of incentives, payments, penalties, etc., so that agents reveal their true information. And this is so what we are basically, what I have basically talked about is the impact of one such instrument on the learnability and learning of in a learning context. All right, this is just scratching the surface. A proper interplay of game theory and statistical learning will come up in a few years, I guess. Okay. All right. Enjoy your lunch.
Thank you, Ankur, and I hope everybody got the even bigger big picture that there's a lot of work happening in this area, and that's why we had so many speakers also. So I apologize to the speakers and the audience that we couldn't take questions, but I hope you'll use the opportunity of lunch to talk to the speakers and so on, and we'll end. I think the next session is scheduled to start at 2:15, so we have about 35 minutes for lunch. Thank you, everybody.
So may I invite now our first speaker, who is Ameya Divekar from Michelin. He'll be speaking about how Michelin is applying AI ML for tire manufacturing and overall engineering. So Ameya, please.
To be here, okay. Hello everyone, good afternoon. I'm Ameya Divekar, working as a principal data scientist with Michelin. Most of my work in AI is actually around trying to apply AI for 3D geometry. So I started my AI journey when I was with Dassault Systems, where we tried to see how we could apply AI for improving engineering efficiency. And so the challenge was how to apply AI to non-image, non-text, non-structured tabular data. From there on, right now I'm working with Michelin as a principal data scientist. In my current role, I'm leading the Moonshots program, which is one of the 3 pillars we are pursuing at the AI Center of Excellence. One pillar is around working with the more established technologies like CV, NLP, forecasting, and so on. The other pillar is about creating a good infrastructure to be for citizen data scientists to be quickly able to use prototype ML models. And then the third stream is about trying to look out there for the emerging AI technologies which are, and identify, define problems which are kind of high risk but also high reward, and possibly see what we can, how we can gain transformational value with those at Michelin. So I will take you through some 5 or 6 technologies that we've looked at over the past year. Some of them we've gone really deep into, where we've published papers. Others we are still scratching the surface or even in the process of defining. But I hope you find it interesting over the next 20-25 minutes. So the first trend I want to talk about is, of course, everybody's heard about it. In fact, you almost have it every day on your all your social media feeds, which is generative AI. So these are kind of some of the more popular startups that are beginning to get a lot of funding around generative AI. If you look at the funding scene in generative AI startups, it has significantly moved on from 2018 to 2022. You can see that it's almost at an inflection point. 2023 is when I think, in fact, it will be more like a hockey stick curve that you will see with generative AI. So with that, we like with every enthusiast, this slide might appear slightly old because I did it about 3 months back when I started looking at how could potentially some of the generative large language models could be applied at Michelin. So I gave it a very simple task or not a simple task, but a creative task of being able to design or suggest an ad campaign for Michelin winter tires, ChatGPT. And as you can see, I won't read through all of the suggestions given, but already you can see that it's doing a creative job or a perceived creative job of humans quite well. And we are seeing how we could best use this technology for across our marketing, sales enablement programs to try and help them augment their creativity. So this is kind of the ChatGPT algorithm. Won't go into it. But another experiment that I quickly did with something like a Dream Studio app out there was to try and see if we can essentially transform the way we do our design the material around our ad campaigns. So for example, I gave Dream Studio the task of seeing how an SUV in snow with Michelin tires would look like, which could, with the end goal that potentially someday we may not have to spend 300, 400K on every ad campaign, but just be able to have a generative AI model be able to do it for us. Again, you can see that it's not such a bad job. Of course, I imprinted the text on top of the image, but I think even it's done a pretty good job at even coming up with an image that can potentially well portray the strength of Michelin in winter tires. Again, another picture, it could spin up in minutes. Again, if you really look at it, it's still at a very nascent stage. So, if you ask it to generate a girl enjoying sunshine on mountains, you can almost see that in some places it can, it actually does not so. Sorry. Move back. Yeah. So, especially you can see around the fingers of the girl that it's not very accurate. It's actually created more than 5 fingers, but I think it's already doing a pretty good job. But it's not all rainbows and sunshine yet. If you ask the generative AI to generate a Mercedes car with a female driver, probably it's not seen that many samples of those images, and it messes it up. So what does it really mean for Michelin? Of course, we cannot rely on public generative design models to generate ad campaign pictures for us. So the moonshot here would probably be to see how we could use build a generative model within Michelin to be able to take all of the ad campaign pictures that we've ever shot in the history of Michelin, and then be able to possibly come up with new ad campaign pictures. Again, another, how do we really interpret generative AI in the context of manufacturing? So it's all good to see ChatGPT see generated AI images, but the real application that we perceive or we foresee is, for example, if you wanted to, let's say you've built a predictive model for predicting the rubber quality using some of the data at one plant, right? Now, many times whenever a new product is launched, whenever a new product starts getting manufactured on the manufacturing line, it has very few labels. So you cannot really just apply the same predictive model for predicting the rubber quality onto another plant which has just started, the product has just started. So how do you really do you get generative models to generate data for you for a certain plant with the plant signatures for a certain product, certain tire product with kind of the product characteristics, and then with kind of a certain mix, rubber mix for the rubber mix characteristics. So one solution that we initially believe that could help us here is diffusion models, and we plan to cascade these diffusion models across several different aspects of generating new data and possibly experiment with it. Another big trend that we saw over the past year or two, and then again, ChatGPT changes this, but which is of using knowledge graphs and ML. So if you look at a huge company like Michelin, which has more than 100 plants across the globe, you can easily imagine that there are, but you can see that almost across the 100 plants, there are some processes that are very similar. So for example, the tire curing process, it's the same, almost the same across all the plants. And yet all defects that are observed during the curing process or the curing machine are typically very disparately arranged across the globe in different systems, different languages, different ways in which they are captured. And there's no way in which, let's say, an operator in the US who has seen a fault with the curing machine has entered it, and the same fault appears in China. There's no way an operator in China can leverage that knowledge. So we are potentially seeing if we can use all of the textual database of defects and knowledge, use deep learning, use an ontology of the curing process, which means that we are no longer dependent on the language in which it is expressed, the manner in which it is expressed, but we are capturing the concept of the curing process when we create an ontology. And largely our efforts were around trying to create an ontology in a more automated way, because it's very difficult to create one manually, and especially if you want to make it scalable, you want to try and do something that can automate the ontology creation for you. And then eventually be able to match the queries with the diagnostics using a graph database matching or a graph match. Again, here we want to try and unify across all of the languages so that we have like a single source of truth across the globe, and any operator anywhere in the world he has seen a defect that can be leveraged across the globe, across different factories. The third trend that we saw and we invested in significantly was around interpretable machine learning. A lot of our stakeholders, business stakeholders across the globe, were really trying to help us, asking us questions like, can you help us understand what is causing the share of market to decline for a certain product in a certain market? And the predictive models were only so good because they were not really able to explain the causal factors. Yes, there were strong correlations between some factors, but there were no strong causal factors that we could attribute them to. And we experimented with causal inference by setting up a causal inference graph manually, then being able to populate it with the data, and then being able to attribute it with quantified impacts for each of the factors that could potentially influence the share of market in a certain product. Another, of course, popular technology in this is the counterfactuals, where we try to understand if we want to flip a result. Let's say if we want to say that the share of market in a certain market is bad, and we wanted to flip the result to good, what is it that we would have to change, and what is it that is controllable and that is something that we can change, that we can then convey to our business. So that's another technology we've again explored. Again, some of these are more applied problems than research problems, but it's slightly different when you actually apply it in business context with the constraints of data, with the constraints of limited visibility in the business. I think it becomes more interesting. Then we also implemented, or we experimented with trying to, so this is a project where we were trying to identify the characters on the sidewalls of the tires. And we were exploring how we could use interpretable machine learning, interpretable computer vision machine learning, to be able to see why we were making errors on some of the characters than others. So the first thing that we did was, are we even predicting the right mask? Which is where we read papers around interpretable ML around mask detection, which was something like DRISE, and we implemented that paper, tried it out on our computer vision problem, and although that the mask detection didn't really help us, subsequently being able to then go on to use saliency maps over the characters helped us identify some of them. And then the same problem we did for computer vision explainability, we tried on using for accident prediction. So again, here we were able to then, in the middle column, you can see the saliency maps. On the left-hand side, you can see the inputs, left column, and the rightmost column is the road segmentation. So these saliency maps actually, and on the right square tells you the place where the accident happened on the road. So the idea was to see what features has it seen on the road to really call it out as a possible accident spot. So this is the one, the fourth trend that I want to talk about is deep reinforcement learning. This is a moonshot that we started about a year and a half, 2 years back. Again, it was along in collaboration with our stakeholders in France, and this is one area where we really went deep, and we were able to publish a paper last year at the MLDS conference, also which was quoted in the top 5 papers at MLDS in 2023. So the larger problem was that we have a problem of autonomous system control, where if you're trying to create the rubber mix in a plant, you have about 200 variables that impact the quality of the rubber mix. And out of those 200 variables, there are about 120 parameters that you cannot anyway control, which are things like the climate, the temperature, pressure, ambient pressure and so on, but there are about 80 variables that you can control and that you want a RL agent to figure out the values of to then at some point be able to suggest to the process engineer what are the right values he should set on the equipment to get always the right quality of rubber mix. And then, of course, this was done through a simulator or a digital twin which predicted the quality of the rubber mix given all of these actions. So as you can see that it is a highly nonlinear or a continuous state, continuous action, non-model free reinforcement learning problem. And when we started working on this, we had no idea about even when we trained an agent, how do we really even understand whether the agent is previous one? How do we even understand whether the agent is taking any meaningful action? And towards that end, my colleague here, Gaurav Adke, he came up with a variety of training plots or training visualization techniques that we were able to, using which we were able to not only understand what was going on with our reinforcement learning agent training, but we were also able to debug our RL agent training much better than we could do before. And this was required because most of the literature around in reinforcement learning agent debugging was around the gaming domain, where you could see snapshots of the games played by the agent, and then you could understand what is going wrong or what is going well. In a continuous state action problem, you cannot do that, especially with a high dimension of about 80 odd dimensions. So you need a lot of other plots which are relevant. And towards that end, we developed like the training dynamics plots, the agent behavior during training, environment dynamics plots, among others, to be able to understand whether the policy has explored enough, whether the replay buffer has been well utilized, and so on. Again, this entire paper is available publicly at the MLDS, this year's MLDS website. Another problem that we are exploring around reinforcement learning, this one is slightly, which was partially discussed today morning by one of the professors from industrial engineering, which is to do inventory optimization given the different constraints around job shop scheduling. So in a normal environment, job shop scheduling is today done in a very ad hoc manner, or at best it's done using in a rule-based manner. But often when the demand is very dynamic, the production plans are very dynamic, it's difficult to do a job shop scheduling without really having reinforcement learning agent at your disposal. And here we see that a lot of related companies are pursuing a similar line of research, and that's something we plan to pursue over the next year or so. Another trend that we clearly see in manufacturing and also disrupting models around services around automotives is autonomy and robotics. And towards that end, last year we explored this Spot robot from Boston Dynamics. When we evaluated it last year, it came out that, for example, the entire Beijing city, it runs on Michelin tires. The entire Beijing city bus fleet runs on Michelin tires. Can you have, for example, a Spot do an autonomous tire inspection of the entire fleet every night? That was a question we were trying to even understand better. And at last year, it was just not viable with the Spot robot, because the cost of the Spot robot is about $100K just for the navigation in a predetermined environment. When it comes to building the RL around it, building the computer vision around it, it's even more. But this has largely changed over the past year. Today, if you see the landscape, you have these kind of quad robots built by companies like Xiaomi and Unitree, which are now available, at least the base versions are available at the range of $3,000 or $4,000. So that changes the equation largely, and it sparks interest for us to possibly build something around this again. Again, a lot of our automotive inspection solutions currently require a lot of investment in infrastructure. So there's a company owned by Michelin called as Proof Station, which requires you to invest about $100K in being able to drive a car through the station, and it will automatically inspect whether you have any damages or not. But possibly with a robot like this, we could do it much cheaper. This is, yeah. And then the last trend I want to talk about is alternate data sources. This is something that we explored around for our Beyond Tires business. So it's, Michelin has three-pronged strategy for growing its market share, or growing its market, which is, first is with tires, of course, which is something it's been traditionally very good at. Another thing is around tires, and then the last one is beyond tires, where we are building software tools for making roads safer in the United States and helping the road planners in the US understand the probability or the riskiness of any road, any arc at any point, given different data sources. And this was a paper that we implemented from, or we thought we could implement from MIT CSAIL. We realized that once we actually started implementing it, there were a lot of challenges and things were not exactly going as the way they had described in the paper. And that's where we modified it. So here essentially we are using the satellite imagery, the road segmentation network, and the previous accident data to essentially estimate the systemic risk of an accident at any point in a road, on a road in the US. So the way we modified it was we transformed it into a more of an advanced computer vision problem where every data point that we had in addition, so for example, we had the GPS traces, which is something, of course, you can model as another channel in a computer vision problem formulation. But then we also had things like how close is a school to any spot? Is there a supermarket nearby? All of those. So we clubbed all of those point of interest also as each of them as a channel in the computer vision scenario, and then we used an efficient net model to be able to predict what would be the risk of an accident at any point. Again, this required us to do very careful labeling because you cannot just put a one label for any point where there was an accident. If you say that because you're doing a grid-wise prediction for a 120 meter by 120 meter grid, and if you say that a grid has a probability of accident as 1, and then the neighboring grid has a probability of 0, you're inherently creating a bias because that neighboring grid also has a similar road characteristics, similar GPS characteristics, similar count of vehicles. So you had to have some way of modeling better even the labeling. So we've taken some efforts, we've created some equations to model the labeling of the accidents or the risk indicators better. Hence, the hypothesis is that the training will be better and the results will of course be better. And then very recently, again, my colleague Gaurav Adke, he has been experimenting with doing safety analysis from drone footage to have a digital twin of an intersection and then be able to see from the different video streams of the drones, can we forecast how risky an intersection is in a city. These are publicly available data sets, and again, we are pursuing something in this. So these are some of the things that he's trying to extract: proximity of vehicles in a single lane, conflict events like lane change, diverging or merging, excessive accelerations, and study of events with post-encroachment time. So I think, yeah, we can of course talk a lot in detail about each of these, but today I just wanted to give you a landscape of the different problems we are solving, and possibly if any of you are interested in doing internships, find any of these problems interesting, do reach out to Senthil, who is from HR here from Michelin, and we'll be happy to take it forward. Yeah, I think that's all from my presentation.
Thanks, Ameya. So, looks like we have time for a couple of questions from audience.
Hi, thank you for the nice talk. My question is about the accident prediction model. So, has that been applied to a scenario in Indian cities or towns, or would it work the same way?
So it's, that was kind of the first question that I had asked the CEO of that subsidiary, and she said that in India there's no one willing to pay for that kind of service. Okay. So it's essentially in US it's more relevant because every authority has ownership of every road. So for example, the city is responsible for a certain road, the Department of Transport is responsible for other roads, and then there are states, and then there's a federal government that is responsible for interstates and so on. So every agency wants to make sure that their roads are safe because they are also accountable for every this thing. So that's why it's so far it's more relevant for France and for France because Michelin is from France, and US because they're willing to invest in that. But I mean, couldn't agree more that it's more relevant most relevant in India.
Any more questions from audience? One last non-technical maybe. So being a tire company, how do you relate tire performance to the human faces that you were showing in the ad campaign? I mean, I was curious, what is the concept there?
No, I didn't get the question.
So what do you want to show in your ad campaign if a tire is performing good or bad? How does it reflect in the ad campaign?
So I think that's, so our marketing heads, they design personas of people who would be interested in Michelin tires, and then they essentially create ad campaigns around these pre-selected personas. So there are multiple personas that are created with different age groups, different demographics, different males, females, and then they create ad campaigns around that. It's less with maybe a video campaign, maybe more suited to the, but just a picture campaign is more to do with the persona.
Thanks for this very nice talk, Ameya.
Sure.
Again, let's thank the speaker. So the next talk of this session is by Vijay Patnala and Rishabh Sharma, both from Michelin. After this, we have 4 talks by IIT Bombay faculty members. So welcome Vijay and Rishabh.
Good afternoon, everybody. So my name is Vijay Patnana, and I am leading data science and numerical science team in Michelin Research and Development Wing at India. So what I am going to present today is the more on the business challenges side of the Michelin. So my colleague Ameya just presented more towards the trends and the technology, technical or technology landscape of the Michelin problems and the solutions, and I'm more focusing on the business challenges. And after me, my colleague Rishabh will present one use case. Okay. Can I have this? Oh yeah, I got it. Yeah. So partially to answer Alankar's question, tire industry is pretty much perceived as a commodity industry, and Michelin wanted to consider or put ourselves as not a tire industry, but a mobility company. So mobility for us means moving people and things from one place to another place with safety, with efficiency, and with free. So that's where partially the question on why we focus more on people, right? So and people, planet, and the third thing, obviously, we are a company, profits. So the 3 P's are our base. So we give more importance to people than the other 2 as well sometimes. Coming to the business challenges of the tire industry, so Michelin is, as most of you know, is the world leader in this space, in this domain. The tire industry, basically, it's very wide. The tires, right from passenger cars to truck tires, to aircraft tires, to spacecraft tires, and the tires for MotoGP and Formula 1, and also the mining tires. So when we look at each tire, the tire usage conditions and the performance and the road conditions and weather conditions, and also the geographic regions, and particularly the roads in India are way different from the roads in United States or any other country. And the weather in India is very different from the weather in the other places. So like snowy and wet conditions and dry weather and etc. Right? So to be a world leader as a global player is a big challenge, considering the type of the variations we see for the different business lines for the tires, and also the conditions and usage. And the driving behavior is also very different. The speed conditions are also different. So how Michelin is able to maintain its pole position is based on the Michelin's kind of, there are some particular capabilities and features, and also the Michelin's know-how of the tires and the usage conditions and the performance. Okay. And to give a little more deeper into, so to give a little more perspective to the challenges, so we are dealing with a large scale of the problems, right from the navigation systems where the satellites track the vehicles from the thousands of kilometers, and the vehicle, the size of vehicles, and the kind of the understanding of the vehicle and the vehicle dynamics, to coming to the size of the tire, the third one. Sorry. Okay, and coming to the tire, and our data collection and our know-how of the different areas, like right from the GPS and navigation, and also the sensors which we use in the vehicle, and it will percolate into the next stage, like the tires, so where we understand the forces on the tires and the way the tire behaves for certain usage conditions, to the tire, the way it creates the contact patch on the road surface, and the slip conditions of the tire on the different accelerations and the torques that are given to the tire, right? And again, the change of the ground conditions, and again, when we talk about the ground, the surface of the ground, and and the other conditions of the ground, right? Because we talked about wet and snow, etc. And to the last, where we talk about the material characteristics. So the materials that goes into the tire. So there are about 200 different types of materials goes into the tire, and the characterization of the materials and the behavior of the materials will play a major part in terms of generating the performance for the tire as well. Okay, so you look at the scale, we are dealing with the kilometer range to micrometer, nanometer range of the understanding. Okay, so here Michelin has developed the understanding over hundreds of years, because Michelin started in 1889, and since then the way we are trying to understand the performance of the tires for given conditions is evolving over the years. And this is where we believe right now AI can come into the system and challenge our current understanding and help us in identifying more areas where we need to understand better about the tires and the performances and the conditions, and also increase our efficiency of our processes in terms of reducing the time, or in terms of identifying new areas where we probably have some preconceived notions that the tire performs this way because of this reason. But yes, with AI and with identifying those pockets where AI can play a role to help us with challenging our know-how and continue to push us to stay at the market pole position in the coming years. That's where we are looking at AI to play. And with this, I hand over to Rishabh for continuing to talk about one use case which is very relevant in this scenario.
Thank you, Vijay, and thank you, IIT, for giving me this opportunity to present this use case to you all. So the use case that I'm going to be present over here is a tire strength prediction model. So it's a use case under the umbrella of road hazard. So it's a set of tools and simulation methods that we are developing. And tire strength prediction model is one of them. So to give you a context about this, tire strength is nothing but a method provided by the regulatory authorities. And here we push a plunger inside a tire, and then we get basically your plunger energy from the tire. And this is what we are trying to predict over here. So this tire strength test is actually conducted in Michelin worldwide, and the challenges for this are the data collection, the pre-processing of the data, and the feature generation as well. So usually the data is scattered everywhere. It's not just sitting in one place, so you get few amount of details from this test, which is the braking energy, but you need to know about the tire physics, tire mechanics, all the data. Everything needs to be combined, and it has to be predicted and to know the know-how. So moving forward. Yeah. So the approach used was a very basic and general approach to build this model, basically gathering data and all. And there were around 50 plus features that were used to train this model. It's a TensorFlow based ANN model. And a very lot of thinking went behind in creating the features. Like, it was not just created by us, like it was done with the help of domain experts as well. We actually went into a lot of detail into how the model is being trained as well. So the idea was to make a model such that it also understands the physics behind whatever is going behind it. So the model selection was also done while keeping in mind that the physics is relevant, the model is understanding the physics as well. So just giving you a large context, because I cannot go a lot into detail about the features and all. So the R square we were getting was around 97% and MAP 7%. But for a tire designer, these things doesn't matter. Like MAP, R square, all these accuracy metrics, they don't matter to a tire designer. He wants to know what the model is learning, what how the prediction is coming up. So there was a lot of when we were selecting the model, we spent a lot of time in understanding which model is understanding the physics best, and we made sure that also the tire designers are able to understand this. So we made a dashboard. So you might have heard about explainable AI and all. So we use all those learnings inside that to explain how basically the prediction is happening. So basically, just to give you a context of it, this is just a sample dashboard that we had created for the users. So there's a long list of parameters that users can change and all. And they can check, if they build a reference tire and then they build a new tire, they can see what that particular feature is impacting on the new braking energy of the new tire. So that's how it is being done. So the idea is tire designer. So for this, the tire designer, usually the simulation, it takes around 3 days to complete. So for that time, the tire designer can have these breaking energy prediction in hand till the time their simulations are completed, and they can spend more time in designing new tires and all. And this in turn actually also saves Michelin time and money as well. So like in terms of like what we are getting out of this is like we are reducing a lot of time for predictions, and we are like also reducing like saving a lot of money because these tests aren't cheap. Yeah. So yeah, thank you. If there are any questions.
Thanks, Vijay and Rishabh, for the nice presentation. Are there any questions from the audience?
You mentioned something about incorporating physics in the neural network. So how are you doing exactly that? Through some features, or what are you, like if you're comfortable to share that thing?
Yeah, sure. So have you, can I
To start with, what we are doing here is the model results. Okay, so we have our know-how from years, like I mentioned in my content, right? So we have developed the design rules, so which are basically okay if you change something, okay, how the prediction should change, and we validated our model against all those rules which were built. So it is a time-taking process, but we have done that. And physics incorporation is via simulation. So we understand better about how this kind of that tire strength works from the simulations which we conducted on Abacus simulations. Basically, these are finite element simulations. And we kind of, we incorporate those results, and we incorporate those kind of equations into machine learning model, and we train the model accordingly. So that is the way we are looking at for infusing physics.
Because the general assumption is that physics equations are not really much incorporated in neural network. That they cannot reason based on that.
Yes.
Interested how you are incorporating that.
So there are a lot of ways.
Yeah.
This is a
so
kind of a
just to
ongoing
give you a
research.
context, like simply if you can understand, so how a neural network is built, just think about it. What is the difference between a normal ML model and what is the difference between a neural network? It is you can introduce non-linearity into it as well. So if you think it from that perspective, and if you build your use cases around it, you'll see, I'm just giving you a hint. I cannot go into detail, but you can see like a neural network actually is able to understand physics, and there are a lot of ways also to make your model learn physics as well. I won't go into that, but yeah.
No one-stop solution. It is basically like a combination of multiple things and multiple validations all together. You say that okay, the physics and the model is working in the same direction.
Thanks, Vijay and Rishabh, again for this nice presentation. You have.
So we've actually trained a lot of linear models. So we've also used XGBoost, Random Forest, mostly linear models. So we are just comparing all the linear models with the linear models. So this is also ANN regression. So linear regression models. Any more questions?
I think we are good. We can take the.
Sorry, I cannot talk about tire pressure. I cannot talk about features.
Yeah. We can probably continue the discussion during tea break. I'm sorry, we are running out of time. So, thanks again.
Thank you.
So our next speaker is Professor Abhijit Chatterjee from IIT Bombay.
Okay, good afternoon to everyone. Thanks, Alankar, for the invitation. So this talk is going to be slightly more technical than the previous two talks. I hope that's fine. I'm going to talk about accelerated thermodynamic calculations using neural network models. A lot of keywords here. Since this session is about engineering and manufacturing, so I think that the audience would be aware of the importance of thermodynamics in engineering and manufacturing. And when it comes to computer-based design, materials design, discovery, thermodynamic calculations play a big role. So in this talk, I'm going to focus on multi-component solid materials. So these could be like metal alloys or solid mixtures, which typically tend to have fairly complicated phase diagrams. And depending on the thermodynamic phases that are present, the properties can be drastically different. And that's where these calculations come in very handy. And if you look at literature, there's a wide range of calculation methods, some of which are approximate, but those are inferior because they don't have the predictive capability. And on the other hand, there are fairly accurate methods which are very predictive, but they are also expensive. And that's the big challenge. So some of the examples I'm going to talk about, the simulations require typically a few weeks of time. And so therefore, that's the undesirable part. And the focus of this talk is going to be on accelerated thermodynamic schemes, which we have developed in our group, which bring down the time to seconds. So that already is boosting the computational capability and giving speed up of thousands of time. But when we combine with ML, then now the speed up is even larger, so factor of billion times. In just a few milliseconds, we can get the results. So that makes it very powerful. These ideas were first initiated by Gargi Agrahari, and then there have been other students, Aditya, Sohail, Akash, and Swati, who have taken these ideas further. And there are a number of publications which have discussed these ideas, and those you'll find in the detailed abstract which is online. Okay, so just to give you a background, if you look at typical alloy systems, the types of variables of interest would be composition, temperature, and so on. But if you go to something like a nanomaterial, then there are more quantities like particle size, particle shape that start coming into picture. So this is an example of a ternary metal alloy system, gold, platinum, palladium system. And we are looking at cross sections of nanoparticles. And because I'm a chemical engineer, we are interested in using these for catalytic applications. And it really matters which metal species is present at the surface. This is already a fairly complex system. Now, if we bring these nanoparticles in contact with a solution, an electrolyte solution, for example, there could be a variety of adsorbed species like oxygen, carbon monoxide, OH, and so on. And they start interacting with these surface metal species. So not only do you have some phase thermodynamic equilibrium between the surface and the bulk, but now you need to consider the equilibrium between the solution side and the metal side. Okay? And this is not only true for metals, but if you consider ionic materials, semiconductors, it's a whole wide range of applications where this kind of complexity is coming. And ideally, from a manufacturing point of view, what you would like to have is details of the elemental composition profile, the types of phases, the microstructure, defects, and so on, as a function of time, composition, history, and so on. There are lots of variables. And now you can see where the problem is. If you have to do experiments to understand all these relations, the structure property relations, it's just a very difficult problem. So therefore, if we can have simulation methods which can obtain these connections, that makes it a very powerful method, right? So I'm not going to talk about how to build these maps, because that's where machine learning can come in, but rather I'm going to talk about how to generate data points, each data point where if you have certain bulk conditions, thermodynamic conditions, how the materials will equilibrate at those conditions. That would be the focus of this talk. So what is of essence here is that none of these systems are well mixed. You have some preference of these atoms. So if you have considered different components A, B, C, and so on, the interactions between A and B, and so on, would be different from each other, and that gives rise to ordering. You can have phase separation, you can have good mixing, and you can have ordered phases. So in this case, we have A and B kind of stacking up in an alternate manner. Okay? And in these pictures, all of these materials have composition of 50% A and 50% B. So this is a binary system. And the first question is, mathematically, how do I differentiate between these structures? The composition is the same, but you can see the structures obtained are quite different. And the answer is that, well, we can talk in terms of probabilities. For example, if we consider a pair of sites, what is the probability that around an A atom, another A atom would be present? Okay. So if we look at this example here, we have a lot of A around A, and that's why the pair probability is high. Okay, the probability can be between 0 and 1, and this is a high pair probability. On the other hand, in this case, A doesn't like to sit with A. It's mostly A followed by B, and so you can see the pair probability is low. And in this way, we have now a measure by which we can describe the phase behavior in terms of this short-range order parameter. In fact, there can be other types of order parameters. You can consider triplet of sites, or even larger site clusters. And one common type of short-range order parameter is the radial distribution function, which I think hopefully a lot of people in the audience would be familiar with. And this essentially is also a pair probability, analogous to the pair probability I was talking about earlier, but it just extends to multiple coordination shells. So once we have condensed this structural information into certain probabilities, we can also go back. We can do a reconstruction using a method called reverse Monte Carlo, where we basically specify how the ordering should be, and then we do a lot of random moves involving the atoms so that the final desired ordering behavior is achieved. Okay? And now we have a full 2D or a 3D configurational information available to us. So it's possible to go from in a coarse-grained way also, as well as we can get to the microscopic details. Both are possible. Now the short-range order parameter is an extremely powerful concept, and that we can see here. So this is one example, a ternary system, where we did fairly expensive Monte Carlo simulations to get the equilibrium radial distribution function. So that's the radial distribution function. And if we specify just 3 order parameters, which is the silver-silver arrangement in the first neighbor, gold-gold arrangement in the first neighbor, palladium-palladium arrangement in the first neighbor, so all these probabilities are specified to reverse Monte Carlo, then we can get the full radial distribution function which matches with Monte Carlo. The structures are equivalent. All I have to do is just give 3 numbers, and that describes the whole structure. Okay? Similarly, for the ordered phases, again, you just need a handful of order parameters. So this is the way to now describe the whole phase behavior. Now, how does the system choose the value of the short-range order parameter? That is described in terms of these order parameter evolution equations. So first we have a species balance equation, which tells how the population might change. When you are processing, you might have time-dependent quantities, material might flow in, might flow out, and based on that composition, your atoms and molecules may try to order themselves. So this second equation basically tells us about the ordering. And what we do is that we try to solve this system of ordinary differential equations in time, which is very fast, right? You can solve ODEs very, very quickly. But at each time step, we need to know a lot of atomistic configurational details. So for that, we use reverse Monte Carlo. You basically reconstruct the microscopic structure and get the different environment probabilities. So how atoms might diffuse around in different environments. And that is passed to the macroscopic scale. So that gives a more accurate picture of the system. So no more, it's no longer mean field, coarse-grained picture, but rather you have the microscopic details being passed. Okay. For equilibrium, the time derivatives are 0, so you just have to solve a bunch of nonlinear equations. The solution gives us the equilibrium short-range order parameter, and we can get the equilibrium structure. That's it. Okay. Now, where does ML come in? So reverse Monte Carlo is slightly expensive. It takes few seconds to do these simulations, and for each simulation we have to specify the populations and the order parameter values to get the corresponding structure. Okay. Now, if ML can predict these 3D structures instantaneously, then we can get all the microscopic details, and that can be passed to the ODs, which are quick to solve. You can solve them very quickly. Okay. So the strategy we use is we do an offline sampling of material structures with a variety of short-range order parameter values. Once we have sampled the structures, then we construct a neural network model, and then finally, when it comes to solving the equations I mentioned earlier, these are called the probabilistic microkinetic equations, we call them. So the neural network model can be solved in conjunction with these equations to get the equilibrium SRO parameter. So this is the overall idea, and the applications which we have been looking at right now, it's still at a fairly simple level, but we are increasing the complexity. The same method can be used for looking at adsorption, dynamic adsorption behavior in variety of systems. It can be used for looking at insertion and de-insertion behavior. So for example, if you have lithium-ion batteries where lithium might get inserted, or hydrogen storage material where hydrogen might get inserted, we can predict bulk phase behavior as well as surface segregation. Okay. So these are wide range of applications, all being studied by solving this ODE equation, which apparently doesn't have a spatial term, but the spatial aspects come in through the short-range ordering. Okay. So I think I'm running out of time, so I'll just conclude here. So in a lot of these multi-component systems, there's a lot of complexity which comes from the structure, from the time-dependent behavior, dynamics. There are multiple chemical processes, time scales, and so on. And this set of equations we use, one is the species balance equation, which is fairly common. I think everyone knows in the audience. But the second equation is the new equation we introduced, which is the short-range order evolution equation. And that tells us how atoms and molecules arrange themselves in time. And so the kind of scheme we have right now, we can solve these equations for full system in a matter of seconds. And that's much more faster than the earlier simulations which we used to have, which took weeks to solve. So with that, I'll end. Thank you.
Thanks, Abhijit. Very nice talk. Are there any questions from the audience?
Hi, very interesting topic. Just one thing, how does this compare with actual experiments? I mean, have you done any study on
Yeah. So in these examples that I showed, all of them have been validated to experiments. Okay. So the whole framework is a first principles framework, by the way. That means the simulations have been, first we have done some electronic structure calculations to get the model parameters. And that's an expensive part I didn't talk about. But once we have the interaction models available, thereafter this framework is giving predictions. And then we compare to experiments. And experiments typically give a macroscopic picture, right?
Okay.
So when it comes to phase diagrams, that can be compared. When it corresponds to something like an adsorption term, that we can predict. Okay. Right? So these kind of quantities we compare to show that this method works.
Thank you.
Any more questions for Abhijit? One last question. So there is a very well-established theory of 2-point, n-point correlations, and we have discussed about it. So did you reach this methodology coming from that route, or it was an independent find?
I would say it was an independent route because the thing here, is a very special aspect of our method is the evolution of short-range order parameters. So Z, for example, could be a radial distribution function. And we were interested in knowing how the radial distribution function evolves in time. Whereas these 2-point correlations are just giving you correlations within the structure. They're not giving you the dynamical evolution or thermodynamic characteristics, right? So this is on top of all of that information.
Thanks again. Excellent. Let's thank the speaker again. The next speaker is Professor Ammutan Ramabhathiran from Aerospace Engineering from IIT Bombay.
Hi everyone. Yeah, welcome everyone. So thanks for staying back. And so what I want to talk today is some work I've been doing with my colleague Professor Prabhu Ramachandran over the last couple of years. And I'm going to talk about certain models for explainable neural networks in the context of solving partial differential equations, right? And there were already a couple of nice pointers about explainable AI in the previous talks from Michelin and so on. So today I want to talk about the same thing from a more fundamental level, a slightly more fundamental level. Okay. So to start with, I think partial differential equations are, they arise in a variety of different applications. That should be, I think many of you here should be aware of that. So here is a simple example from my field, which is aerospace engineering. And so let's say you want to understand the deformation of a wing when it's subject to external forces, aerodynamic forces, for instance. You can go ahead and set up a bunch of equations that are, where is the pointer here? Oh, okay, never mind. Sorry about that. No, it's fine. I think I was pressing the wrong button. Yeah, happens. Yeah, so you have a bunch of equations that tell you how the internal response of the material arises as a consequence of the external loads that happen, and that typically takes the form of a partial differential equation, right? And the goal in many engineering applications is to kind of predict this internal response so that we can design the material better. For instance, you want to understand the internal stress distribution so that you can learn to avoid the high stress concentration areas, for instance, right? And the typical workhorse in let's say solid mechanics, where you would typically solve this kind of problems, is the finite element method. And I'll talk very briefly about that soon. But the bottleneck is that these methods can be very costly. They are very time consuming for realistic applications. Right? And so the question is, how can you go about making the situation better? Before I go on to the notion of interpretable or explainable neural networks, let me quickly recap the essential ideas behind finite element methods from a more abstract point of view. Okay, so the idea is that your exact solution, the solution that you're trying to capture, lives in some infinite dimensional function space. And that is typically hard to compute. So what you do is you project the solution onto a finite dimensional subspace, which is a lot easier to deal with. Okay, and the key thing about the finite element method is that this projection takes the form of a linear algebraic system, and so that makes it very efficient to solve. And the second thing is that you also design this subspace in such a manner that the resulting linear system is sparse. And that is absolutely essential, because if you're looking at realistic applications, the size of this particular linear system can be very large. So you really need to have sparsity to understand, to have a realistic shot at solving these kind of systems. Right? And so here is a very simple example in one dimension, so where you choose a bunch of what are called as hat functions, and a linear combination of that can give you a piecewise linear approximation of any function. Right? And the interesting thing here is that if you look at it from the point of view of the solution, once you solve it, what you have is a approximation for the actual solution, where these unknown coefficients ui, right, so those are the ones which are computed by the finite element method, they appear in the context of an equation like this, which is completely interpretable. Interpretable in the sense that if you compute the solution ui, that precisely tells you what is the value of the field variable that you're studying at a particular point. The reason I emphasize this is because every single aspect of this breaks down in the context of neural networks, and it's important to understand this flow of ideas. So a very short summary of the finite element method is that it's a very smart subspace projection algorithm. Okay, good. So the latest kid on the block for solving differential equations is the use of neural networks to solve partial differential equations. And the surprising or frustrating point of view thing about this, depending on how you look at it, is that this actually makes the situation worse. From the point of view of numerical analysis, this is an extraordinarily bad idea to use neural networks to solve differential equations. I'll very briefly explain why that is. Okay? But before that, let me explain how this method works. So the idea here is to represent the unknown solution as a neural network. So you have a network which takes the spatial position as an input, and it gives you the field variable as the output. And you can have any kind of deep network that you want as the solution, as the output. And to train the network, and here's where the physics in the name comes about. You choose a different loss function. Instead of choosing a loss function like in typical machine learning applications, what you do is you choose a loss function that is directly related to the partial differential equation that you're solving. Okay? So in this case, let's say you have the system of equations that I showed earlier. You look at the squared residue, the integral of the squared residue, and augment it with terms that are related to the boundary conditions. Now this loss function is exactly 0 when the solution is exact, when the neural network completely captures the solution. But if it doesn't, it's always going to be positive. Right? So that's a very good loss function. But because this loss function depends on the partial differential equation that you're solving, it is supposed to capture some of the physics of the problem. Okay? So the idea looks very good in principle, and once you have the loss function, learning the network is exactly the same as training it using the standard methods of stochastic gradient descent or variance thereof, right? And so this method looks interesting in theory, but in practice it's an extraordinarily bad idea, right? So it actually is infinitely, not infinitely, much slower than finite element simulations. And it's not hard to appreciate why if you look at it from the numerical analysis perspective. I'm going to go back to the previous slide. And if you look at it, something very similar is happening. You have the same differential equation, you have a solution living in an infinite dimensional space, but now you construct your finite dimensional approximation. It's not a nice space anyway, but it's a set of neural network weights for a neural network with a fixed architecture. Now, if you construct it in the standard finite element approach, right, so this subspace has a lot of nice properties. It's a Hilbert space, a lot of beautiful properties, mathematical properties, which we can use to our advantage. The space of network weights of a neural network with a fixed architecture, on the other hand, does not have any of those nice properties. It's in fact, it has some really terrible properties. And so this kind of a simple advantage that you have, a nice subspace, a linear subspace that you have in finite elements, is already lost. Okay? And the second thing is that the projection that you see here, typically the projection happens with respect to a choice of an inner product. And let's say in typical finite element applications, this is related to an energy inner product that gives you a suitable choice for this projection. And that's the reason that results in this linear system. Now what happens is that you replace this projection with a collocation scheme that is coming from the physics-informed laws. Okay? And finally, what that results in is that you no longer have a simple linear equation that is resulting as a consequence of the training. Rather, this projection has to be done by means of a iterative algorithm like a gradient descent, for instance, which is very, very slow in comparison with a linear solver, like what you get here. Right? So from a numerical analysis point of view, it is immediately evident that physics-informed neural networks are a terrible idea, right? But big companies are very happy about that, and there's a lot of money and there's a lot of work that is happening here. Okay, so just to quickly summarize the state of affairs. Okay, the current status with physics-informed networks, despite the fact, the really nice thing about them is that it's very easy to formulate. It's very easy to formulate arbitrarily complex differential equations, and it's easy for people without domain expertise to get into it. But there are a whole host of really serious numerical issues that surround it. Okay, there is no evident way to choose the architecture. The equivalent of this in finite elements is how do you choose the finite element approximation, like how do you choose the mesh. We do have rational ways of doing that. They are much slower, inefficient compared to, and this inefficiency is not a matter of implementation, it's algorithmic, as I mentioned earlier. And the errors are very hard to control locally, boundary conditions are hard to enforce, and I think most fundamentally, they are not interpretable. So earlier I mentioned, for instance, that if you look at the solution here, once you compute the finite element solution, the unknowns that you learn as a consequence of this projection are directly interpretable in terms of the values of the field variables. But if you look at the solution of a neural network, what you're learning are the weights and biases of this network, and there is no direct way to interpret them with respect to the solution itself. And that is at the heart of all the problems related to, let's say, lack of error control. And you put this together, what you get is as a method which is very popular, but nevertheless it's actually, in my opinion, a step backward in terms of how you would go about solving these differential equations. Right? So what do we do about this? Right? So one thing is, of course, don't use neural networks. It's a great idea if your problem is simple enough. But let's say you want to use it, then I think it's imperative to kind of develop interpretable models so that you can begin to address some of these issues. Right? And one kind of approach that we have been looking at in our group is, can you develop architectures that are interpretable? Right? If you use a dense neural network to begin with, you are going to hit this problem because you're turning even the solution of a linear differential equation into a highly non-convex optimization problem. Rather, can you, look at different architectures where the problem is simpler or easier to work with while still remaining interpretable, right? And the starting point is this observation that if you look at the standard radial basis function meshless method, they can be exactly transcribed as a single layer neural network. This is known very well from the 80s or so, right? And just using a standard radial basis function network, you can use the same physics-informed losses and you can train these networks instead of the collocation methods which were used in the 80s. And that itself already gives you a lot of significant efficiency gain. But the moment you understand that these special architectures are interpretable, you can go ahead and then design variations or improvements of that where you can retain the interpretability of the network while still having the ability to use all the techniques that are developed in the context of PINs. Right? So we have developed two variants. For instance, we have developed something called SPIN. It's a spin on the word pin. So just wanted to. These are sparse networks essentially, where we generalize the kernels using neural networks, or we can also have variants where the local widths of the RBFs themselves are learned as a process. These are entire matrices. These are learned as part of the training procedure. Okay. So rather than getting into the mathematical details, I'll show a bunch of examples which kind of makes it clear. To start with, we have a very simple example of an ODE, and of course the algorithm gets it right. But more crucially, once you solve these kind of special architectures, the weights and biases of these networks are completely interpretable. There is a direct link between what the network weights mean and the solution. Right? So it's not like the case of a dense neural network. So here, for instance, we can extract that the points of influence here, the node centers, if you will, where the network prioritizes its solution. So you can see them here. And they also turn out to be more efficient compared to physics-informed neural networks, obviously because they are simpler networks, so it's easier to train. So this can also be applied to all kinds of differential equations. There's no limitation of that. So for instance, here is an example involving, here is an example involving an elliptic PDE in 2 dimensions. And the interesting thing here is that the nodes and circles here are actually visualizations of the nodes, weights and biases of the network. So unlike a deep neural network, you can actually see where the weights and biases are and what they're doing. And here you see that they are kind of adapting to the solution. So here is a problem with the slit. So you see closer to the slit where you want to have finer control, the network is having a smaller zone of influence, whereas farther away you can have larger zones of influence. And of course, if you use the anisotropic version, where you also learn the local shape of the basis functions, you see that you can get the same accuracy with much fewer bases, and they also adapt their shape locally to the solution gradients. Right? And you can also do this for time-dependent problems. So here is a simple animation where we want to understand linear wave propagation. And if you look at the animation on the left, you see that initially, I initialized the weights and biases of the network randomly, but it focuses the weights and biases exactly along the wave front. Right, so it learns that the wave is propagating in this direction. This is an XT diagram, by the way, space-time diagram. And what you're seeing is a space-time snapshot of a traveling wave. And what you see is that the solution, the network weights beautifully adapt to the wavefront. So you already get a lot of interpretability from these models, right? And if you use an isotropic version of the same model, you see that the nodes also locally align themselves along with the solution gradients. So not only are you having a neural network here, which is sparse and interpretable, you can also directly look at and verify that it is actually learning the physics. Right? So this is something you cannot do with deep neural networks, even if you use explainable methods like LIME or Oracle. Yeah. And here is another example to show that you can actually capture really sharp nonlinearity. So here is an example with something called as a Burger's equation. This develops a shock front, which is like a sharp discontinuity in a finite amount of time. And what you're seeing here on the x-axis are actually the node positions. These are actually the network weights. And they cluster around the shock front, and you see that they're able to capture the solution perfectly well. And if you look at the anisotropic zones of influence, they also align themselves naturally along the shock front. Okay, so I think I'm already running out of time. So I just want to conclude by saying that interpretability absolutely matters. Okay, there are many applications for which interpretability is not really a problem. For instance, I think the kind of very nice talk that Professor Abhijit gave earlier, those are examples where interpretability is not an issue because the primary physics is coming from a different differential equation. But if you are trying to use neural networks directly as a means to solve the differential equation, in the best case scenario, it's bad numerical analysis. In the worst case scenario, it is actually irresponsible because these can create artifacts which are hard to control. But the point that I want to, the takeaway point that I want to finish with is that if you want to use neural networks, it is better to use special neural networks with specialized architectures that are interpretable. That will ensure that the solutions that we develop are actually interpretable, and we can learn something from the solution and hopefully do some interesting things with that. Anyway, I'll stop with that. Here are a couple of references to dig in deeper in case you're interested. So thanks again for your time. Yeah.
Thanks, Samuthan. Very interesting talk. Any questions from the audience?
Yes. Yeah. Yeah, so thanks for the question. So the first question, spin is definitely faster than pin. But it is in the same ballpark. It's not faster than finite elements, absolutely not. And the reason goes back to, if you look at the slide where I showed the projection, this is still a non-convex optimization problem. And that's the reason why it works. But if you freeze the network weights and biases, it becomes a linear problem again, and it's as fast as FEM. Right, that's the first thing. The second question was about industry. No, yeah. So can it replace FEM? I hope it doesn't. It should not. Okay, because finite elements is actually a brilliant numerical method with a very strong mathematical basis, and there are robust and mature solvers which are available. These methods are still in their infancy, and as I mentioned, even algorithmically they are not fast enough, right? And the non-interpretability of these methods kind of make them undesirable, I would say, for applications. But in any case, for realistic problems, let's say you're looking at an aircraft wing, or you're doing a full-scale simulation of an aircraft wing, I don't see any reasonable timeline in where these methods, neural network-based methods, can replace finite elements. Finite elements are much, much faster. Yeah.
be applied to, I mean, only this aerospace field, or we can solve any partial differential equations?
Yeah, so there is...
And the second one is,
Yeah, sorry.
like, how much data is needed? Like, I mean, how much should be how much wide or deep should be the neural network?
Yeah, so that's a good question. The first question, it's not dependent on the field. So these are methods that are designed for partial differential equations in general. So the specific partial differential equation I showed in the beginning is just to motivate the discussion, but they are really applicable for any PDE. The second question is actually a very important point that you raised, because if you look at a typical deep neural network, there is no rational way to design the network architecture. How many layers do you need to have? How many neurons per layer? There is no trivial, straightforward answer for that. But here, with SPIN, we can actually go ahead and answer that question. Because if you look at typical solutions, right, let me go back to the linear elliptic PDE. So you know that the solution here has a certain, this is the exact solution from the solution computed using finite elements. So you realize that you need more nodes in this region, for instance. So you can think about a periodic or a uniform distribution of nodes in the domain, and that automatically tells you how many nodes in the network you want to have. So just having an intuition about the domain and the kind of problem that you're solving gives you a direct and straightforward route to design the network architecture. And these are shallow networks. SPIN always gives you a shallow network. They are not deep networks. So the number of layers is not really a problem. The moment you understand that these regions are important for your solution, that can be translated immediately to a particular choice of architecture. That's the point, yeah. That's where the interpretability comes in. The fact that it is interpretable allows you to do that, and that is very hard to do if you're using a dense neural network, a deep neural network.
Time, let's thank our speaker again.
I can definitely answer your questions.
We can
later.
take more questions during
sure.
the break.
But thanks again for your time. Yeah.
Thanks, Amuthan. Our next speaker is Professor Shyamprasad Karagade from Mechanical Engineering.
Hi, good afternoon, everybody. Thanks Sundar for coordinating this and giving an opportunity to present some of our work. So what I'll be talking about is in some of the approaches where you can actually combine solutions of numerical methods with some of the techniques from ML to solve some rather complex problems in materials. So this is a work of students Shiv, Bijay, Utkarsh, and partly from Abhishek and Supriyo, and our collaborators Beta, Peter, and Shankara and Gururajan. So I'll probably spend the next 10, 12 minutes or so just to sort of take you through some of these things. So to give a context which you have already sort of obtained from a couple of earlier talks, is typically if you look at a metallic material which is used for a structural component, you have a lot of structures that are defined at lower and lower scales. So for example, at a less than a millimeter you have some mesostructures, then at micrometers you have small scale microstructures, and then you have interfacial kinetics that is represented by let's say thousands of or millions of atoms, and then you have something very fine. So it's hard to really capture all of this in one single simulation. So you need ways to sort of fasten your predictions or sort of link lower scales through some better information. So our effort is primarily into sort of seeing where we can actually leverage some of those advantages through ML-based predictions. So this is one of the images that many would have seen, and this was an aircraft crash, and you have a problem that was coming from a weld repair, and the fact that this happened because it was not known that the weld repair had certain defects that were greater than a certain size, right? So a predominant engineering interest comes in the fact that whether we can predict, let's say, locations and distributions of the defects in engineering component, and thereby one can obtain a better prediction, right? So for example, these are some of the porosities that are seen in your, probably some of the components in your car engines, and then this could be again in many of the parts where it is a weld joint and you see cracks of various kinds. So they come in different shapes, they come in different sizes, and all of it is quite crucial if it's bigger than a certain minimum size. So these features are formed through a lot of complex phenomena. So one small subset of what really happens is that such features are formed during the process of producing such a component, and they will eventually affect the properties. So for example, you see small scale structures here, and then there are porosities that are at various spots. And on something that you can spot in a naked eye, this is a macroscopic front. So there are lots of things happening which are usually multi-scale in nature. There are multiple phases, components of various chemical compositions, and so on and so forth. And it's often difficult to incorporate all of them to capture either a property or even the state, including all these structures predicted in, let's say, at an engineering scale level. So what are the important things that one really has to sort of take into consideration is, as you've already seen earlier, some simulations can take from weeks to months, and hence it's not viable. And a lot of these difficulties come up because the equations are coupled and they are interlinked strongly. So one needs a better ways to sort of address or make them really fast. And in many cases, the physical description of a system itself is not complete, in the sense that even if you use and solve all the equations that you have, you will still not be able to capture something that's there in, let's say, practice. So where do we really see an advantage of ML coming into picture? So whether ML can replace some of the difficult to calculate calculations. We have seen one such example already in Abhijit's talk. And similarly, can a well-trained model infer some of the missing physical information through the way it has learned the model from various data, right? So that's the objective. So here I'll just introduce a very simple problem just to introduce the complexity. So if you look at even a one-dimensional problem, you have a temperature profile, a composition profile which has a discontinuity, and a few equations that are to be solved in each of the phases, and then you have an interface where some conditions are to be established, right? So in the beginning, we just tried whether pins really help address this, and as we saw a few minutes ago, it was not really. Is the battery on? Okay. Yeah. So as you saw, both in terms of the interpretability as well as difficulty in capturing certain things is not always very easy. So hence, no matter what methods you would try, a seemingly simple problem, but with a moving sharp interface that has a steep gradient, it becomes very hard to be captured by a pin kind of a model. So what I would like to sort of introduce with this context is that you could have sharp jumps occurring at a very small region, and let us call this as a sharp interface. And almost all material interfaces are sharp in nature because they have very thin. However, to handle them numerically, it is made diffuse in many approaches. And that allows you to capture some geometrical characteristics easily, but then they also come up with other overheads. So what can we do to really retain the sharp nature of it while enabling simpler calculations of, let's say, for example, the curvature of this interface through an ML model? So that's where we first looked at what can we really achieve. So for example, here we see a volume fraction field. So here there is a value of 1 and a 0, and then one can reconstruct an interface to represent this. So this is a reasonably continuous information. So you have a 0 value between 0 and 1, and then 1 here. And if you use a diffuse, it would actually spread over a couple of cells around, and hence estimating double D radius and things like that for curvatures becomes easy. Whereas even this, for a lot of small scale problems, it starts giving you incorrect curvatures simply because the gradients are not sufficient. So we first developed a neural network model that captured these curvatures and then used that as a transfer learning model to capture a dichotomous or a pixelated data, which actually becomes something like this. However, it makes the computations of an overall evolution of such features really, really faster. So this was one such case where different kernels were estimated for an output, and then one could sort of reconstruct as well as capture an interface, and then see how that interface evolves, which can be consistent with, let's say, an analytical evolution of simple circle, which is as a function of its curvature. So, and that same thing can be now applied for a variety of other problems. So for example, here there is a single feature that is growing based on different curvatures that are acting on different locations. And so to some extent, the local microscopic details are very well captured, which was otherwise not possible with conventional methods. So there's a poster if you are interested in getting more details. And what I would like to now emphasize is, okay, so that is something that we can get at a micro scale, but how can you really capture sporadic features that are sort of distributed at really, crazy fashion here. So for example, you have spherical as well as really longish, and these are important for understanding where the failure would initiate. So in this context, we looked at what are the possibilities in which we can sort of combine. So let's say there was a model that can clearly capture a local phenomenon, and there are finite element or finite difference based solutions that are highly reliable, highly robust, and that can get you a macroscopic, and then can in some way they be linked with each other while developing a model that will also learn the locations where the defects are likely to occur, as well as their sizes. So this is just a representative example of what happens in a microscopic domain, and then what really happens in a macroscopic domain, and then how they can be sort of combined. So the data for us is really coming from something like a microtomography scan that gives us spatial resolution of very small dimensions, as well as over a large dimension of the component. And we sort of build a framework that trains a one-dimensional ML model that can resolve features that are not represented by, let's say, the finite element scales. And then a finite element model can feed the data that can also train models for a, let's say, 3D machine learning model, right? So this, if they can be sort of meaningfully combined in a locally optimized manner to obtain a prediction, which can be simply based on locations of an engineering component, based on, let's say, some controlled or known parameters of or something that are easily obtained through a macroscopic simulation. So the training gave us reasonably good, and as well as when it was tested on a 3D model, there was a reasonable match with respect to predicted location as well as the size. So the smallest bar here actually represents the deviation or the distance from predicted with the actual defect that was measured in a tomography scan. So, and similarly, one can also get a three-dimensional distribution of this porosity, and which is a defect, and which is a very crucial information, because if you would go to an existing commercial software, you would predict a size that is sort of spread everywhere, so there would not be a location-specific information, because it would identify every zone as a possible defect-inducing candidate. So this was one of the examples that I wanted to just mention, where these have really helped us bridge certain gaps, get faster simulation results, and we are also coming up with or seeing a lot of exciting challenges where this can be taken up further. So with that, I'll conclude. Thank you for the time and attention, and I would like to acknowledge the funders, and feel free to reach out if you have any questions. Thank you very much. Yes, so in the continuum model, for example, there were two cases. One, so estimation of local curvatures in, let's say, when you have a pixelated field data, it was not possible through the regular discretization calculations. So that's where ML gave us the edge. And that was also transferable from a slightly continuous to completely pixelated information.
All right, I think in the interest of time, let's thank our speaker again. Next talk is by me. And we are already running over time. I'll try to do it as fast as possible, so bear with me. So this is an overview talk, and a lot of this you have already seen. But since I spent time on making the presentation, I'll present what I have. This talk is about machine learning for material design and how we use it for mechanics. Right? So I thank all the funding agencies and the students, especially George, who's a lot of work. I'll be sharing today. Some of the work was done by Harat, who is already working for a company, and that work is now being continued by Manish. So when people were not using machine learning very actively, people used to use these kind of charts for material design. So you look at the density as input, and you try to predict what is tensile strength, right? And these charts are available for very well-known materials. There is no composition here, so the material has to be already established. Lot of tests are done, and based on that, you come up with these so-called banana charts, and you come up with a selection of material based on that, right? But that does not work very well, because if you look at the overall material behavior, it is over multiple length scales and time scales, and you think about bonds, and then those bonds create defects, and those defects break the continuity of the lattice and so on. So real material has a lot of defects, and those defects are the ones that define the performance of the components that you are really using, right? So the problem is both forward way and the reverse ways. You have a lot of choices of elements from the periodic table. You come up with any random component, or someone tells you what component to make, you come up with an inverse correlation and precisely tell what is to be done at various length and time scales. It's a challenging problem. On top of all of this, there is also process. This is some data that we received from one national lab in France. So this is additive manufacturing data from TIE64, and depending upon which property you are looking at, the performance can be very, very different. It's a challenging problem. In the sense that if you have a deposited structure and you take the samples, let's say in 0 degree, 90 degree, or call it 0 degree, and this is 90 degree and 45 degrees, the performance of the material for, let's say, stress versus strain can be different. It's kind of intuitive, right? If you look at the fatigue property of the same material, and you don't see any difference here, unless you clean the specimen, have a nicer surface, you start seeing that a clean surface has longer fatigue life, non-clean surface has shorter fatigue life. Same material, more process is giving you a different performance, right? So there is complications there. This is some of our own data. These are conventionally made TIE64. These colors are representing chunks of material which are called grains, and the colors means that the atoms are stacked in different directions, right? For the people who do not know this. And this is additively manufactured TIE64, in which you see a lot of flaky structure. right? So intuitively you can tell that this material is going to perform differently as compared to this material. And as you can see in SEM, some of the additively manufactured Ti64 has some of the powders coming out of the pores, right? So the idea is that we know that the performance is different, and we have measured the performance that conventional material has has more ductility, right? Probably sometimes higher strength also. Additively manufactured material has shorter or less ductility and so on. Even the fatigue life of the conventional material is more, than why are we doing it, right? And for how long can we do it so that we reach some optimum process and material, right? So I'm trying to justify why should we be using ML, well understood or not understood. I mean, do we need it right away? The cost of doing one experiment that I showed you is the following. So one printed specimen is 10,000 rupees, and you do rest of the experimental characterization and mechanical characterization is another 10,000 rupees. There is human resource on which we believe or not, and then there is overall cost, which is lots of INR, right? So we are looking at sometimes 20,000 per test. And you know, if you think about developing so-called structure property process correlation, it is a very expensive business here. So we definitely need something which is going to accelerate it. So the method that we chose before we jumped to ML was that, you know, you do some kind of simulations using which you could create synthetic structures. The first layer is coming out of kinetic Monte Carlo. The second layer is from statistically generated structures, and then I can do some more simulation to impart some residual stresses so that it becomes more representative of additive manufactured material. So I have this kind of virtual environment in which I can choose the elements, right? And I can create the structures and assign the properties to these structures and run some of the simulations that we can based on our developed programs, and look at the performance in cyclic deformation or uniaxial deformation, or fracture analysis and so on. This whole thing is also very, very expensive. Each of these simulations sometimes can, as Abhijit was mentioning, can take sometimes weeks to months. This particular simulation that we published in CMIM last year took exactly 30 days. So, the idea is that if you want to come up with something like this structure process property, you have to do it very fast, right? Collect data fast and do it smartly. So essentially, we are looking at these two types of problems. We have materials, we have collection of elements. We want to know what is the property of that material for our application. Or I have a property that my vendor wants, I want to know what is the material that is suitable, right? So inverse problem or the forward problem. So I'm going to give you now series of examples very quickly. The first problem is in which we collect some data from open databases like Materials Project, and we did some of the calculations of our own using DFT, and we were trying to predict elasticity constants for binary alloys, right? So we collected about 1,400 data points, and the materials involved cubic crystal structures or tetragonal or hexagonal and so on, and there is some bias in the initial data set. There are 42 elements, and some elements are appearing in our collection more than the other. And then we figure out that what are the features that should be used for correlations against the elasticity constants. We come up with some features, for example, ground state energy of that particular binary alloy and so on. And we apply various algorithms like linear regression, neural network, and random forest, and turns out that random forest works very well for the other problem that I will show you for that as well. And then we are able to establish correlation between these elasticity constants and these features, right? This is a standard workflow. I'll repeat it again for a more complicated system, which is having sometimes 4 to 6 elements. These are called complex concentrated alloys or high entropy alloys. Elements are sometimes even greater than 5. And since there are so many elements, all the properties are not available in the databases, right? So what happens is that what is available, based on that, you predict sometimes new properties, and those properties, for example, density is a property that we calculated based on existing features, and then this density becomes a feature for another layer of calculation, and based on whatever we have in our newly generated database, we are able to calculate the properties which are needed for engineering design. For example, we can calculate yield strength, we can calculate peak compression strength, or fracture strain, and so on, right? So it's, if you look at the type of features that we are selecting over the generation of machine learning models, this is a multi-scale problem, right? And not just the composition property correlation, we are able to do now process property structure correlation as well. In this chart you see that on the x-axis we have grain size. For those who do not know, these colored patches are the grains in a polycrystal. On the y-axis we have yield strength, and as you have larger grain size, that relates to arc melted material, and that is predicted by the model that we have established. If you do hot rolling on that, the grain size is decreasing and yield strength is slightly increasing from here. And if you anneal it further, some other reactions are happening in the alloy, and you are able to see even increased yield strength, right? Also, this model is able to predict some novel high entropy alloys which do not exist currently, and definitely some experimental experts need to come forward and try out whether this model is working or not. At least based on the model, we are able to push the boundaries that are predicted by the Ashby chart that I showed you on the first slide. So the Ashby chart said that these are the best materials we have in terms of strength. We are able to predict some materials which are possibly better than that, right? That is to be tried. Not just the composition property, we also tried the models for mesoscale structure versus performance. So in this, we are scanning the structures through neural networks and are relating it to stress in that structure for a given strain, and it does a very good job for this simple structure. We are able to correlate how much stress is coming from which area of the mesoscale structure. So this black region is the region which has higher modulus of elasticity. The white region has lower modulus of elasticity, so it is supposed to give higher stress, and that matches with our finite element models as well. We did this work in 2019, and next generation needs to come where we should be able to predict very precisely where are the local regions from where the stress is coming, right? Amuthan is not going to like it, but I'll go forward. We did use pins for just doing some, high performance simulations because we wanted to do things faster. At least for uncertainty quantification, I can tell you that pins are still good. And maybe we can do the same uncertainty quantification now with a spin. So what we are doing here is that we are looking at simple linear elastic heterogeneous solids where we have various types of defects. Some are void, some are fibers, and we are solving this linear momentum balance equation, right, by using a loss function which is made of the governing equation and the boundary conditions. And we are able to get good solutions here which match very well with the finite element solutions, right? This center column is pins, the left column is the FE. Various types of structures can be simulated, and they can be much better performing if we go for large number of epochs, but it is expensive. Even more complex composite structures can be simulated. Like Amuthan said, that these simulations take a lot of time, and you have to spend a lot of time in figuring out which structure will work for your problem. So it's time consuming, but once the the simulation is or the problem is set up well, you can do things very quickly. And an example is shown here. For example, if you make your elasticity tensor parametric, and you introduce some heterogeneity by changing your elasticity constant as a function, right, of x and y, you can do you can set up your pins problem, and then if you want to do uncertainty quantification, it works very well. So if you want to do, for example, 1,000 FE simulation, let's say 10 minutes each, it is going to take 1,000 times 10 minutes, lot of time. But once your pins model is trained, you can do each pin simulation just in 1 second. The solid lines here are coming from pins, and the dots are coming from FE. And the uncertainty that we are measuring from FE versus pins, they are identical, right? These are some more complicated problems that we are currently working on. This is a fracture problem. This is a static crack problem. We are able to predict very nice test concentrations around static central crack. This is a crack propagating, in which we solve two coupled partial differential equation. One is the linear momentum balance, and this is the phase field equation for crack. The loss function is the strain energy here. If you have any questions, I'll be happy to answer either here or outside. Thanks a lot.
Thanks, Alankar, for a comprehensive talk. So we have time for a couple of very quick questions.
Nice talk, Alankar. So for the high entropy alloys, is there sufficient data for
हेलो नहीं वो चेक कर रहे थे ना सर. हेलो हेलो ओके. So we'll be having computer vision talk after this, so please join that.
Check, hello. Check, hello.
Check.
Check.
ऐसा रख दो ना इसमें, अगर चाहिए होगा तो। हैं? हाँ। पानी ऐसे रख देते हैं, वो नहीं तो डिस्टर्ब होगा. हाँ. So we'll just announce it.
Anybody else? Okay, so welcome to the last session on computer vision. I am Professor Biplab Banerjee, Associate Professor at CSIR and CMINDS. I work in vision and deep learning together. So in this session, in total, there will be 7 talks from industry as well as from IIT Bombay faculties. Without delaying further, we'll start with the first talk, and we have Dr. Shoaib Ahmed from Mercedes-Benz. He's the technical manager there, and he will talk about data-centric AI and their applications in computer vision. So we have the first speaker, Dr. Shoaib. Yeah.
Good evening. Thanks, Professor Biplab and IIT Bombay for giving me this excellent opportunity to share our work, that what we do in our group in Mercedes-Benz India. So the title of the talk is Navigating the Shift Towards Data-Centric AI. We saw a tremendous growth in past decade in computer vision, various computer vision tasks. For example, if we take a ImageNet classification challenge, we came up a long way from 25% error to in top 5 error to at least like 1.9, 1.7% hardly error. All of this because of the increased focus in deep learning from 2012 onwards. But it is very recent that we realized there are like a lot of problems, there are many ambiguities, there are multi-classes that we can, ImageNet data has, and also there's like a lot of label errors in many benchmark data sets, including CIFAR, including ImageNet. So there is a website dedicated itself which shows about what are the errors present in multiple benchmark data sets. So if you go to the production level systems, the main problem, the main requirement there is we should have like a high quality data with very less margin to errors. So this leads to the shift the focus towards data-centric approaches. So nowadays, like in the recent years, in past 1 or 2 years, there is a significant shift. What we can see is like we have a workshop in NeurIPS planned for data-centric. There is a course in there's a course in MIT which talks about completely talks about the data-centric approaches. We have multiple research articles piling up on data-centric approaches, and also multiple startups are working on data-centric approaches. So what is this data-centric approach? If you take the traditional computer vision or a machine learning pipeline, it's a waterfall model. So we have something like data collection, data annotation. Sorry, I think there's some formatting problem here. And then we model the data and then test those model training and test the data. And based on the feedback from the testing, it just loops in, and we try to continually improve the model. So here the most of the focus is mostly on the code or model development and very less on the data. But if you go for the production system with this approach, here the data requirement is very high. We need like a very huge data set, and it often fails in the stress test because we don't know the failure cases where we have to improve the models. So it often fails in the stress test, what we call as like corner cases.
On the other hand, data-centric approaches is the approaches where we start with a smaller data and we train the, data collection, data annotation, and we train the model and test the model. Based on the feedback of the test, the areas where to improve, we collect the data again. So this approach is where what I call is like a balanced approach between the development of model for training purposes as well as for the data, the high quality data. So as I discussed, we can start with the smaller data. So actually the thing is like very small data is sufficient often in multiple applications that can solve 80% of the requirement for that application, be it autonomous driving, be it human pose estimation. But the problem comes when it is unexpected. If you have something like a rare class, or if you have something like unusual activity. So these are the things where we spend lot amount of data. As I can say that it follows something like a Pareto principle. 80% of the data is spent in those 20% of the long tail problem. So the main 80% of the cases can be solved with just 20% of data. So the main objective here is to reduce the data from the bigger part, from this part. It's a very important question and it's very challenging. So following this, in this talk, I will focus mostly on these three topics. One is on zero and no annotation, that is zero shot, few shot learning, and strategic sampling for good annotation or good data for annotation, and how to leverage the synthetic data. So I chosen this topic because we have also contributed something to the literature in these topics, and I will be focusing more on those papers. To start with, on zero shot and few shot, we have published a couple of papers in a couple of years back. So zero shot learning here, it's for the activity recognition, where it's in the generalized zero shot setup, where we have during training we have the classes for scene classes, data for scene classes, and some parameters for the classes where we don't have data. But during testing we have both scene classes as well as novel classes. So the main crux here is like during training we synthesize the features for novel classes with just the parameters what we have, and during inference we try to distinguish between seen and unseen using an out of distribution classifier. So we are formulated this problem as an out of distribution where when we have the data for during inference, we try to segregate it based on whether it's a seen or unseen, and a separate classifier for seen and unseen data. So this helps in making the scene more robust and very good inference even for the unseen categories. So extending this work even for the few shots setup. So here what we did is like we have scene classes with many data samples, so we can represent in features. Using these features, try to compute something called class prototype networks. It's something like similar like Centroid. Use this class prototype to generate, again synthesize some of the data within that cluster. So do this for the scene classes, and when novel class comes in a few shot setting with only few data, try to generate the class prototype, as well as when we have the class prototype, try to synthesize the features for, the number of features what we require for training purpose. So this turns up pretty well for our task of activity recognition. On the weakly supervised weak supervision, we recently published a paper on generating the localizing the objects given only the image level annotation. So the annotations are given only at the image level. For example, here is a dog. So what we had to predict is the bounding book, the localization of it. In this case, so the problem here is if we use like a transformer type model. Normally what happens in the deep learning is like the model is more concentrated or mostly biased towards the discriminative features. So if this is an image, the classification, this is sufficient for a classification. It is biased towards most discriminative. But what we need is little bit, even it is relevant and informative, but not that much. Model might not be seeing that as to be a discriminative. So and also, so For this purpose, we have proposed something like similar to dropout, where we just dropped out the attention for the highest magnitude, just to suppress the attention for that being with some probability, enforcing the model to see also the regions where are not most discriminative, but also discriminative to some extent. So as we discussed, like low annotation or no annotations are definitely an important questions to work on, but it definitely cannot replace the manual annotation. Manual annotations are required in some way. But the problem with manual annotation so the problem with the manual annotation is like when we have the data collected, we have the huge data when we collect. So for example, just assume like we are collecting the data at 30 frames per second, putting a camera in, outside the car. Within 1 hour, we'll get like around 1 lakh images. And just imagine for the day how much we'll get, for a week how much we'll get. So how to, definitely we cannot annotate all the images. We have to find something which is more relevant for our task. So one thing we can do, like what we can do is like we can go for a strategic sampling, what we can go for a systematic sampling, 1 in n, or we can find visually something discriminative images and use those only those images for training. But what we focus more on is something called active learning. Active learning is a method where we ask the model to decide. So might be, for example, so might be these two images visually look similar, but for the model it might be very important. Even though it is a similar, it is redundant, we may think, but for model it might be the more important, that those images may have more important features that will improve the model itself. So simple explanation, what is active learning? So active learning is a method where we have something like unannotated database. We start with a large chunk of unannotated database. As I said, like we can collect a huge number of images and select randomly, or we can also do some self-supervision, some kickstart, and use those for annotators, give it to manual annotators, and initiate the annotated database, and use this for training a model. So once we have a model, we something called as active learning wrapper. This wrapper is a key for active learning. So this wrapper decides what type of images we have to query. So this might be a modification of the model itself, or this might be in a different way we can interpret. And this will define like what images to query from the unannotated database for the next cycle. So the next cycle starts from the querying those images, and update the database, and use this for further updating the model, training the model, and then this loops just circulates. So in this aspect, what we proposed is like to have for the human pose estimation, we formulated the problem as an out-of-distribution problem. Again here, so the thing is like we for human pose estimation we define the key points. Along with the key points, we also define something called a skeletal model. So the skeletal model is nothing but a simple Bayesian construction of the different key points, how it relates to each other. So this can be applied to any things which has a structure, like a hand, human has a structure, hand has a structure, face has a structure, even eyes have a structure. So just expand, so just maximize the likelihood for getting the proper structure of the problem what we have. And use this during inference, just pass all the images which are there in unannotated database, just infer that, and what are the images we have maximum likelihood, we can say that those are the ones which are predicted properly as a structure, but the minimum likelihood, the images which are with very minimum likelihood are the assumed to be that images which are the models has failed, where the structure of a human or any problem in hand has not been given, I mean, it has not predicted it properly. So the structure is not forms a human structure at all. So the next one is on the active learning itself. It's a learning loss method where we try to, we have a model, and this model normally do some activities. For example, let it be human pose estimation itself. It predicts something, a target, and we have a check between the ground truth, and whatever the loss is there, we will have a small module which is attached to the main module itself, and the task of this module is to predict the loss function. What will be the loss during training? Okay, and this prediction loss we have control towards like one more loss prediction loss. So it is like a ranking loss function. So what happens in during inference is like we have a lot of annotated database. With a small annotated database, we train the model, and when we infer on the annotated database, we check what is the loss. So the images which gives more loss are likely that they are not trained properly, and we have to, including those images will definitely improve our model. So we saw some improvement opportunities there, that the ranking loss, whatever is used, is mostly based on comparing two different images in the data, like while training. But if we have the loss predicted and the original loss is even huge, the magnitude is on the higher side, still we don't have scaling in the gradients for the ranking loss. So we just added how to scale the gradients such that if there is the loss is huge, just we can make it, we can give the networks more gradients such that it learns it properly. Active learning is all about annotation, annotating the proper data sets, collecting the data which we can choose, which we can annotate. But there are some use cases where even collection is very difficult. For example, we have some scenarios like outside scenarios. We cannot let the crocodile come into the road and collect the data there. So for this, like one of the method what we see is use of the synthetic data. So in synthetic data, we get like ready available labels. We can model the exterior of the car. We can model interior of the car. And when we model interior of the car, we can model any objects, any actions of the human. Readily we get the semantic segmentation, we get the part segmentation, depths, normals, everything in just one go. So the problem with semantic segmentation is the domain gap. So we have the real image here, we have a synthetic image of the real same person there. The problem here is like, even though what is look as a different, even the model tends to look this as a different entity or the features altogether. So in this aspect, we have published work on domain adaptation techniques. So what we do is the crux of this is like normally we try to have something make the model enforce the model to learn the features from the either from real or from the synthetic to go in one group, like a contrastive learning. We have the classes, so we make the classes of two different domains, the synthetic and the real, to be in one class. Even though the classes of different classes are the different, like we just make like two different clusters where one cluster have the same class belongs to synthetic as well as real. So in that way we enforce the model to learn it properly. Similar way we did in autonomous. So we did for multiple use cases there. So what we are building upon with all this research work. So what we are building on with all this research work is like something like a factory. So we have a factory for a assembly line for the cars. We are also building an assembly line for the computer vision pipeline. What we are working on, it's not just data collection, annotation, model, and testing, but also using of like a proper data using active learning. And when we are in the loop, learn through like a proper incremental methods and use of synthetic data wherever we don't have. Where we don't have leverage to collect or leverage or time to collect them. And also adapt it if the tests are failing, can we adapt them and then test it? So this is a pipeline what we are working on. So these are the things what I said is mostly which are in the public domain, which are most on our contribution towards literature. But our main work is focusing on making the car intelligent in interior as well as how it is there in exterior. So today we are talking about the autonomous driving, level 2, level 3, many autonomous driving at different levels are available already in the market. Can we bring the same intelligence inside the car also? So in this aspect, we have we have a product we have developed in 2020. So this is the this with intelligent interior, what we call MBUX interior assist. So in this you can see a person, we can close the door just by doing the gesture, and get the seat belt just by presenting the, putting your hand there, close the sunroof, open the sunroof just with the gestures. Illuminate the light just by reaching to the light. You don't need to search for where is the button. So this is the old one in 2018, what we propose, what we have. These are the products which are already there in the market that you can buy it. So going forward, we are working on not just on the comfort use cases, what we see as like a gesture and illuminating lights, but also on the safety features, making the driver more alert, making like to be safe for the occupants. So on this, like on the focus on the research topic, what we are working on is mostly on deep learning for quantization, because what the model we put in the cars are something like 10x to 100x than what is in the literature, just because of the constraint what we have, because we cannot put a GPU with which has many constraints like heat constraints. We cannot put in automotive grade, it should be automotive grade hardware, and also the economical reasons. So quantization is one of the important topic what we always work on. And then multitask learning, we are doing multiple tasks. So can we make it into like one multitask so that we can leverage multiple aspects of each task. And active learning, all these things which I have already discussed. On the machine learning side, it's more on uncertainty estimation, AutoML, incremental learning, so which I have discussed that, and also explainable AI, that's obviously required for the future, and responsibility, responsible AI. And when we talk about the sustainability, it's more on the green AI. The applications which we focus on for doing all these activities in deep learning and machine learning is focusing on human body and face parts recognition, eye gaze, head position and head orientation recognition, identity estimation, object localization, activity recognition, etc. So our group has not only worked on the product which is there already, and our group is mostly, what we did, we developed end-to-end in India. So it starts from the conceptualization, starts from the data collection, data annotation, training, testing, quantization, and also like target hardware compiling, and from there putting into the car and testing it. Everything is done in India. So we have around like 20 patents on this topic, and also like around 17 publications on many computer vision conferences as well as workshops. So with this I conclude my talk. Thank you. If you have any questions, we can.
Thanks, Shoaib, for this insightful talk. So any question? We have a little bit of time for question answers.
It's a non-technical question. I just wanted to know where the camera was located when you are doing the interior,
So actually the video is available in YouTube. MBUX interior assist, you can search, and
so
it explains like what is
the CV, the cameras that you're using for computer vision. Do you have separate cameras for front seaters and back seaters? So
it depends. Like we can keep at various places where we need the visibility. So whatever the product what we already have, it has 4 camera setup, 2 at the rear and 2 at the front.
Just wanted to understand how do you set up cameras for that?
It's a big process.
You shouldn't have objects interfering with the.
Yes, obviously constraints are there. You have to work with those constraints.
Okay. So any other question? Okay. So thanks, Shoaib, and so we'll move. Yeah, sure.
So I was just intrigued about that, gesture recognition for sunroof and things like that, So this is a typical problem which we face in different domains also. How do you isolate spurious input? If I accidentally raise my hand, to do something else, and the system detects it as a valid gesture. So do you have a framework to isolate spurious gestures from real gestures?
Yes. So it's like as I said, it's a long tail problem. We have like the 80% of data goes towards identifying those kinds of problems where the human intentions are not there. Can we identify the human intentions and say that this is not a gesture, it's an unintentional movement? So we have already worked on those aspects as well.
Okay, so thanks, Web, for the talk. So we have our next speaker from Adobe Research, Dr. Kuldeep Kulkarni. So he will talk about video editing and manipulation techniques which are done in the latent space rather than on the data actually. Yeah. So Kuldeep, over to you.
So, can you hear me?
Yeah, we can hear you. Yeah.
Okay, all right. I will share my screen. Now. Okay. Can you see my screen? Okay. So all right. So I'm going to give a talk which is titled "Controllable Visual Synthesis." So basically, this is on manipulating intermediate representations for image and video synthesis. Hello?
Yeah, please continue. It's fine. We can hear you.
Okay. Okay. So some peek into some of our recent works. So this is the stuff that sort of I'll try to cover in the next 10 to 15 minutes. I definitely don't have the time to do a deep dive, but I think I'll try to give some ideas on the kind of things that we have been doing. Hello? I'm hearing something in the background. I'm not sure if someone is asking me anything.
No, it's fine. It's fine. You can continue.
Okay, all right. So if I give you this image and if I ask you to extrapolate, what do you see? So what are the kind of, how do you actually go about extrapolating this? Any quick answers? Okay, so if I extrapolate this, basically the grass gets extrapolated, the sky gets extrapolated, the river gets extrapolated, and so on and so forth. Now, if I give you this image and ask you to extrapolate it in your mind, then how do you extrapolate it, right? So if you extrapolate it, you actually end up having to add new objects. For example, you add a table, you add a TV, a table. So all of these objects actually did not exist in the initial image. So there is a difference between the two images and the corresponding extrapolation, the image extrapolation does. So the previous works, and when I say previous works, this is prior to the work that we did, which eventually got published in ICC 2022. We use those methods and try to extrapolate the image that is at the top right corner. Then these are the kind of results that you would get. And why? Because they solely concentrated on trying to use the existing pixels or the existing objects to extrapolate, and hence they pretty much failed in the extrapolation task. Now we see our results. The dotted line here shows the input image, and anything that is outside is extrapolated region. So here you can see a significant difference in the results. Our algorithm is able to add new objects based on the context. It has added people, it has added cars, it has added buildings, has extrapolated the sidewalk nicely. Now, how does this actually happen? This, and also maybe I'll show you a teaser video as well. So we actually keep doing extrapolating again and again. You actually can do a city tour like this. I don't know if the video is actually coming through, but
it's coming. Yeah.
Okay. All right. So how does it work? So the first thing that we do is express the image in a in an intermediate representation rather than trying to extrapolate just using the pixels, which is what the previous works were doing. So we compute the segmentation, image segmentation, or rather the object segmentation map for the input image, and then extrapolate in the segmentation space. So once you extrapolate in the segmentation space, automatically you're forcing it to add new objects because there is you have certain number of channels in the segmentation map, and you're adding more pixels in a particular channel, which corresponds to a particular object. And obviously, we have training data for this, and it's a supervised training of a GAN network. And once we obtain the extrapolated segmentation map, we have a method which can actually compute the instance maps for the extrapolated segmentation map. Bear in mind that we do not actually have the extrapolated image itself yet. So computing instance map is difficult because we don't have the extrapolated image. So we have an algorithm to compute the instance maps directly from the segmentation map. I mean, maybe I shouldn't use the word segment. We estimate the instance map from the segmentation map. So once we have this extrapolated segmentation map and the corresponding instance map, we use the input image and train another GAN network to basically obtain the extrapolated image. So basically this involves this whole pipeline of computing the segmentation map using a pre-trained network, then a GAN network to extrapolate the segmentation map, then another network to estimate the instance map, then finally the fourth network which uses all of this information and produces the extrapolated image. So anyway, these are some of the comparisons with baselines. So as I had shown in one of the earlier examples, the other works which also had used GANs, but they pretty much stayed in the pixel domain when they tried to extrapolate the image. So they fail to add new objects. They work very well. The prior algorithms work very well for extrapolating landscapes, but not while the extrapolation necessitates addition of new objects. So this is for the 8020K bedroom data set. So it adds a lamp, it adds table. I mean, I know the shapes are off, but at least it's able to actually add new objects rather than just throwing some random pixel. Okay, now coming to video synthesis. So this is control level animation of fluid elements in still images. Basically, given a still image, we want to animate the image given the inputs in the form of arrows. So the user basically provides some mask, the region where the image needs to be animated, and also the directions in the form of a very small number of arrows. You can actually see the result here. This also got productized recently. This is a CVPR 2022 paper, but we also productized this. So I'm just going to play this video where we show several examples on which you can use Photoshop elements, Adobe Photoshop elements, to animate your own images. So I'm muting the audio. So the user basically draws the map and the arrows. So accordingly, you can also change the speed and then import it as MP4. All right, so how does this actually work? Given the user arrows, we first compute what is called a dense flow. So which is not a network, it is a sequence of functions that takes in the user provided arrows and then converts it into a flow map. And once we have that flow map, we actually refine that flow map using a GAN network. And this is basically a constant flow map that we assume can approximate the motion between any pair of consecutive frames. So it's a single flow map that we compute for the entire animation, and we make this assumption that the same flow map can approximate the motion between any pair of consecutive frames. So obviously this does not work well for motions like simple harmonic motions, for example, right? Or any or different kinds of motions like circular motion. If the motion in the animation that you want can be approximated using a constant flow model, this method works really, really well. For example, river, waterfalls, smoke, clouds in the sky, all of them basically move pretty much in the same direction throughout the animation. So, so once you have the flow map, we have this network. I won't go into the details of it. It is inspired from UNet, but with a lot of modifications. It takes in the input image and the computed flow map, and it does warping at pretty much every layer, including the image as well as the intermediate features. So we warp the features to obtain the final frame. So we have to do, let's say we want 120 frames, we have to do it 120 times. So the user provides arrows, and then we compute the dense flow using a sequence of exponential functions of the arrows. You can go into the paper for more details. And then from the dense flow, we have a GAN network which refines this dense flow that is estimated. This basically defines the flow between any pair of consecutive frames for the animation. So here are some of the results. So this is the waterfalls. Let's say the user had provided the direction such that the waterfalls had to defy gravity and move upwards, right? Does that actually work? So here we can actually see the waterfalls is going upwards because the user provided arrows were in upward direction. So moving on, I'll talk about cinemagraph generation, which is also single image or still image generation of human clothing. So this is paper that got accepted in CVPR 2023, and this is the teaser sort of image. So given a static image and a direction of the wind, can we create an animation as if can we create a loopable animation depicting the wind direction and the movement associated with it? Now, why do we need a new method? I just showed you a method that works for fluid elements, right? So this works really well for fluid elements, the one which is based on the flow. Now, when we apply the same method for human garments, this is sort of what happens. Let me play this again. It displaces the texture without 3D deformation. So how do we actually account for the 3D deformation in a neat manner? So to this end, we actually compute, instead of flow, we compute surface normal. Given the input image, we first compute the surface normal and then predict the sequence of the surface normals for the subsequent frames. I won't go into details of how we actually predict the surface normals. Basically, it's just a single, it's a network that takes in the surface normal for the first frame, and then it also takes in the particular frame for which you would want to compute the surface normal, and then the output of the unit is the surface normal for the t plus delta t frame. So once we have the predicted surface normals for every frame of the animation that we want, we go back to the RGB frame. So we have the input image and the surface normal for a particular frame. We decompose the image into product of reflectance and surface using some state-of-the-art technique, and we can safely assume that the albedo or the reflectance is constant for every single frame, and then from the normal we can compute the shading. So basically, again, we just compute the product of the albedo and the shading for a particular frame, and when you actually put all of the frames together, it looks like we actually have that motion or the animation. So albedo is constant, and the shading change gives the perception of the motion. So let me show some more results for the clothing. I mean, some of these motions are really, really subtle, so I'm not sure how much of it is actually coming through the video, but I'll share the link to the website of the papers so that you can actually check the results on your computer. I think they will be more conspicuous. Okay, so that's basically all that I had, so I'm open to questions.
Thanks, Kuldeep. So, any question we have? Yeah, Professor Sunita.
Sorry,
So this is really impressive. I am not quite in this area.
I'm not able to hear clearly.
Okay, so if I speak louder, can you hear now?
Yeah, I can hear now.
Okay, so I just wanted to know how much learning is involved in achieving these tasks.
Which particular one?
So, for example, the last one you showed about changing the texture of, the clothing with wind. So, was there any learning involved, or this was just totally based on computing?
I'm missing you in between.
Okay, so Kuldeep, the question is the amount of learning involved in the last task of that you showed, the CVR 23 work.
Okay. So the learning is to predict the normals for a t plus delta t frame given the normal for the first frame. That's a place where we actually use learning, and everything else that comes after that does not involve any learning. So we have two modules. One of them is surface normal computation from the input image, and then computation of the frame given the surface normal. So the second part does not involve any learning. We just decompose the image into reflectance and into product reflectance and surface normal.
And what is the training data for estimating the surface normal in this network?
So that is to compute the surface normal for the input image. So that was a pre-trained model, and then for given the surface normal for the input image and computing it for a subsequent frame. So that one, we had two sets of data sets. Actually, one of them was simulated data. The other one was real data.
So any other question?
Sir. Yeah, so I had two questions. My first one being, you showed it for applying for movement of dresses or movement of waterfalls, but does it also work for a movement of a specific object, like let's say a ball? And my another question was, I read this other paper called Cog Video where they generate frames and they recursively interpolate frames between them to form a continuous video. What is your method of arrows compared to that?
Sorry, I think I understood half of it. So the first ball one, I didn't completely understand the question in the end.
So you said you applied it for waterfalls, right? Or maybe it's like just a continuous body of movement. But what if it's just one object that's moving from one place to another? Does the same model apply to that?
Oh, no. So basically, if you have an infinite extent, then if that object is moving from one point to another point, then you can basically apply this method. For example, waterfalls, it's almost like it has that infinite kind of extent, right? Now, for a ball, you actually have to displace it from one place to another place. So the moment you displace it, you actually have to replace the pixels at which it has been displaced with the background pixels or some other neighboring pixels, which we didn't have to do for the fluid elements. The moment a pixel gets displaced, it is already, we just have to fill that region with more of whatever that existed in that particular object itself. Whereas for ball, when it gets displaced, it has to be replaced by some other object, the pixels of some other object. So it's a completely different kind of approach that will be required for a ball. For a ball, or let's say you throw a mobile phone in the air, right? So it's the same thing applies. So your second question was?
Yes. So the method that you used for arrows, right? Is the other method was you take 2 frames and then interpolate images between them. So
yes. So there are some works which actually try to. In fact, we try to do it using StyleGAN. Similar things. We try to manipulate the latent space. Basically, you have one image and you have another image, and you get latent codes of StyleGAN for both the images, and then you kind of try to interpolate in the latent space and then come back to the RGB space. We kind of try to do, in fact, exactly that before we went for the flow method. But it was actually, that method was manipulating other things also, not just the part that we wanted to animate. So it was actually making changes in, let's say, let's say the mountain also was sort of getting changed. So interpolation, you need to be careful in what kind of interpolation technique you use. Maybe there are some video interpolation kind of techniques do exist, but I'm not sure if you just have 2 frames, you'll be able to fill in all the rest of the whatever 30, 40 frames. I think that might be pretty hard.
Got it. Thank you.
Hello, am I audible, sir? Hello? Hello, am I audible, sir?
Hello?
Hello? Hello?
Try this mic.
Hello? Hello? Okay, so I wanted to ask when you were extrapolating the image, so were you considering the semantic maps or some sort of instance map? Like suppose you have walls there, it is not necessarily the buildings will have the same color or paint while extrapolating. So how are you tackling that problem in your extrapolating case?
So we obtain segmentation map, semantic map, not the instance map.
So how are you tackling in the semantic maps only? Suppose buildings are assigned 1 pixel label. Now the buildings might be different for different region of image. How are you tackling that problem in there?
No, we estimate the instance map from the semantic label.
Okay.
So we estimate, so once we have the extrapolated semantic map, so let me just share my screen and show it again. I think I stopped sharing it. Yeah, so this is the extrapolated semantic map, and this is the corresponding instance map. So there are two cars which are which have different instance labels.
And how are you doing that? Like if the two objects are overlapping, how are you computing the instance from that?
I'm not able to hear actually.
If the two objects are overlapping in semantic map, how are you tackling that to convert it into instance map?
Okay, I'm not sure if I'm hearing things correct, but I'll just try and give a generic answer. I'm just second guessing what your question might be. So once you get the extrapolated segmentation map, we train a network. Basically, it's a supervised thing to obtain the instance map. Now, once you have the instance map, it's not a problem to actually generate different textures for different instances of the same object, because we encode. Once we have the instance map, we have some kind of encoder which actually gives different RGB values for different instances of the same object. So we have another channel which actually I don't have in the figure. So the final image generator takes in the input image, the semantic label map, the instance map, and an encoder which actually tries to give different textures for different instances of the same object. Okay, I think that was your question. I just second guessed the question and try to answer it.
Hello. Yeah, that was it. Thanks, Kuldeep, for this talk. So I think there's no more question. We'll move forward. So thanks, Kuldeep, for the talk.
Okay, thank you.
Okay. Yeah. So our next speaker, Dr. Ranjini Guruprasad. She's a senior research scientist and senior manager in IBM Research, and she's going to talk about precision agriculture in emerging markets. So she's there.
Thank you, Professor Biplab. I would like to share my screen. Should I get started? Am I audible?
Yeah, please, let's start. Yeah, you're audible. We can start now.
Okay, thanks. I can hear you now. Yeah. Hello, everyone. I'm Ranjini Guruprasad. I'm a senior research scientist at IBM Research India. And the topic of my presentation today is precision agriculture in emerging markets and how we've developed a AI-based platform for agriculture. And I'll take a couple of foundational services that this platform offers and go into some details. Just a quick look into this whole ecosystem or the platform that we're offering. So starting with the data, we have the weather company, it's called the TWC, which gives the global weather and climate parameters. We also ingest a lot of satellite data, for instance, Landsat, MODIS, Sentinel-1, 2, and we also have the capability to ingest IoT and local sensing. In addition, we also have various models that we run in-house and also ingest outputs of other physics-based models, which give us various soil parameters. And also, if there is some input coming in from the user, we've had this in the past when we worked with the clients. They've brought in their shape files, they've brought in their yield data and various other characteristics of the crop and the field, right? So spanning from weather to satellite to soil to sensors and user input. These are the data that goes into the platform. And this platform employs AI and the insights and the analytics based on the data using AI. Like I said, we have public and private data, IoT data, and various applications are supported as a part of this ecosystem. It is delivered as an integrated cloud-based managed service. We do support various services like the pest prediction, crop and farm advisory, which could be used by various stakeholders such as the farmers themselves or aggregators such as the pesticide or fertilizer companies, or it could be banks or traders. And these are the various insights that, there are various insights that we deliver to these various stakeholders, right? And this is called the Watson Decision Platform for Agri Business. The various foundational services that this platform offers are crop health monitoring using various indices like the Normalized Vegetation Index, NDVI, the soil moisture estimation, disease prediction, yield, quantity and quality estimation. Quality comes in when we're talking about crops like sugarcane, where we want to understand the amount of sugar, which is very important, because that's one of the key parameters that the aggregators use to pay out to the farmers. Of course, going further down, the crop ID, the acreage estimation, and the field boundary estimation, field boundary identification. So out of these, I will start with the field boundary identification work that we've carried out. So in terms of the field boundary identification, this is for, delineating the field and detecting the areas where crops grow. These are not necessarily the cadastral boundaries which are in the electronic, which are recorded, because at least in countries like India, we know that the field boundaries keep changing due to various reasons. It could be a division of property, it could be encroachment, it could be various other things. And of course, each of the agricultural field with its boundaries is unique, right, in terms of its shape, texture, and various other characteristics. So we want to do this field boundary identification. What are the challenges that exist if we want to do it in a manual basis? It is done, but it is very laborious. And it is not possible to cover a big country like India and do the physical survey of each and every agricultural land and document it, right? Even if it was done, for various reasons, it keeps changing, and it is very intensive in terms of cost and labor to repeat this process. So I've called out all the challenges, and there are also the very small fields that exist in countries like India and Kenya, very specifically, that becomes very challenging. And the GPS error itself, could, because of the small size of the field, could shrink or expand the field because of the GPS error. What are the different use cases that such a service could bring about, or such a capability could bring about? Is you could have electronic twin of your field, hence making it digitally trackable. And given the field boundary, we also can efficiently track what is being grown. Also, we would be able to know what is the crop that's being grown. And various other farm level analytics like the crop health, if we were to alert the farmer with various alerts for pest, or give them information like when is the best time to sow and things like that, we could customize it depending on the field size and of course the various other where they're located and what is the crop that they've been growing. From the crop identification we can do. So these are the various use cases that such a capability could bring about, right? So like I said, called out the various challenges in actually determining the field boundary using a physical survey. So this translates to having very limited training data. If we were to use image segmentation, then also there are some challenges in the sense of there are variations in the color, the low resolution of the images, and can we can we bring out or segment out the non-farm area, because you could have a patch of some other vegetation growing in between your farm. Also, how do we accurately delineate? I think that's the main objective, right? How do we accurately delineate the homogeneous objects and the field boundary? Also, to bring about scalability, because you want to be using this model across smallholder regions in countries like India, Kenya, and other developing nations, and also these big farm sizes in developed countries like the US. So as part of the results, I will talk about how the method or the solution we've developed performs across the large field size and the small field size. So what you see here are some of the satellite view of the images of different farm sizes. So overall framework, right, what we've developed is a mix of image processing techniques as well as machine learning to achieve this delineation with a heavy focus on smallholder countries, small farm holder countries, right? So the input image is these high resolution images, which shows the farm boundaries. What we would want to do as step one is to do the segmentation into candidate polygons. So here, we'll have to cull out a large part of the image that we're interested in, and we also use the land use land cover as a starting point to identify the agricultural and non-agricultural lands. And then, of course, the initial contour detection for the segmentation. So that's like the first step one or stage one. And of course, we will do some operations like erosion, dilation to clean up whatever polygons that we have identified. Now, this initial set of polygons are candidates, but they require further processing, which we call as the post-processing, because it could be subjected to either over-segmentation or under-segmentation. So fields which are small are going to likely suffer from under-segmentation because of the small size. And now we need to go into, we've brought in some heuristics to eliminate the non-agricultural region. Now the non-agricultural region could crop into these whole polygons simply because the land use land cover that we've used may not have the resolution to, pick up those pixels which are the non-ag region. So these are some of the heuristics that we've developed, to eliminate these non-ag regions. So one is that we, based on the geography and some statistics that we have on the field size, the area perimeter, we have some thresholds that we pass these candidate parameters into. And whatever the perimeter and area thresholds that we've determined, if the candidate polygons do not satisfy them, then they're dropped as a first step. And also we want to see the convexity threshold, right? They are not perfect convex polygons, but we want to see if they're close to being a convex. So we do have the convex hull, area of the convex hull and the polygon per se. And then we take the ratio, and again some thresholds that we've set, if they are not satisfying the thresholds, then they drop. Then again the ratio of the area and the perimeter is above a particular threshold, then given the statistics that we've gathered, then if it's over segmented, that's another filtering that we do. And we also want to identify these long, if you can see these long pathways, they could be roads or they could be water channels. The aspect ratio, we detect that they are very long. Then we also drop such areas, which will enable us to get closer to the field boundary that we want to do. And then as stage 3, we want to fragment these over-segmented polygons, right? Like I said, so if we have detected a larger region, then we want to determine these, along the contours, we want to determine the cut points and also the min cuts to further split them. And then also take some of these local characteristics of the field, like maybe the means, to localize the algorithm runs. and again do the edge detection. For instance, we've tried the Canny edge based detector, and we've fed these localized means to further improve the performance of the contour detection. And as a final step, we want to do another round of classification of agriculture versus non-agriculture, right? And for this, we bring in the machine learning aspect. We've taken some training images wherein we've learned the color distribution, the texture histograms, also the, like I said, the shape features, the perimeter and area of manually annotated training data. And then we've run these polygons that we've arrived at to classify them as agriculture or non-agriculture. And at the end, we, after passing through these various four steps, we get to the identified fields. The paper that I'm referring to is mentioned at the bottom of the slide. So going on to some results. So what you see is these agglomeration metric and as well as the fragmentation metric, right? And then we have the small fields and the large fields that I spoke about. So the data for the large fields come from various parts of the US, about 10 images which have fields of average size of 11 hectares. And these 10 images put together cover about 50 square kilometers. And then for the small holder setting, we've looked at 15 images from India and Kenya, which have fields of about 1 hectare average size. And 50% of them are even lower than 0.5 hectare, right? And I have not mentioned here, but they cover about 1 square kilometer in total area. So what we see is for the large fields, the fragmentation is low, which is, because the polygons are large and it's fairly easier to detect the boundaries. But when we come to the more challenging setting of the small fields, we see that the fragmentation, the agglomeration is high because the small fields are getting aggregated or agglomerated into larger fields. So this is one of the observations, but with these results, we've been able to detect about 98% of the large fields and about 95% of the small fields. And qualitatively, we can see that the plots below, the A to D columns refer to the small fields and E to H refer to the large fields. And what we see on top is the images that we've gotten, and the bottom row are the predictions. So we see that the bottom row we do fairly well even with the small field setting. And of course the large field setting, you can see that there are different polygon shapes that are coming in, and the algorithm performs fairly well. So I'll take a pause here because this is about field boundary identification. So if there are any questions before I proceed to the next service. Okay. So after having identified the field, like I said in the beginning, this will help us, go on to further services. And the next one that I'll talk about is the crop identification, right? Again, with the focus of why it is challenging to do it in a country like ours. So again, the same challenges that are just small size and across the fields that are proximal, they could be significantly different crops that are being grown. And also we suffer from the cloud during monsoon where a lot of crops are grown. And if we are using the satellite data, then the optical sensors in the satellite suffer from cloud occlusion, right? As an example, we can see that on the right side, there is a label which says, if we have acquired data starting from the month of April all the way till October, we see that a lot of them have significant cloud coverage. The rightmost column tells us the percentage of cloud coverage, and during the months of June to August, more than 50% mostly is occluded by cloud. So And if we are able to solve this problem, then it does lead to, having a better estimation of what the yield is going to be for different crops across different regions. And this will help the government and various other stakeholders to estimate the price better and manage the supply demand. And also this feeds into a lot of these insurance companies and claim validation, right? So these are some of the downstream use cases of crop identification capability. So what we've done to address this cloud issue, especially because we're using the satellite data, is we've also brought in the SAR data, which is more robust to cloud occlusion than the optical imagery such as that from Sentinel-2. So we've used the VV-VH polarizations, and we've of course done some the processing on the SAR data for calibrating, multi-looking terrain correction, and removing the speckles, right? And as far as the optical imagery is concerned, we are using the Sentinel-2 data. Again, it has a resolution of 10 to 60 meters. The revisit time for Sentinel-1 is 12 to 14 days, and for Sentinel-2 is about 10 days. And also this Sentinel-2 requires the processing using the CentuCode tool from the top of atmosphere to bottom of atmosphere. Now coming to some of the data that we get from these respective satellites is what is shown on the right. On the top is the across the dates for 4 counties in the US, we see the backscatter coefficient. And we see some delay across the counties depending on, we do see different signatures emerge, but there is a delay because depending on where the county is situated and the weather conditions, the planting date differs. And then similarly, if we were to look at the NDVI, we do see some variations come in across the crop growing cycle for the different crops. So this is to show that, using this satellite data, because there is differences in the signatures, we are able to, learn the patterns corresponding to each of the crops and do the crop ID. So the results that we have for different crops are shown here, and using both the Sentinel-2 and Sentinel-1, we see that it's performing fairly well, and this is a confusion matrix that has been brought about, right? And we use NDVI basically using the Sentinel-2 imagery and the VV and VH coming from the Sentinel-1. So we see that sugarcane, paddy, millet, pigeon pea is not there, but sorghum, non-cropland, and built-up. We do see the numbers at about 89.2%, and the ground truth here has been collected by colleagues in the team. So we do have some colleagues who own farms in India, so they've personally gone towards that farmland and collected the samples. So this is the accuracy that we have achieved for fields less than 1 hectare, right? Again, it's a small field setting, so this becomes a critical service for countries like India. And we've also worked with the Niti Aayog and also the KPC in Karnataka government for various crops for crop identification and acreage. As a forward-looking note, we are now moved on to geospatial foundation models, wherein we have a model that we're working with satellite data and with weather observations data. And we are doing this for various downstream applications like crop ID that I spoke about. This is the last slide, I will wind up. And the biomass estimation and also the sustainability applications like the GHG, greenhouse gas emission mapping, right? And in terms of the climate, we're looking at renewable forecasting, outage protection. We are releasing this model as well as the results in the Think conference coming up in May 9th. So stay tuned. So open for questions.
Yeah, thanks, Dr. Ranjini. So any question? So any other question? Okay, so seems like there's no question. Thank you, Dr. Ranjini. So yeah.
Thank you
Yeah.
everyone. Yeah.
Okay. Okay, so we have our next speaker, Dr. Mori Yamada. He's a principal researcher in Fujitsu Research India, and he is going to talk about futuristic AI techniques in human behavior analysis at Fujitsu. Dr. Yamada.
Should I? Hi, thank you for having me here today. I'm Moiri Yamada. Today I would like to I'm going to talk about Fujitsu AI technologies. First, I would like to introduce Fujitsu because you may not familiar with us. Oops. Okay. Oops. Okay. Fujitsu is a #1 IT service company in Japan. We provide services around the world, and our core technology is a core of Fujitsu. We are now focusing on 5 key technologies: computing, data and security, network, and converging. And AI is the center of these technologies. Thank you. And I'm from FRIPL, Fujitsu Research of India. And I'm working on AI with global partners. We are already, our AI technologies are already used by more than 6,000 users globally in a variety of industry and operations. These are just examples. But on the other hand, okay. There are many challenges to AI adoption. Only 90% of companies which are interested in AI have been able to use AI solution in production. This points out the complexity of turning AI into real-world business use case. On the other hand, okay. Okay, and on the other hand, 73% of companies which have completed proof of concept POCs have moved to actual use. So that means POC is very important. Go next. Okay. The problem for successful POC, problem is tailoring AI models. So we have various users in different domains, different companies. So they have their own domain-specific, company-specific knowledge that AI model need to understand. So for specifically for human behavior analysis, customers in retail or manufacturing or energy and utility or logistics and the other domains. So they want to recognize specific behaviors in their work field. So even if we have pre-trained action recognition model, it cannot be used as is. So, for example, in retail, they may want to recognize the person picking up a product. Oh, thank you. Or in manufacturing, they want to detect the person or a worker falling down on the floor, like that. So there are many wide variety of behaviors, and only one pre-trained model cannot recognize that kind of behaviors. Oh, sorry. Yeah. So to solve this problem, we developed a video-based behavior analysis technology called Actualizer. Actualizer consists of two components. One is a pre-trained AI model. We developed our original action recognition model that recognizes around 100 basic human actions, such as walking, sitting, standing, bending, elbow, bending knee, like that. And we also developed the user interface on top of it. That user interface enables us to define the various behaviors by various behaviors as a compositions of the basic actions without any coding. So user can define their specific behavior without any training. So this new technology critically accelerates the POC system, in various domains. Okay, I will show you how it works. Here, this is the user interface, and here we want to detect a smartphone zombie. That means walking while texting. So here you can choose a basic action from the list and connect them to define the specific behaviors. And since you don't need any training or fine-tuning, you can see the recognition result immediately. Okay, and you can also test it on the real world, like this. So here our question is, how can we apply the AI model to the various use cases without retraining or fine-tuning? So one direction is building a large universal network that can be used for all tasks. In this approach, a single model handles any tasks. For example, what color is the cat, or detect a person driving a bike. You can already see the GPT-4 or Flamingo as examples. A drawback of this approach is it is difficult to fine-tune the model to add a specific knowledge. For example, specific word or specific product or specific rule. This is actually important because our customer or our user have their own knowledge. And another direction is dynamically composing a neural module into a task-specific neural network. here we have a library of module. Okay. We have a library module, bottom part, and we can choose a module. Each module is a small neural network, and we choose a module. For example, for task 1, we can choose a filter object module and the query color module to get the color of cat. And for task 2, we can choose the same module first, and then we can choose a related module and the query position module, like that. In this approach, we can add a new module without retraining the whole network. So just add a small neural network and then train that small network only. I'm exploring this direction for compositional task. Visual question answering is a compositional task. Here we give an image and a question about the image. Task is to provide the answer. And object in the image is compositions of visual attributes such as shape and color. And the question is also compositions of linguistic construct or phrases such as where, what, left of, or same as, like that. I worked on this task. This was a collaborative research with MIT, where we propose a transformer module network. Left figure shows a transformer module network, and the right figure shows a standard transformer-based model. Our transformer module network ensures the TMN takes an image and a program instead of a question. A question and the program represent the same information. It can be question can be converted to the program, and the program can be converted to the question. And we built a program-specific network. In this case, filter module and query color module. And each module is a small, just one or two layer of transformer encoders. And we use a completely same transformer encoder for both approach for fair comparisons. This slide shows how it works. The question, input question is how many things are either cubes or spheres that are the same material as the large blocks. And this is a program, and there are two threads. In this thread, white region means a region each module attended. So in this module, a filter size attended to an object, a large object. This filter shape cube attended to a cube, and the same material module attended to the object same as material as the large cube, like that. And the union module merges the two threads, and the counter module attends the region where the previous module mostly attended. So we first evaluate two synthetic data sets. These data sets can test performance for novel visual combination and for novel linguistic combinations. This data set provides these green combination for training and test on these red combination. This data set provides a relatively simple question for training and test on the complex questions. And this is a result where we cannot see the large improvement on novel visual combinations. But actually, yeah, it's improved, but not so large. But on the other hand, on novel linguistic combinations, we can see the very large performance improvement. Actually, standard transformer largely degrades in this case. We can also test our model on more complex situation. I mean, with a natural image. We built a novel test set to test the model, and we could confirm that our model improves the performance in this case also. But the performance gain is relatively smaller than that in synthetic data set, because the question in the synthetic data set more complex. So beyond the modular approach, we combining the foundation model and the modules, neural modules, as on the basics of based on the concept of AI model as a component. And we recently, I mean, in this month, we released our AI platform. In this platform, user can use our AI models as a component and combine our key technology with the others to accelerate the implementation of POC systems. Okay, that's all. Feel free to contact me and collaboration with me. Thank you.
Yeah, thank you, Dr. Yamada. It was very insightful. So, any question do we have?
Yeah, thank you for that talk. There are a lot of very rich models available. I'm wondering whether your Actualizer and other models are available in the public domain for research.
Not for research, but can be used for research.
It can be used.
Yeah.
Oh, I see.
Okay, so thank you, Dr. Yamada.
Thank you.
Yeah. So, our next talk is from one of our alumni, Dr. Janaki Porwal, and he's going to talk about responsible AI. So, he's the founder and chief architect of the company DigiPerfect. Yeah.
Just give me a moment as I become familiar with this. Easy. All right. So thank you everyone for attending this talk, and thank you to IIT Bombay and Professor Biplab and C-Minds for giving me the opportunity. So this talk is going to be a little bit non-technical in nature, which depending on your mood may or may not be a good thing. So I'm going to speak on responsible AI and envisioning an AI-powered rather than an AI-driven future. Now, some of you might be able to understand this distinction immediately, but let me just explain. So an AI-powered future is where AI is actively helping human beings achieve their goals, while an AI-driven future is when human beings start taking major and minor decisions of their life based on capabilities and, more importantly, the limitations of AI. Okay, so we don't want to be living in an AI-driven future. Should I just quit? Okay, so I'll start with something which may seem very orthogonal. Is a issue of AI and copyrights in what people call today artificially generative intelligence. Okay, so this is an example of I'm sure all of you by now know the capabilities of AI in terms of AGI, right? ChatGPT and even Stable Diffusion and other such models. So some researchers recently came up with an interesting use case where one of the images from the training data sets which was copyrighted, and the AGI generated almost a similar looking image, you know. So, and this is a blatant copyright violation if human beings do it, but under the garb of AI, people can get away with such violations, okay. So, what are the boundaries between fair use and theft of art, okay? And what is really the distinction between inspiration and reverse engineering? So these are some of the difficult questions which, you know, in a hurry to adopt AI, people are bypassing, some people are bypassing, some people are actually actively researching in this area. So I'll be explaining how potentially some of this can be mitigated by using the right models and the right, you know, data set. So the problem here is that when we talk about AGI, we are not attributing, forget rewarding, the human contribution behind AGI. It's like we are taking away the face of all the artists, okay? Like let's say there are 3 painters, and if I come and tell you, now here is this AI can replace you and it can do everything which you have been doing. And the painters will obviously feel very dejected, right? I mean, that the skill which I learned over so many years is now some piece of software is able to replicate it in minutes. But what the software is really doing is remixing content, okay? So the terminologies which we use make a lot of impact. So if I tell the same painters, here is a software which can remix the content which have been, you know, which the 3 of you have been painting, and it can generate new forms, then suddenly there is a lot of acceptance, okay? Because it's no longer, it's acknowledging the human contribution. So now this is not just a social cause, but I'll tell you why this is a very real problem for the evolution of humanity itself, okay? So, but for the time being, let me just, in this slide bit, saying that attributing and rewarding the original artists helps develop the right perspective of what we are dealing with. It helps the individuals maintain self-confidence, and a thriving society is only possible when the individual is thriving. So you cannot expect technology to make a thriving society when the individual is not thriving. Okay? It is fair, which is subjective, but more importantly, probably very easy to understand that it is also important for economic sustenance, you know, why we need to reward the human contributors behind the AI. So what happens, I mean, apart from the immediate social consequences, what happens when we do not acknowledge the human contributions, okay, and we rely overly on AGI, okay? So what happens is we fall down into the trap of information and creativity loops, okay? What are these loops? To explain, there is a phenomenon in real life, how ants, you know, behave. Ants cannot see, you know, so they follow each other to reach a destination. Sometimes what happens is, they start going around in circles, okay? So one ant following the another, another following the another, and they somehow end up in a circle. But they feel that that's all they can do. The only thing that an ant can do is follow another ant, okay? And because they are going around in circle, they will get no food, no water. They will keep going around in circle, and they will die, okay? And this really happens. You know, millions of ants die like that. It's very sad. What happens is, we are starting with an artificial intelligence which has been fed on limited human data. Okay, we are not living in an utopia where human beings have the solution to all problems. Okay, now we are suddenly feeding all of our knowledge, which is limited. The important thing is it is limited and it is partial and it is biased. We are feeding all of this into AI, and now ARC, okay, we start with the creative example, but the same thing is actually applicable in more important fields. So the artificially remixed content is what is consumed by the masses. Then it goes on again, other AI systems feed on that. So here you see a human being is training an AI, okay, this is a metaphorical description. And now the same AI is training another AI, okay. So what is happening is, whatever the limitation and biases of the content pool which we are starting with, it actually gets reinforced as we feed in more and more information. So newer generations of AI learns from previous generations ARC, which is the term which we count, artificially remixed content, okay? And we form, like in the case of art, we fall into the trap of a creative loop. What we'll be seeing is the same thing in different forms again and again, okay? And human creativity will stagnate. So information in creative loops can be avoided. You know, the only way to come out of a loop, as you know, is through some external, you know, impetus. So we need external input for positive evolution, okay? And we at DigiPuppet are creating such models where no matter how powerful AI becomes, it will always be monitored and reinforced with human inputs, okay? So this is one part of the problem, okay? Now another problem which I would like to highlight, which we are again trying to solve, is the psychological health impact of AI. So in one of the cases, there's a famous company called Replica, right? They started with good intentions, and people became used to the AI chatbots and forming friendships and bonds with it, okay? And afterwards, due to some restrictions and study, they toned down the AI, okay? They made it less human, and they restricted some features. Now the human beings had become so attached to the AI that some people contemplated suicide, okay? Now, my AI friend is no longer my friend, okay? Or it's no longer human. So we don't want to, make humans go here. So the way we are trying to solve this problem is by choosing AI personalities in a more judicious manner. I mean, it's a very psychological topic, okay? On the left, you see, all of these are scenes from movies. But you see, if we give a very realistic personality to the AI, it's interesting, but it is dangerous. On the other hand, if you give very robotic look and feel, it's dystopian. So the right balance is somewhere in between, okay? So another thing which you might have read about is the environmental impact of AI. So ChatGPT style searches are 10 times more costly per search in terms of money as well as carbon footprint. So, the short takeaway I would like to, because I'm running short of time, is I would like you to take is, let's not use a hammer where a screwdriver is needed, okay? So this is a image of an intern who has joined a large organization. He's asking his manager, should I use bubble sort or quick sort? And the answer is use AI, okay? So let's not do that, okay? Problems which can be solved with fundamental algorithms, we should better be solving them with fundamental algorithms. That will also keep our minds active, okay? This is the only slide which I could not, limit it to be verbose, is the dangers of using a black box, okay? So we're working on a new term called predictable unpredictability, okay? If you make, what is the difference between AI and traditional computer software? Traditional computer softwares are predictable, okay? And AI outputs is not predictable, right? And if we make it too predictable, it loses the fun. We lose out on the fun. But can we somehow make the unpredictability itself predictable? Like when we deal with human beings, we don't know what is going to be your response, okay, when I talk to you. But still I can predict that it is not going to be too far from a normal human being's response. So similarly, through the use of formal evaluation methods, okay, software verifications, we are trying to come up with a methodology. What are the areas in which AI can be made more predictable? Towards the same end, we are also developing some data visualization techniques, because visualizations can be used to uncover deep insights. So imagine if the internal workings of the AI, ChatGPT or anything, can be visualized, okay, if it cannot be understood. Other things which we are working on, these last two slides are a little bit abstract, but we are just not limiting ourselves to pure technical analysis of problems. We also started referring to, we started actually actively hiring psychologists in our company. Although it's a technical company, and to understand the nature of intellect, okay? So all of you know the DIKW pyramid, okay? Data, information, knowledge, wisdom. But we are expanding this wisdom into multiple levels and trying to understand, is, like for example, if I asked you, is ChatGPT wise? Some of you may answer yes, okay? And some of you may answer no, it's not wise, okay? So these are some challenging problems which we are trying to tackle. And yeah, towards the end, we are also actually actively trying to study the synthesis of spirituality in science, because this has become an active debate now that AI will become conscious. Okay. Now, either this is a misunderstanding or it's an agenda, or maybe it is really conscious. I don't know. We are not taking any sides, but agnostically, we are studying the foundations of spirituality in science. And we have a small unit in our company doing this. Okay. So yeah, hopefully I just gave you a new perspective over what problems industries are facing. I mean, not as researchers. And if some of you are interested in joining us, you can drop a mail on these IDs. If you are interested in more information or just directly interacting with me, here are the emails. Okay. So thank you for the answer.
Thanks, Janaki. It was really insightful talk. So for the sake of time, we'll just move on and we can have questions later on. So we have two short talks from IITB faculties. So first one is by Professor Amit Sethi. So he's going to talk about their AI-driven work on oncology prediction.
Hello, thank you, Professor Biplab, for the opportunity. So I'll quickly talk about some work that we are doing in collaboration with people from Tata Memorial and other medical research institutes such as UIC College of Medicine and King's College London. So when we apply AI to medical data, we run into some problems. First of all, we are solving real world problems. These are not standardized data sets. These are data sets on which that are similar to what we might expect if we deploy AI in the clinics. So we will face issues such as shortage of data, shortage of labels and annotations. And then many times doctors don't agree with each other when they annotate this data, label this data. So there is label noise that is there in these annotations. And then there's unexpected data characteristics. So you take data from one hospital which has been recorded using a GE scanner, but then you take it to another, you have trained a model and then you deploy it in another hospital. They may have a Siemens scanner and so forth. So there will be a lot of changes in data. So a lot of our research focus is in developing methods that work with these problems, and yet they give better results, or we are trying to push the results so that we get closer and closer to deployment. So for that, we keep a view of the entire life cycle of AI, not just the model development, model choice, and training and validation, but also we start early with the clinical researchers. So we help them define the problems themselves. We help them review their data. And based on that, we also help them gather the data. So we help them write their proposals, which they take it to their institutional ethics committee and so forth. And then we also have a view on the deployment. So for example, if their deployment environment cannot support very large transformer models, then we will not build very large transformer models for them. And in the end, we will also be looking at the monitoring of how these models are performing once they're deployed. So one of the first initiatives that we are working on with Tata Memorial is building a large cancer image biobank. So currently there are a few biobanks that are image biobanks that are there across the world. The biggest one being the TCGA and TCIA archives in the US. And then similarly there are some archives that are there in Europe also. A lot of these are very focused on Caucasian population, with the disease mix that's more prevalent in developed countries and so forth. So we felt the need that there is a strong case to be made for a data that is India-centric, because the kind of disease mix that we see and the presentations of disease that we see and the kind of equipment that is used is slightly different from what we see in these Western data sets. So this is funded by the Department of Biotechnology, and this is going to be hosted at Tata Memorial Hospital. We have already now gathered roughly 1,000 digitized slides. So what I mean by slide is, if you look at a glass slide that's put under a microscope, that pathologists would view under the microscope, there are scanners that you can use to scan these at very high magnification, so it becomes a gigapixel image, 100,000 by 200,000 pixels, that kind of size. So this requires large data center to store these slides, because each patient would have probably 20 slides and so forth. So what is being stored in this data center or in this biobank is right from the beginning, what is the diagnosis, what is the planned treatment, and then of course the pathology as well as the radiology data, and then follow-up data. So what happened after the treatment, if you look 5 years later, 3 years later, was the treatment successful, did the cancer come back, or was it cured? So now, we are not answering specific questions about diseases using this data, but we are enabling future researchers to be able to answer these questions using the data set. So this is basically an infrastructure or building exercise for the nation and for the society in general. And then we need to annotate this data, and that annotation takes a lot of effort. So we are trying to gamify some of this annotation. So anytime you log into a website, many of them, they are testing whether you are human or not. They will ask you to, click the tiles that have all the traffic lights. So they're not just verifying that you're human, but we suspect that, of course, they throw in some unknown tiles also, because they are trying to use your time to annotate data for their self-driving cars or whatnot. So similarly, we are doing this to our pathologists in Tata Memorial. So every time they log in, not every time, otherwise they will get bothered too much. But let's say every 5th time they log in, we ask them to annotate or click on the tiles that have cancer, for example. So some of these tiles we know the answer, for some of these tiles we don't know the answer. So for the known answers, that basically establishes the credibility or the reliability of the pathologist. And for those where we don't know the answer, we get the annotations. And then we have a system at the back end to see the concordance between pathologists and so forth. So what can we do with these annotations? So here what you see is on the left-hand side, the pink and purple is the inexpensive HND stained slides for breast cancer. And there is a specific form of breast cancer which has to be detected, for which the treatment protocol is different, and it used to be a more dangerous form of breast cancer, but these days it is not that dangerous, because there is a precise treatment available for that cancer. Now to detect that, we used to need genomic tests, but then later on inexpensive tests like the brown slides that you see on the right that have been developed. But can we go even more inexpensive and just detect it in something called HND stained slides, which is on the left, the pink and the purple, because these any surgical pathology lab can prepare. So we basically trained AI models to, these are multi-stage pipelines. Some of them detect nuclei of cells, some of them detect cancer nuclei, and then further bifurcate into HER2 positive and HER2 negative cancer nuclei. So based on that, we have been able to detect these mutations, and then later on, where you cannot even annotate, we have started using something called weakly supervised learning, where you don't even have to annotate, you just give the gross label for the entire slide, and then the AI figures out like where the signal is coming from. And we've got some good success with some of the mutations where we got lucky that we were able to detect it with more than 98% accuracy. But not only that, now AI is pointing out where the signal is coming from, and when we look closely, the features that we see were detected by some pathologists like decades ago, but no one else paid attention to it because they could not teach it to others. But AI is rediscovering the same features that in 1960s some pathologists discovered, but they're not taught in pathology schools because of these new technologies such as weakly supervised learning. Then we also try to model the microenvironment of the tumor, so we know that a tumor repurposes the immune system to do its bidding. And when it does that, it has to be, now with immunotherapy, you have other kinds of therapies that can do better treatment for certain kinds of tumor. So we have multi-stage deep learning pipelines where one stage of the pipeline detects all the all the cells, the other classifies the cells, and the third one will form a graph and then form the a model of the tumor microenvironment using graph neural networks. So with that, we are able to point like what specific features define a certain subtype of cancer. And this is for known subtypes, but we hope that because we have validated it on known subtypes, for unknown subtypes also it will help us discover new features that are telltale signs of that, particular subtype of cancer. Similarly, we work on data with noisy labels, where the labels, let's say 10% of the labels are not correct. And one of the techniques that we use, where we train a model for some time, and then when we look at the distribution of the loss function, if the loss function, the samples that still have a very high loss function, loss value, we think that those are mislabeled. We try to reduce their emphasis in further training and so forth. And based on that, we can improve the results. And then also cautious AI. So once AI has been deployed, the people who are using AI after deployment don't have the same training or the time or the understanding as those who helped you with the research to build the model. So many times they throw things at the model that they're not supposed to throw. So for example, they may change the equipment and maybe even use a better equipment to gather the data that is given to the model. But that doesn't always help the model. So we work on something called cautious AI, where we are basically, it's uncertainty estimation. We're finding the uncertainty. We are making models more cautious, that at deployment, if they see something that is not similar to the training data, they should raise an alarm that my decision is not to be trusted. My decision should be handed over to a human expert. So we are able to now detect these. If you put artifacts in the slides, then it lowers its confidence. If you distort the slides too much, it lowers its confidence and so forth. And same with the radiology data. What happened? Okay. So this is my last slide. So basically what we are hoping is we are now pushing a lot of these models into production in Tata Memorial. So this is an exciting as well as challenging time for us, that we will now start to pit it against experts. I'm not saying pit it against experts, but let's say validate it against the expert opinions, so that we can take on the easy cases and push them more and more to AI. It will take a few years of effort before we can trust AI enough so that we will be able to give the easier cases to AI. But that is exactly what we are going to do in this coming year and going into the future. Thank you.
Yeah, thanks Amit for the nice talk. So any questions? Yeah.
Accuracy, by bringing the individual's accuracy in the role, or is it something else which you use there?
So not the individual's accuracy, but definitely we have thought of using active learning. We haven't put it into use yet, but that is our next plan. Yes.
Thanks.
Thank you.
Okay, so the final talk is by mine, so I'll introduce myself. So what I'm going to talk about, these days there is a huge hype of this vision language models, the large scale vision language models, and how they actually help in dealing with computer vision tasks, in particular cross-domain tasks. So we have some recent works with some of our PhD and master students. I'll just give a brief overview of that. Okay. Till now, as we talk about this visual recognition or James prediction kind of thing, they are basically based on this vision-based backbones, right? The ResNet, the transformer models, and they have suboptimal the semantic meaning, the semantic richness. In contrast, recently we have models like Cleep, Align and all, so which are trained on this vision language pairs, right? For each image you have a text prompt and the model is trained with some contrastive loss. So we have a vision backbone, a text backbone, and then this contrastive loss is there. And these models are very much rich in this transferability as well as the generalization aspect. So, but of course these are very large model, and when we try to use them for downstream tasks, the question is, are we going to fine tune the whole model totally, or we can solve the task with very few parameters, learning very few parameters. Now, by the way, so the Cleep in last 2 years, it has been extremely popular, like people are solving various tasks, be it like segmentation to depth estimation, multimodal learning from sketch and image, all this kind of thing. We are particularly interested in using Cleep for 3 broad domains, one for domain generalization, another for adaptation, and finally the third one for discovering new classes, the thing we call GCD, the generalized category discovery. And I mean, if you see Cleep, I mean, the way we give the text prompt is through this, the photo of a class. This could be anything, this kind of instructional text prompt, which are suboptimal because they are not optimized for a particular downstream task. Instead, we are working on learning these prompts directly. So we have a fixed Cleep model, the backbones, but can we learn the prompts based on the task so that it can solve the task with more precision? This is the main setup, and I'll talk about how for generalization and the class discovery we can do the prompt learning. Okay, so we have this work which is currently under review in IJCV, the International Journal of Computer Vision, which we call StyleLeap. And this is to do with domain generalization. So just to give a context, in generalization we have a source domain which is labeled, and we want to learn a model that can be adapted to any target domain that comes during the test time. So you don't know the test data as we do in domain adaptation. Now if we see this graph, I mean there's a data set called DomainNet which is extremely complex, 6 domains, 345 classes and all this thing. And as we use the vision backbone, the state of the art was SWAD, this model, and which had around 46% average this leave one out accuracy. If we use Cleep model as it is quite equal. I mean, so the pre-trained Cleep model, which is around 44. We did another experiment where we give the domain name directly into the prompt. So this is the photo of a class, this is the sketch of a class, things like that. And if we do that, just simply giving the domain name, the accuracy moves up to 47%. And finally, with the model, with this automatically learnable prompt, we have the StyleLeap. We can reach all up to 52%, almost 6% improvement on this data. So now, how are we learning the prompt? So that's the main point. It's a very simple thing. So in image, what happens if we see the statistics of the feature representation of different layers? So they captured the style information, the domain information, okay? So we are using this knowledge to learn the textual prompt directly. So from every layer of FV, which is the vision encoder, we extract this mu sigma, this parameter, so the instance parameter, the feature statistics, and they are actually the initialization for each prompt. We pass them through a number of this projector, this P, you can see below, and then we get something, and this knowledge we concatenate the like a class information and pass through the pre-trained text encoder of Cleep. Okay, so in this way, directly from the style information which is taken from the visual space, we are converting it into the prompt for the textual thing. So this is the style part, and at the same time we have to look for the content part of the image. We are taking the content information and passing through another set of content projector, and this PA is kind of a fusion that is being done between the style and the content. We get the prompt embedding, we have the image embedding, and simply we do the contrastive learning from here. And with this simple modification, as you can see that on all this 5 benchmark domain generalization data in vision domain, both in multi-source as well as single source, it's actually beating the only vision-based backbone by a large margin, and the other prompting techniques which are there in Cleep, so it's beating all of them, giving the new state of the art in this problem. So other than that, we tried it for some other generalization setting. For example, the top table is across data set, where we train this model, these projectors on ImageNet, and evaluate them on the 11 other data set. And for each data set, the tasks are extremely different from each other. And there also, as you can see, that StyleLeap is able to beat all the previous predecessors by substantial margin out there. And the third table is for single domain generalization, where we have a single source domain, but they are tested on multiple targets out there. Now, these are like some analysis. Since we are using data from multiple layers of the clip, I mean, the immediate question is multi-level data is always good. But we proved that, I mean, if we use multi-level data with other models, so they are not as accurate as clip out there, the style clip out there, because of the fact that we are disentangling the style and content in learning the prompt. Now, after that, we had this work recently published, AppleNet, because this generalization is a very, very important problem with satellite imaging, because as we move to different places, the new objects might come. The images taken by the passive sensors, they are affected by the cloud conditions and all. So we proposed another model of this prompt learning specifically for satellite data. And here our main focus is we want to learn again the image driven prompts, but at the same time we also reduce any ambiguity or any correlation between the prompt tokens. Okay, so I'm not going into much detail of it, but it's using the multi level information but in a different context, using attention and the other kind of stuff. So with that also we proposed a new this benchmarks and protocols for this experiment for satellite images with AppleNet, and it came out to be really interesting out there, the result that we got. Now, so these are some ablation just showing that it gives a very promising feature space and all. And finally, just to further improve clip, we also supplement it with a self-supervised task. Okay, so we get the augmentations of the image, and we want consistency of the augmented images both in the visual as well as in the prompt space. Like if we put this kind of constraint, we see that it's actually beating StyleLeap also. So you can see the last one, the GoPro is the model. So I'm not going much detail because these are in submission now. But with this self-supervision, we are seeing that it's actually also beating StyleLeap for all the generation tasks out there. And finally, the last one. So these are some experiments to show. And finally, I'll just talk about another work where is class discovery. So typically, if we have a training and test data, where in the unlabeled test data, there could be samples from novel classes. So one way to deal with them is open set recognition. So we give the one label to all these unknown unlabeled classes. But this is not good because the unlabeled unknown data may have some cluster structure, right? And that could help in the labeling later on. So the problem that we tackle is we have some labeled data from known classes and we have unlabeled data having known and unknown class sample. The task is to properly cluster this unlabeled data. Okay, so we have to transfer knowledge from this labeled known class data to unlabeled data comprising both known and unknown class samples, and you have to do proper clustering. And this problem came up last year, 2022 CVPR, and so again, of course, nobody used CLEAP in this aspect. So what we tried here is two things. So since we have some label data from some known classes, the model will have some bias towards that. We want to reduce the bias. So what we do on top of this CLEAP's encoder, text encoder, we put a GCN. So we want to preserve the class neighborhood property so that, if two things are neighbor in the original semantic space, they should remain neighbors. And that acts as some regularizer. And we have a series of this metric losses that gives the discriminativeness of the model. And below you can see the results that we have. So here the evaluation is typically done, you evaluate separately on the known and unknown class and the overall clustering technique. So now with this space, with this CLEAP space, we see that like if you train it on the label classes and evaluate on the total unlabeled set with this GCN and all this stuff, so the model is giving some good improvement in all these accuracies there. So in total, this CLEAP is of course good, and because it has this multimodal nature and all, and the good part is that all this model training, it requires few samples, and all the experiments we did with 16 samples per class. It's a 16 short kind of setup. And now we are kind of interested in extending this for more dense prediction kind of tasks like depth estimation, multitask and all these things, where it seems to have some prominence. Yeah, so that was it. Just I wanted to highlight the work with this CLEAP for vision task. Yeah.
So actually, it's very interesting. When you do the domain generalization, that time, whatever the prompt that you generate, is that generated from a set of images?
No, per image. So
per image?
So it's passed to the visual encoder, and
Yeah.
you take the feature statistics of this thing, and they are then passed through the projector network that we have. And
How
so
did you train that network?
right. So I mean, you append the class name with that, right? So that gives the prompt, the typical textual prompt, and you have the visual feature anyway coming from the output of the visual
Yes.
encoder, and you do a contrastive learning between them.
Okay. But so this kind of, but if you actually, I think it's just something very specific to Clip then, because Clip is trained with sort of, photo versus sketch versus, but what are the set of things that it can generalize? It's not clear, right? I mean, suppose instead of like style, suppose if you want to generalize color,
Okay.
then would it work also?
So no, in that case, maybe the feature that we consider that would change. So here our major focus is the style part,
Yes.
because the domains are given by style. So that's why we took this features. But it will change, like if you have the color change and the other.
So
but
suppose if I'm doing OCR and if I change the font,
right.
then I'm not sure if this will work.
Yeah, so that might be case. So we have to take this shape or this other kind of things into
Or if you
account.
consider the standard rotated MNIST,
Right.
you change the angle of
Huh.
rotation.
No, but these features are already like it's good against many transformations. So the way this is trained, it takes into account the many augmentations out there. So it's it's not
Okay,
affected
so maybe
by.
rotations is fine, but
Yeah,
suppose
but
if
there
you
are many
consider
others, of course,
fonts and
yeah,
others,
yeah.
then it sort of, it sort of works for the current data sets for all
Right.
domain generalization.
Yeah, because we are dealing with those data sets only. So, where the clip art, painting, and these specific styles are there.
Okay.
Yeah. Okay. Okay, so if there's no question, so we are ending the session now. And okay, Yamada-san is there and Amit is there. So Shoaib is here. Janaki is there. We have some small. Yeah. Yeah, yeah. Yeah, Yamada-san. Yeah. So Janaki. Thank you. Thank you. Amit. For me? Thank you.
For Biplab sir.
Okay, so this concludes the AI Impact Workshop. Thank you all for being all through the last session, and I hope you enjoy the weekend, and I hope this workshop has given you fresh thoughts, and please, maybe you might want to reach out to the speakers and talk to them, and hopefully this will, the main goal of the workshop was to synergize collaborations, and I hope some collaborations will come out of the workshop. Thank you very much. Enjoy your weekend.